Hello, everyone. How are we today? Oh, I realized I did not pull up my chat once again. Oops, nope, not bad. Sorry, 1 second. Let me pull up my chat. Pop-up chat. There we go. One moment. I forgot to set up something on the stream. I'll be back in just a second. There we go. Now I can see what you have to say. I could bump my camera down. I could bump my camera down. That's fine. Properties. Figure video. You would like that. That is one notch down. Alrighty. So, how's everyone today? Are we having a good day? Are we ready for some more bitty bites? So if you did not join us last time, we started this packet of puzzles by Clover called Bitty Bites. All the puzzles in this are 4x4, and they are tricky 4x4 puzzles, as we discovered. Some of them last time were quite difficult. But we did, up through this page, it had started to get a little frightening and ominous by the point we'd gotten to. And so now we are on to this one. So let's go ahead and open this up and see what we have in store for us. So we can zoom way in like that. Okay, so hopefully that looks reasonable on camera. Looks like it looks reasonable. Okay. Normal 4x4 Sudoku rules apply. A digit in a pink cell tells you how many of the up to 8 surrounding cells contain higher digits than the one in the pink cell itself. And then there is... the rest of it is just blacked out. I thought I was going to be able to select this blocked out part, but no. Okay. So it's going to count how many of the digits contain higher digits. Okay, so let's just write in candidates for each of the pink cells right away. Yep, same rules on Penpa, although good to check. Clover may be trying to get into our sanity here. I don't think that Clover would make the rules different in both places, but we will see. Okay, so this can't be a 1, because if this cell were a 1, it would be saying only one of these digits is higher than 1, and I know that that's not true. And this can't be a 4, because if this were a 4, it would be saying that 4 of these digits were higher than 4, and that's not true. So this is automatically either a 2 or a 3. If this was a 2, is that at all possible? Yes, I think this could be a 2, because if I think about it, if this is a 2, I know that these digits are a 1, 3, and 4, so 2 of them will be higher than 2. One will be a 3 and one will be a 4, and then I could put a 1 here, a 1 here and a 2 here, and it would be correct. So 2 is possible. Is 3 possible? If this is a 3... No, that's not possible, because in order for this to be a 3, it would need to see 3 4s, and it can't possibly see 3 4s. So in fact, this is a 2, this is a 1, and this is a 2. Just to get started. And then these are, of course, a 1, 3, 4. That's not a 1. But that's the only way that this is going to work, because this 2, once we realize this has to be a 2, it's going to see the 3 and the 4 over here, so it needs to see nothing else over here, so it needs to have a 1 and a 2, and the 1 and the 2 have to go like that. Okay. So therefore, this digit needs to be a 3, because it certainly can't be a 4, so that digit's a 4. These are a 1 and a 2, these are a 3 and a 4. Okay, so now... I need to make sure this 3 sees a total of 3 4s. So it sees a 4 here. It might see a 4 here. Oh, and it needs to see a 4 here. Okay. So the 3 can see exactly 1, 4, and in fact will see exactly 1, 4 in these 3 cells. So it sees 1, 4 here, 2 4s here, it needs to see a 4 here. So that's a 4, that's a 3, that's a 4. These are not 4, so they're a 1, 3 pair. Okay, so that is a reasonable place to start. Okay, so now we've got to look at this cell, and this cell actually, this would probably have been the smartest place to start, because actually we just could write in from the very beginning that it has to be a 2. Because this cell is going to see exactly the other 3 digits, and so it can only be a 2, because a 2 will see a 3 and a 4. It can't be a 3 because it would only see a 4, can't be a 1, etc., etc. So in fact, actually, I think the easiest cell in the entire puzzle to write in is the last one we actually wrote in. But this is going to finish up like this. And then we will be done. That was cute. I liked that one a lot. The answer to Ambrose's prop bet was that there were in fact no 8s, as it would happen. But it would have been impressive if there had managed to be an 8 in there, but we did not get one in there. Yeah, I liked that puzzle a lot, and sort of the thinking through the, okay, what can these numbers really be given that I know the Sudoku rules? And the Sudoku rules are quite powerful, as it would happen in the context of a 4x4. Okay, so next we have a tiny top-heavy killer. Place the digits 1 through 3 into the grid so that each row, column, and 2x2 region contains each digit exactly once. Some cells will remain empty. Whenever 2 cells are vertically adjacent, the higher digit must be located above the lower digit. Digits in the cage may not repeat and must sum to the value indicated. A cage may contain any number of empty cells. Okay, so let's carefully read through that again. So we're placing in every row, column, and 2x2 grid a 1, a 2, a 3, and a blank cell. So there is, because of this, 1 blank cell in every row, column, and box, even though Clover does not say that, but that is a consequence of the other rules. And whenever 2 digits are vertically adjacent, the higher digit must be above the lower digit. Okay. So this cage either contains a 1 and a 2, or it contains a 3 and 2 empty cells. The version where it contains a 3 and 2 empty cells is tempting because the 3 in every row has to go... No, the 3 has to go below an empty cell because it's the higher digit that goes on top. So in fact, the 1 in each row has to have an empty spot above it. Because, no. The 3, no, it is the 3. Sorry, this is for some reason just blowing my mind. The 3 has an empty spot above it. Because if this is a 3, then I can't put a digit here. It has to be empty. So the 3s in each of these rows have an empty spot above them. So in one column, I don't know which column, but I know there is a column which has to go 3 blank, and then because of the rules 1, 2. So one column looks exactly like this. Now, that column could conceivably be this column. Actually, let's start. Could it actually be the column I wrote those digits in? Because that would put an empty spot and a 3 here. So this would need to also be empty. So it would need to go empty, empty, 3. The 3 would go there. That doesn't seem to immediately break to me. If I put the 1 and the 2 and the 3 in this column, I think that's okay, because then this sums to 3. I could make that empty. That would be a 3. That looks fine. I can't put it in this column because... Wait, maybe I could? Boy, this puzzle's confusing to me. Because this would be 2, 1. I'm just trying to figure out if this is 2, 1, empty, 3, if that breaks this cage or not. So I would need to have a 1 here and an empty cell here. And then that would work, I think. Okay, so I think I need to figure out something else that's going on. So one column looks like this. Another column has a 3 here. And a blank spot above it. Okay, here's the point. Okay, so one column looks like this. So we're going to fill in the 4 columns, then we're going to decide how to arrange them. So another column has a 3 here. It needs to have an empty spot above it. What goes at the top? Well, the thing that goes at the top has to be a 1 because there's already a column with a 2 at the top. So that'll be a 1 and that'll be a 2. So one column looks like this. One column looks like this. So now one column has to have a 3 here, has to have an empty spot above it, and then so has to have a 1 and a 2 below it in that order. And then the final column has an empty space at the bottom, which means it has to have a 3 at the top, and then I guess we can just write it in by sudoku, a 2 there, a 1 there, and an empty spot. Okay, so these 4 columns are exactly what the 4 columns of this puzzle look like. We just have to decide what the correct arrangement of these 4 columns is in order to satisfy the killer cage. So let's do that. So first of all, this column can't possibly be right. So it's not in the right place. Is Jay saying just flip these 2 and then it'll be right? Is that what's going to happen? No, not quite. Digits cannot repeat within a cage. But a cage can have any number of empty spaces. So this one certainly can't be in the place that it is. So trying to figure out what to do with that. Okay, so now trying to figure out how to think about this holistically. Let's see. So Jay points out that if I flip the middle 2, so 3, 2, 1, blank, and then 3, 2, 1, blank, that makes at least the cages now don't have repeated digits, so that's a plus. Okay, so what if I don't put a 3 in this cage? Is that possible? If I don't put a 3 in this cage, then I need to put a 3 over here. I'm trying to figure out what the logical way to figure this out is, because we're down to only 24 possible ways of organizing this, and I'm sure we could guess into which one it is, but I feel like there's a smart way to figure this out. Okay, this column can never actually be where it is, because in order for this to work, I would need to have 2 empty spaces up here. So neither this column nor this column is column 3. So column 3 is only actually allowed to be one of these other 2. Hey, Nicholas. So column 3 could be what's currently column 4, or column 3 could be what's currently column 1. Okay. So actually, no, not quite. Sorry. Oh, you can't have two empties in the cage. Let's see if we can prove that. I can't put an empty here and an empty here. Let's check that. So if I wanted to put an empty in both of these places, I would need to put this right. I can't have two empties in it. That's an excellent way to see it, Nicholas. So the rules even specifically say you can have two empties in the cage, but I can't because where would the two empties have to go? By Sudoku, the two empties would have to go here. But if I want to put an empty here, the only way for me to do that is to make it this column, which would then make the cage have an empty, and a 1, which isn't going to work. So the cage does have to have a 1 and a 2 in it. And so it's just a question of where the 1 and the 2 go. Hey, Jessica, welcome. Congrats on your feature yesterday. Let's see. So this one's definitely on the outside. 3, 2, 1, blank. And then this was 1, blank, 3, 2. Just to make it look a little bit better. Because I know the 3s are on the outside. Likewise, I'm going to put the 3, 2, 1 here. And put the other one here. This will be 2, 1, blank, 3. And that's, of course, still not right. But I think I could flip column 2 and column 4, and I think then it'll be right. No, it won't. Okay, so let's think about it this way. If this column is here, then the column that goes in this spot has to be this one. Is that possible? So is it possible that this is in the correct column, and this is column 2? Then this would go, well, let's just write it in. Why not? This would be 0, 3, 2, 1. This would be the remaining ones. This would go 1, blank, 1, blank, 3, 2. Now, certainly as is, this isn't going to work. So I'd have to flip the outer 2. So this would be 1, blank, 3, 2. This would be, now this would be the 3, 2, 1, blank. Okay, that doesn't work either. So, okay, so I think we can actually convince ourselves this column can't be right. Because now with this column here, I need to have this column here. And even if I swap the outer 2, it doesn't work. So this column is not column 3. This column we know is not column 3 either. So that's 2 columns we know aren't column 3. Oh, and we know this column's not column 3. Okay, so we know what column 3 is. Column 3 is this one. So this is 1, blank, 3, 2. And so this is going to be 2, 1, blank, 3. And of course, in order to make the 3 cage work, I'm actually going to have to put the 2, 1, blank, 3 there. Go ahead and set that out. So the other one is blank, 3, 2, 1. And that seems to be it. So we definitely did a logical solve in that we proved that only one column could go here. And once that column went there, then everything else sort of fell into place. But I feel like there was probably a smarter way to figure out that that column had to go there than by trying all the others and screwing them up. Because that did not feel like the intended solve path for that puzzle. I do not know. I think Clover's working today, so we will not learn until much later, if ever, if Clover had a different thing in mind. But I feel like there was a smarter way to do that than by sliding columns around until it worked. But I really like the fact that the rules actually force exactly what the columns are. I think that was super cool. The columns are these 4 strings. It's just a question of what the order is. I really liked that logical bit, and I'm curious if there was some secondary piece that we missed in there. All right, but we have more bitty bytes to do. Okay, so next we have tiny arrow cage sums. So normal 4x4 rules. Digits in a cage may not repeat and must have the same sum as the digits along the diagonal indicated by the accompanying arrow. Digits along a marked diagonal may repeat, and the sum of a diagonal does not include the digits in the cell containing the arrow. Okay. So basically, this killer cage is giving us the sum of this diagonal. Sorry, is giving us the sum of these 2 cells. So in particular, that's telling us that the sum of these 2 cells is equal to the sum of this cell. So this cell has to be a 3 or a 4. Just because we're saying this sum is equal to this sum, so just subtract the common element. So these 2 are the same. Let's see. I will switch back to shade mode just for a second, just so that we can see this. Okay. Now this cage is the sum of these 2. So now one thing I see is that this cage sums to a minimum of 6, and so these 2 need to sum to a minimum of 6, which means there's definitely a 4 on this diagonal somewhere. And so these are either 2, 4 or 3, 4. They have no 1s in them. Hey, Silva, welcome. Let's see. And so this is either 1, 2, 4 or 1, 2, 3. Hey, Anti-Knight. 1, 2, 4 or 1, 2, 3. Okay, so... but the... So... I think we're supposed to use the 4x4 thing that this cell is in the cage. Because one of these 2 cells is that cell. And so, again, we could play the subtracty game, and what we would get is that this cell is the sum of 2 other cells in this cage. You can psychically predict who the next person in chat will be. Yeah, the chat lag, I swear, on YouTube is getting worse and worse now. It's caused a lot of lost GeoGuessr streaks on Rank's stream. So in particular, the upshot of that, and it's not a huge upshot, is this cell can't be 2. Now one of these 2 cells has to be a 1, because again, these 2 cells sum to this cell. So one of these is at least one of those is a 1. So this cell's also a 2, 3, 4, for whatever it's worth. Now, this cell is included in the sum of this cell. Again, I don't know which of these 2 it is, but this cell and one of these 2... no, I did that backwards. Sorry, I said the wrong thing. One of these 2 cells is that cell. So 2 of the cells in this cage sum to this cell. That's the one that's not 2. Still true to say there's a 1 in here. I just marked the wrong cell. Now, I don't know which cell it is of these 2 that's included in that one. But I know that this one's included, so this one definitely can't be a 4. So this is at least 1, 2, 3. Bitty Bytes 2. Yes, we are doing Bitty Bytes 2. Yes, one of those 2's a 1. Oh, okay. So these 2 cells are these two cells. That's got to be powerful, because, yeah. Okay, so that's the point, I think. This cell is also in this cage, just by Sudoku. Where's it going to go? It has to go here. This cell and this cell are the same value, because these two cells, remember, those two sum to this. So this is 3, 4. And I'm going to go ahead and pick a different color. Sorry, I'll try not to scroll. I'll pick a different color, and let's make both of those blue, so that we can remember, hopefully, that that the sum of yellow and yellow is blue. So now those two also go there. That's a good point. We can continue our Sudoku with blue and just sort of finish up our Sudoku with blue, as chat points out. So that's a 3, 4 pair, actually. So this is a 1, 2 pair. That's a 1 or a 2. In fact, it's that 1 or 2, just by Sudoku. So maybe we lose our yellowness and just mark that those two are the same, and then see if we can figure out more about green. Maybe I don't immediately know more about green, but I do know these two sum to blue. So this is the other 3 or 4. Right. So this sum is 7. So because this sum now literally, I can just read off, it is 7. That means that this cage is 1, 2, 4. Now the 4 in this 1, 2, 4 cage is here, which gives us that this is a 3. Haha. So that's the 4. That's the 4. That's the 4. That's the 4. So the sum here is 8. So this needs to be a 1 and a 3. So that's got to be a 1. That's a 1. That's a 3. That's a 2. That is a 2 and a 1. And a 2 and a 3 and a 1. And a 3 and a 2. Love that. Love that. That one I feel like we found the intended path. So I'm very happy with that one. That is one of my favorites of the pack. Okay. Oh, sorry. No, we've got tiny XY differences first. Okay, so let's read how tiny XY differences works. We've got an arrow that says dread left, and then it looks like we've got 4 here, and then we've got whatever on earth this is, and then we've got this craziness. So medium amount number, maybe, possibly. Let's see. But we should get to none Bitty Bytes puzzles, but I'm enjoying these. So Playmaker says 4 small and 2 big. Okay, so normal 4x4 rules. 2 digits separated by a diamond have a difference of n, where n is the topmost digit in the column if the digits are vertically adjacent, or the leftmost digit in the row if the digits are horizontally adjacent. All possible diamonds are given. Okay, so the difference of these two cells goes here. The difference of these two cells goes here. So the difference of two cells in a 4x4 is at most 3. And it can't actually be 2. No, it could be 2. Never mind. Sorry, don't listen to me. So these are 1, 2, 3. Now, that's 1, 2, 3. This is also 1, 2, 3. By the fact that it's the difference for this column. So I guess the obvious question to ask is, are these two cells the same cell or not? Because if those two are the same, then those two are the same. Doesn't seem like a problem to me immediately. Oh, let's think about it this way. Could I not have one of these be a 3? If neither of these is a 3, they're a 1-2 pair. The only way to get a difference of 2 without using a 2 is with a 1 and a 3, because the other way to make a difference of 2 is a 2 and a 4, but I can't have a 2 across from a 2 and a 4. So I could have a 2 across from a 1 and a 3, but that doesn't work because it then forces the other one to be 2, 4. So these actually can't be 2. They have to be 1, 3. They have no choice. So this cell is 2 or 4, just by the column. This cell is 2 or 4. So again, the point was, if I make one of the differences 2 for this box, it forces the other difference to also be 2. And so that doesn't work. Oh, and I see Jay got it as I was explaining that. Jay also sees it. That was a very cool twist that I did not see coming. Okay, so if this is a 1, this is a 3 and a 4, or a 3 and a 2, I suppose. If this is a 3, this is a 1 and a 4. All of that works out okay. Okay, so I need so one of these, by the way, I can say this. One of these is a 1, 4, which means the other is a 2, 3. Yeah, so one of these is 1, 4. One of them is 2, 3. Let's see, these are 1, 3. I can fill in for whatever that's worth. Let's see, Calzone says this is always a 4. Let's look at this. Okay, so if this is a 1, why couldn't this be 3, 2 if this is a 1? Oh, there's a negative constraint. Thank you, Afraid Not. I would never have seen that. I had already completely blanked out on that. So these two have a difference of 2. There's no diamond, so this cell can't be a 2. Good spot. Okay, so there's a 4, 2. And now that tells me that these two are a 1, 4. So that's a 3. Oops. That's a 1. This is a 2, 3 in some order. Okay, so yeah, this could be a 2 or a 4. I'm now afraid that I'm supposed to be thinking about the negative constraint. Ah, right, negativity in row 1. Thank you, Jay. Yeah, because I can't put the 4 next to the 3 because that would be a difference of 1. Okay, so that's a 2 and a 3. So this cell can't be a 1 or a 4, because if this was a 1 or a 4 by the negative constraint, there would need to be a diamond. So if this cell can't be a 1 or a 4, it can only actually be a 2. So that's going to fix all of that stuff. This is the other 1, 4. This is 1 or 3. Let's see. So this being 1 or 3... well, it means this can't be a 1, because if this is a 1, this would be a 4, and the difference would not be 2. So this is a 3, that's a 1, that's a 4, that's a 1, that's a 3, that's a 1, and that's a 4. People were finding lots of negative constraints that we did not need. But I appreciate the endeavor. But yeah, the negative constraint, the last negative... actually, it wasn't... I don't think it was even a negative. Oh, no, it was the negative constraint in column 4 was the one that I used that sort of sorted everything out. But there were many negative constraints as it would happen. But yeah, I was not appreciating how potent this negative constraint is. But this is a very cool... this is a very cool puzzle. I like this one. I really dislike negative constraint hunting puzzles. But this is so small... so small that it is cute. I liked this one. Okay, so we are now into the part called Dread. Okay, and we're doing another tiny numbered rooms. Okay. Each statement outside the grid correctly describes the digit in the nth cell where n is the digit. So normal numbered room rules, not normal numbered room clues. Got to zoom out a little bit so that you can see all of this. Let's make sure that... can't quite see all of that yet. Let's see. Can you see it all now? Looks like it. Yep. So the fact that neither of these is 1 means I can't put a 1 here or a 1 here, which means I have to put the 1 over here. Now, that means I have to place the 1 in one of these, but this is a not 1 clue, so that actually places the 1 in this box here. So that's going to put a 1 over down here. Now, this cell can't be a 4 because the 4 would index the 1. So this is a 2 or a 3. Sorry, so this is a 2 or a 3. Likewise, this cell can't index the 1. So it is a 3 or a 4. Let's see. This one can't index the 1. So it is a 2 or a 4. Let's see. So, what are we going to do with all of this then? Okay, I now have to appreciate the interactions here between these things that are across from each other. So now this cell can't be a 4, because if this were a 4, it would point at a 3 and break the not 3 clue. So this cell can't be a 4. So this cell is at the very least limited to 1, 2, and 3. Are there any of these others that it is limited to? No, 3 is fine, because 3 would put a 4 there. That's fine. Let's see. Garian says row 4, column 1 can't be 2 or 4. Why can't it be 2? I agree it can't be 4. Oh, if it's 2, it makes the other one work. Ah, that's very clever. Okay. So if this were 2 or 4, then either it's a 4 pointing at a 2, which breaks this not 2 clue, or it's a 2, in which case this becomes a 4 pointing at a 2, and so it breaks that one. So this is always a 1 or a 3, which gives us a 1, 2, 3 triple in the row. So that's a 4. So that's sweet. So now one of these two is a 4. It's 3 out of row 3, column 4. Yeah, so Afraid Not is pointing out, I'm not sure this is quite as potent, but Afraid Not is pointing out this cell can't be a 3, because if this cell was a 3, it would make that a 4. Wait. Sorry, let me double check this. If this were a... No, sorry, if this were a 4, sorry, this can't be a 4, because if this were a 4, then it would make that a 3, pointing at the 4. So that does not work. So this is a 1, 2, 3, which makes that the 4. Let's see. So this is a 2 or a 3. Let's see. So row 2, column 4 can't be 2. Right, if this were 2, it would make that a 3. So this isn't the 2. So the 2 has to go here. Nice spot likewise. So that's the 2. That's the 3. That's a 1. These aren't 3. In fact, actually, we know the order. That's 2. That's 1. So this is a 3 or a 4. Uh, Oh, yeah, we can place the 1. We should probably place the 1. That's a very smart thing to do. And so now once we place the 1, thank you, Jaleb, that places the 2, because now the 2 can't go here because it would point at the 1. So now that's a 2. So this is a 3-4 pair, and I know the order. That's a 3, that's a 4. It's a 4, that's a 3. That's a 2, and that's a 3. That was a cute little... very Clover-esque puzzle of sort of like creating this one little theme of these like, oh, if this is a buy value cell, you can't put this digit in this cell because of the way the rules worked, and sort of like repeating that theme throughout. So that is that was very cool. Tiny anti-Sudoku. Fill the grid with the digits 1 through 4 so that every cell contains a digit and all of the following are true. In each row, each column, and each 2x2 region, exactly one digit appears twice, and all other digits appear 0 or 1 times. And each digit from 1 through 4 appears twice in exactly one of the rows, exactly one of the columns, and exactly one of the 2x2 regions. Okay, so just to repeat, we need to repeat a digit in every row, column, and box, but only one digit in every row, column, and box. And every digit from 1 to 4 appears twice in exactly one of the rows, exactly one of the columns, and exactly one of the 2x2s. Whew, okay. Okay. So this digit I know is a 1, 2, or 3. This digit I know is a 1 or 4. Okay, let's see. So 2's already repeat in this column, so I can't have... can't be 4, because then I wouldn't be repeating something, afraid not, in the column. And I'm obligated to repeat something. Oh, and it can't be 2, because I've already repeated 2 in a column. So, yeah, by the rules, I can't repeat the 2. It can't be 4 because of that. Yep, so I need to either repeat the 1 or the 3 here. Okay, so one of these columns needs to repeat a 4 for what it's worth. Let's see. What can I do with the rows? Yeah, row 3 needs a repeat. I technically know these are not 2. So they are from 1, 3, 4. If this is not a 4, these two cells are the same, but I don't know that that does me a whole lot of good. Okay, so there is a box. There needs to be a box that repeats 1s. A box that repeats 2s is there. So we already have a box that repeats 2s, so I can at least fill in that these aren't going to be 2. They're going to be from 1, 3, 4. So that's something, I guess. Okay, I do need to have a box that repeats 1s, a box that repeats 3s, and a box that repeats 4s. Okay, let's see. Calzone is saying I do need a row with 2 2s, which is true. So it's either got to be that there's a 2 here, or... yeah, it can only be there. That's the only place I have not ruled out a 2 of, because I can't repeat 2 anywhere else. So the only row, this is a good spot, Calzone. The only row where I can repeat a 2 is this one. So this has to be a 2. Which now means this can't be a 1, so it has to be a 3. Which means this can't be a 1, to avoid repeating. We've got our 2 2s, so this can't be a 3. They cannot Memeristor, because you're specifically required to repeat all 4 in each set of houses. Okay, this can never be a 3-4 pair. Or a 4-4 pair, or a 1-1 pair. Sorry, I feel like that means this is restricted, because this can't be a 3-4 pair, because that would come up over here. So, could be 1-4. It can't be 1-3 either. Oh boy, okay, so there are 6 possibilities, and we might be able to rule all of them out. It's not 1-1. It's not 4-4. Could be 3-3. This pair could be 3-3, I think. No, it can't be 3-3 because I've already repeated 3-3 in the column. Okay, so this is 2 different digits. And because it's 2 different digits, it's not 1-3 because that would break the column. And it's not 3-4 because that would break the box. So it is 1-4. So this is the weirdest naked single pair kind of thing ever. This is a 1-4 is the only possible thing to do there. Okay. So we're now repeating 4 in a column. So I can't repeat 4 here. So this is a 3 and a 1. So this is a... Okay, so I'm repeating 3s here, 4s here. So here I need to repeat 1s or 2s. Well, I'm repeating 2s here. So this has to be a 1. Now this row is repeating a 1, so that's a 4. This row repeats 1s. Let's see. No, that's not quite going to do it. Let's see. Okay, we're almost there. Oh yeah, and column 2 already has a repeated digit, so that's a 1. There we go. Thank you, Afraid Not. 1-4. Only slightly broke my brain. I think I like this anti-Sudoku rule set less than the one where it contains everything but then additionally a repeat. This has a little too much give to it, I think, to work in a larger grid. Like, this worked in a 4x4, but I think a 9x9 version of this would be a nightmare for scanning and all of that. Okay. Next, we have an S-cell sweeper. So let's do the S-cell sweeper. So place the digits 0 through 4 in the grid so that each digit appears exactly once in every row, column, and 2x2 region. Each cell must contain at least 1 digit. Some cells will contain 2 digits. They're referred to as S cells. S standing for Schrodinger, if you have not had the pleasure of thinking about this before. Each circle contains a digit that gives the total number of S cells up to 8 in the surrounding cells, not including itself. A circle may or may not be an S cell. If a circle is an S cell, only one of its 2 digits needs to give the total number of surrounding S cells. And otherwise, the other digit can have any value that is otherwise valid. Okay. So This sees either 0 or 1 S cells, depending on how this counts. So this either contains a 0 or contains a 1. Hooray. This either contains a 0 or contains a 1. Let's see. How do we start this? Yeah, could contain both. That's fine. But yeah, this either is an S cell or isn't, which is going to... Oh, I guess the point is... No, because this one sees S cells out here as well. So I could put a cap on the number of S cells this sees. See, I thought that, Jay, I thought one was going to contain the 0 and one was going to contain the 1, except this one could see a whole bunch because it can see some over here too. So this one, so it's not even necessarily the case, I don't think, that one contains the 0 and one contains the 1. Oh, but between these two, one has to contain the 0 and one has to contain the 1, because this one is subject to the same restriction. Where it sees the whole box. So yeah, so one circle contains the 0 and one contains the 1. So these digits are from 2, 3, 4. Neither of them is an S cell. I'm going to indicate that by coloring them, not by making them 6, by coloring them green. So these are not S cells. Okay. And the 0 is the S cell. Yes, I agree. So yeah, these each contain a 0 or a 1, and the one that is the S cell is the 0. Okay. So if this were the 0, this would see at least 1. That's hard to immediately appreciate. Trying to figure out what the right way to think about this is. So the fact that these two see a different number of S cells tells us a little bit. But not a ton, owing to the fact that one of these could be an S cell, and in all likelihood one of them is an S cell. What's the most S cells something could ever see? I guess it's... No, it's... None of these can ever see 4 S cells. So the sweeper number is always 0, 1, 2, or 3, for what it's worth. But that doesn't mean they can't contain 4, because they could contain a 4 if the other number is right. Which is very unfortunate, as these things go. Now, I could put a bound on how many this sees. Because if I look, this sees all but one thing in the column, and all but one thing in the row. And it can't be that both of these are S cells. It could be that neither of these is an S cell. But regardless, this always sees at least 1 over here. So this sweeper number is always at least 1. And then if it's not an S cell itself, it's at least 2. Okay, I think Afraid Not has the correct observation, which is that these 3 numbers all have to be different. So in particular, this is going to be ugly, I think. This number needs to be different from this number. But unfortunately, I think that happens automatically if one of these is an S cell and the other isn't. I really wish these things saw themselves, because sweepers that see themselves let you do this sort of math a little easier where you look at the overlap. These are going to be a giant pain. So this one is counting these 3. And then this one is counting these 5. This one is counting these 5. Oh, here's a point. One of these has to be at least a 2, and the largest any of them can ever be is 2. So these have to contain 0, 1, and 2. And so this cell can't be 0, 1, or 2. It has to be 3 or 4. Because none of these can possibly see outside of these 2 boxes. So they can only possibly see up to 2 S cells. So one of these sees 0 S cells. One of them sees 1 S cell, and one of them sees 2 S cells. This one certainly doesn't see 0 S cells, because if it did, then the other one that had to see 2... Oh, wait, maybe it does. Sorry, maybe this one can be 0. Never mind. I'm not 100% certain about that claim. It sounds right, but I'm not sure. Okay, so I think JLib is trying to say that this cell can't be the 0, which was my instinct as well, and it was obvious to me for a second, and then I tried to explain it, and then I didn't believe it anymore. So if this is the 0, it's saying none of these are S cells. So then this could be the 1 seeing that, but then this would need to be the 2. Oh yeah, no, this could be the 1 seeing that one. This could be the 2 seeing that one and the 1 in this box. I think that works. I think this could be the 0. Oh, sorry. JLib says it can be the 0, and I agree. It can be the 0. Okay. Yes, there were multiple things for me to flip there. I misread the can as can't. Then I had to figure out the row and column were swapped. We got there. Yes, Afraid Not. I'm pretty sure JLib meant this cell, not this cell. Can this cell be the S cell? Is that obviously borked? Well, this would need to be the one that saw 2 then, so it could see this one and that one, say. These could be the 2 S cells. No, that's not going to work. Right. Whichever of these is a 0 needs to be an S cell, because all of these cells see their entire box. That's the point. So whichever of these is a 0 and one of them needs to be, whichever of them is a 0 needs to itself be an S cell, because otherwise it breaks. So that means that I can green this cell. Okay, so calzone says this can't be the 0. If this was the 0, it would be an S cell. I would need to have... right. If this were a 0, it would be an S cell. Would make that also an S cell, and then I'd have 2 S cells in the same place. So that's not true. So this is not the 0. So it's also not an S cell. Good catch, calzone. If this were an S cell, sorry, if this were the 0, it would be an S cell, and it would actually put another S cell in the same column, which is not going to work. So that lets us DS cell this cell. So this sees either 1 or 2 S cells, depending. Depending on whether that's an S cell or not. Right. Okay. So I actually can pencil mark this. I was being super careful about pencil marks, but afraid not is right. I can pencil mark this because now that this is not an S cell, I can unapologetically pencil mark it as a 1 or a 2 because I don't have to worry that it's also something else. Let's see. JLib says this cell now can't be an S cell. Right. It can't be an S cell because the S cell is in one of these 2 cells. Great catch. Like that. Yep, just by S cell sudoku, old friend. So can this still be the 0? If this is the 0... Okay, so if this wants to be the 0, then this has to be the 2. Which would put 1 there. And then this would be the 1. Okay, this can still be the 0. Can this still be the 0? If this is the 0... this would now have to be the 2. That would be 1. That would be an S cell. This would be 1. I think it works either way. I do not believe there is a negative constraint. I will double check. I do not see a negative constraint on circles. I do know one of these 2 is a 0, so I know this is a 1, 2, 3, or 4 for that that little bit of pencil mark value. I don't think... Someone was saying in chat that that one of these had to be... that we knew which of these was the 0, but in my head I went through both cases and it seemed like it worked out both ways, but if chat knows, I would be happy to know. Okay. This one, I know it sees 1 in this column. It sees either 0 or 1 in the box, and 0 or 1 over here, I suppose. Let's see. Okay, so... Right, okay, I'm figuring this out. Okay, so if this is a 0, then this is a 2, this is a 1, 0, 2, 1, and the S cells are here and here. but now this sees one S cell over here and no others, and so yes, this would be 1 and 1. Okay, that's really hard to see, but I agree with you. If this is the 0, then this needs to be the 2, seeing an S cell there and there. This becomes a 1. But now this is an S cell. How many S cells does it see? Well, it can't see this one. It can't see itself, but it sees 1 over there, so that is a 1 and a 1, right? So this can't be the 0, so this is the 1. And so that's the 1. That's the 0. That's the 2. And let's color. Oh, I should mark the 0 like that. That's the 2. Why not 0, 1, 2 in column 4? Oops. We just went over. This can't be a 0 because if this is a 0, this can't be a 2. 0, 1, 2 is not possible because if this is a 2, it says that it sees 2, but it can't possibly see 2 if this is a 0. So yeah, that's ruled out by counting. So yeah, this is not a 0. Okay. So that's not a 0. This is the one that is a 0. So this one is a 1. This one is a 2. Let's see, switch to color mode. Switch to color mode, try to. That's the S cell. That's not an S cell. And does contain a 0 for what it's worth. So now, wait. Yes, sorry. That's the one that's the S cell. Sorry, I don't know why I confused the bejesus out of myself there, but not for any particularly good reason. Yes. The 0 is, so those are the S cells. That's the point. And so this is not an S cell. Those aren't S cells. Okay. X, this is not a 1. This contains a 0. This contains a 2. So one of those 2 is an S cell. Okay. One of these 2 is an S cell. This sees at least one S. Actually, no, we know this sees 2 S cells. So this is a 2, just because it sees that S cell, and it's going to see whichever of these 2 is an S cell. So that's not a 2. Yeah, it's even better than that, afraid not. It just is a 2. So now by sudoku, that's a 2. And by sudoku, that's a 2. So we've got all of our 2s. So in particular, this needs not to be a 2. And the only way this avoids being a 2 is if it itself is an S cell. Because if this is not an S cell... No, other way around. The only way this avoids being a 2 is if these 2 are the S cells. Because if this were itself an S cell, these would be the S cells, and it would see 2. So these 2 are the S cells. So these are the S cells. These are the not S cells. So this is a 3. So this is a 0, 3. We can get rid of that. So this is a 4. By the row, that's a 1. That's a 4. This is a 0, 1. This is a 3, so that's a 4. So this is a 0, 3. So that's a 4. This is a 0, 1. Oops. No. Center. 0, 1. Oh, wow. And the answer check even worked. I was not expecting the answer check to work on that one. Nice. Yeah, it's really easy to end up with your S cell groups repeating. Yep, and 0 ended up in every S cell. No 0 got to be by itself. All the zeros ended up in S cells. Poor zeros. Okay. Next up, tiny meta sudoku. I hope this does not involve going back and counting things from our solutions to the previous puzzles. I'm pretty sure that... Oh, this was an F puzzles. Weird. Okay. I am hoping this doesn't involve going back through the previous puzzles, but I'm pretty sure it doesn't. I think Clover assured me of that. Okay, normal 4x4 Sudoku rules apply. Digits may repeat in a cage. The digits in a cage sum to the value in the top left corner, A or B, which are not necessarily different. Alice and Bob both hold incomplete information about the solution. Alice knows which digits go in cage A and how many times each appears, but she does not know the order in which they appear. With no other information, Alice believes that the number of possible solutions to the puzzle is A. Oh, God. Bob knows which digits go in cage B and how many times each appears, but does not know the order in which they appear. With no other information, Bob believes that the number of possible solutions to the puzzle is B. Find the correct solutions to the puzzle. Oh, Lord. Okay, and so the cages sum to the value, but of course they can repeat. Does this look okay in the... let's see. I can open this in F puzzles. Sorry, open it in CTC so that we can have a better view of what is going on. Okay. And then switch to CTC. I can't imagine that we're supposed to use the solution count. So I think JLib has the correct observation, which is that... and sorry, I should switch to... Sorry, let's switch to CTC mode. Why is CTC mode not... oh, it's because my window capture 2 is not capturing the right window? There we go. There we go. Okay, so now the rules actually show up. So, so the question to ask yourself is, does this cage contain 4 different digits? And if this cage contained 4 different digits, what would that mean? Well, that would mean that the number of solutions to the puzzle, as far as Alice was aware, because Alice would just know there was 1 of each digit, the number of possible solutions, as far as Alice was aware, would have to be divisible by 4 factorial. So that is, it would have to be divisible by 24, because if these are 4 distinct digits, and that's all Alice knows is that these are 4 distinct digits, then the number of solutions would be divisible by 24, and A can't possibly get to be divisible by 24. So that was really, really clever, JLib. So there needs to be a repeat digit in here, and so that means that this digit has to be the same as that digit. So those 2 digits are the same. Also, if it's 4 distinct digits, A is 10. That is perfectly fine as a way to do this. Now, we do know if you look at this, so let's go ahead and just make these. These are all different digits. Sorry, that was supposed to be a different color, not yellow. Oh, sorry, I can make this green instead of blue. I'm just really giving these things names. Okay, so now how many solutions are there to the puzzle based only on... based only on the fact that Alice knows. Okay, so yeah, Alice knows what digit appears twice. So Alice has to know that these two digit knows the exact value of these two and knows these up to a multiple of 2 because they could get swapped. Wait. I feel like A is 2 and A can't be 2, but oh, because there are other things. Okay, so we've got to figure out, okay, how many solutions does this puzzle have? And so we get to just do color Sudoku for a second. I don't really like red. Let's do gray. No. Orange. Orange is good. Okay, so now we get to do Sudoku. So that's orange, that's orange. Because we need to know how many ways there are to fill in the rest of the puzzle. Is the point. So let's see. Jay says 16. So we do know it's even. So we do know, because I could always switch yellow and green. Alice does not know the order of yellow and green. Notably, Alice knows exactly what purple is and where it goes. But yellow and green could be switched always. So A is even. And so these are both even or both odd, because of course purple plus purple is even. So these are either 1, 3 or 2, 4. But it can't be 16, right? 4 plus 4 plus 1 plus 3 is not high enough. So it's 16 is too high. So it cannot be that there are 16. There have to be fewer than that. As is being pointed out by chat. But this cage can't sum to 16. So something is being missed. The answer is probably 8. But I don't yet completely understand exactly what's happening. Two for row 1, 2 for row 2, and 2 for column 3. I'm confused as to how Josh's explanation does not seem to take into account not knowing what green and yellow are. Uh, 12? Is 12 possible? 4 and 4 and 1 and 3? No, the most this could possibly sum to is 8. 4, 4, 1, and 3. Sorry, no, sorry, 12 is possible. No, I can add. So 12 is possible. If these are 4, 4, 1, and 3. So yeah, the well, I mean, it is a well-known question. So we could well, no, you can't use answer check. Let's let's try Tristan's idea. Oops, sorry. I did not open that in the right tab. Okay, so let's do Tristan's solution. So that's 4, that's 4, that's 1, that's 2. Solution count. Oh. Solution count. At least 100 solutions. What? How can this puzzle have at least 100 solutions? I'm confused. I was expecting 6. Oh, it's because I didn't actually enter the digits. Thank you. Solution count 6. Okay. So I'm not 100% sure, but whoever said 12 is correct. The answer is 12. So we'll go with 4413. So that's a 2. So we know all of that. That's a 2. So these are a 1, 3 in some order. Oh, it could be 3, 3, 2, 4. You're right. So we know the sum is 12, but you're right. 3, 3, 2, 4 is also possible. So yeah, we don't know which of those is going on yet. Okay. So now I guess we're supposed to think about, okay, what is going on in Bob's world. So yeah, we can pencil mark that if we want. I don't know that it is useful to do so, but we can. So in Bob's world, Bob is looking at this cage now. Okay, so Bob knows these 3 digits are different. And so the only thing that Bob's question is this 4? Is the 4 also in the cage? Or is the 4 not also in the cage? And I guess those are going to give different answers. Oh, no, I guess there's 2 questions. Is the 4 in the cage and is the 3 in the cage? Just trying to think about this. So first of all, if the 3 is not in the cage, then the number of symmetries is already locked into being a multiple of 6. What's the maximum B can possibly be? Oh, that's right. There's always a 1 or 3 in the cage because the 1's going to end up there otherwise. Okay, so yeah, this is going to be a 1 or a 3. Let's try this both ways. So we'll make that the 1, and then we'll try putting the 4 here, and then we'll do the solution count. That has 2 solutions. And then we'll try putting the 4 there. That has 4 solutions. So, Lord. But Bob doesn't actually know. Yeah, 1 or 3 has to repeat. I agree. Although which repeats might change the answer. Let's see. So if I make this a 3 instead, and I do a solution count, that's 2. Oops, that's not what I wanted to do. And if I do that, that is 4. Okay, so it's always 2 or 4 times, and then we get to actually assign these digits values this is a mess. Hey, Logan. So Bob knows which digit this is. It's a 1 or a 3, but Bob knows which it is. No, because Bob just knows the contents. Okay. So Bob does know if every digit is in the cage or not. So those are really the two questions. Is every digit in the cage, or are only some digits in the cage? So if every digit's in the cage, then what are the possible totals? Well, then the possible totals are 11, 12, 13, 14. Okay. So if every digit's in the cage, there are not a lot of possible sums. Because if every digit's in the cage, the only possible sums are 11, 12, 13, and 14. And 11, 13, and 14 are all immediately discounted as being possible answers to this combinatorics question. So if every digit's in the cage, then the sum has to be 12. So if Bob knows... So if every digit appears in the cage, then what Bob knows is that Bob knows that every digit appears once, except that 2 appears twice. And so in that instance, we would end up with something like that, or 3. And so we would have our symmetries here would come from, we could not swap out the 3s. We would, but we could permute, as far as Bob is aware, the 1, 2, and 4. I think. But that would be okay. Yeah. So that would, and so if we went with not that one, but that one, that would be 12 solutions. So this is the arrangement. If every digit appears in the cage, this is the arrangement we're looking at. Is this exact sort of combination, I suppose. Wait, but no, Bob only knows the digits, so it would have to be the sum of those two. Oh boy, this hurts my head. Yes, I agree he knows how many times they appear in the box. Right, so yeah, these are swappable. So I think we end up with, if we knew that... so if what Bob knew was that the digits were 1, 2, 3, and 4, and a second 2... then I think the number of possibilities is in fact actually too big. It's more than 12. So if the combination is 1, 2, 3, 4, and another 2, then as far as Bob is aware, I could have this arrangement, and then fill in the rest of the grid however I want. Or I could have this arrangement and then fill in the rest of the grid however I want. So that is 6 right there. But also, there is no reason why the 4 and the 3 could not also swap, which then gives us... Oh boy. So let's think about this very carefully. Okay, so there are 3 factorial ways to arrange the 4, the 3, and the 2. I realize this is being made more confusing by the fact that the digit that's repeating is not the digit that I actually have repeating. So yeah, there's 3 factorial ways to arrange these digits, times 2 ways to maybe swap these 2 digits. That's 12, but then there's way more than that. Ways to then fill in the rest of the puzzle. So I think the point is, this is not possible. It is not possible that every digit appears in the cage. Because if every digit appears in the cage at least once, then the total is 12, and we have just now shown in a roundabout complicated way that there are way more than 12 solutions to the puzzle with the knowledge that Bob has. So, that means that we're not in the case where every digit appears in the cage. So that means that when we go to look at this, this digit that shows up here, whatever it is, it has to show up here in order for that to even begin to work. So then both of these digits need to be repeats. So this digit is a repeat of that one. And then this digit is a repeat of one of these 2, and then one of them is sort of a lone digit. So already, sort of if I make this yellow and I make these a pair of yellow and blue, then already there's a choice of what order I put yellow and blue in. That's a factor of 2. And then there's the choice of which of yellow and green is which. That's a factor of 2. So we're already a factor of 4. So Nicholas is right. The blue would go here. So we need a number that's divisible by 4. That's 2 green plus 2 yellow plus a blue. Let's see. Okay, so Tristan says that max is 16. 2 times 4 plus 2 times 3 plus 1. I get 15 as the max. Oh no, sorry. 4 plus 4 plus 3 plus 3 plus 2. It is 16. Okay, so 16 is the largest possible. Yeah, I think Clover maybe or maybe didn't intend people to use the solution count of F puzzles as a result of this this puzzle, which will be over soon. Hopefully, fingers crossed. So it's a multiple of 4, but chat has proven it is at least 12 and at most 16. So the number of possible solutions is either 12 or 16. So we can figure it out with the help of solution count here. Okay, so that's 4 solutions. 3 and 2. That's 2 solutions. So we have 6 total ways to get it, plus we can swap green and yellow. So yes, the answer is there are 12. So there are 12 ways to do this. And so how am I making a sum of 12? So 12 is... so 12 is the answer. We have just verified with FPuzzles. And so we know that these 2 digits are the same. And may or may not be yellow. So from Bob's adventure, we know that these 2 are both the same color. 4 plus 4 plus 1 plus 2? Or 1 plus 1 plus 3 plus 4? Okay, so these 2 are the same. So, no, I do know. Because gray sees orange, green, and purple. So gray is yellow. So those digits are yellow. So this digit is the digit that we... this digit's purple. Now, I believe we know purple does have to appear in this cage, so purple has to go there. Orange in this row needs to go here, so that's green. That's green. That's orange. That's green. That's yellow. Okay, so purple is 3 or 4. Orange is 1 or 2. So, remind me what A needed to sum to. I've completely forgotten. Does anyone remember? Did A need to sum to 12? I think A and B both need to sum to 12. I think is the point. So both sum to 12. Okay. So now the question is... No, B is done, Nicholas. So if we went 4, 4, 1, 3, then this would be a 2. These would be 4, 4, 2, 1, 1. That works. If these are 3, 3, then these are 2, 4. This is a 1. This is a 3, and a 1. And I need these 2 to add up to something, and it's not going to work because these 2 need to be... I guess the easy way to see it is this digit has to be even, because the total sum of this box is 12, and it's 2 times yellow, 2 times purple. So I guess the easy way to see it is that orange has to be even, so it has to be 2. And now once I know that this is a 2, I know that this is a 1, 3, and this is a 4 and a 4. So that's 4 and 4, and so now we just solve and see that 4 and 4 and 2 is 10, so these are 1 and 1, so that's a 1, that's a 3, that's a 1, that's a 3, that's a 3, that's a 3. Oofda. Yeah, completely unclear to me whether you're intended to use the solution counter, if you're intended to do the hard combinatorics problem. So anyway, let's go on to this crazy puzzle next. Was your hint not that orange was even because of parity? I assumed your hint was that orange had to be even because of parity, but I didn't actually look. All right, so let's open this monster. Because I think the parity was the slick way to do it, but there was probably another way as well. Let's see. Fill in the grid with the digits 1 through 6 so that the following statements are all true. Each of the 8 4x4 subsections of the grid is a valid 4x4 sudoku that uses exactly 4 distinct digits. Each of the 8 2x3 regions contains the digits 1 through 6 exactly once each. Wherever two 2x3 regions are orthogonally adjacent, they see each other and must follow Sudoku rules exactly as if they were two adjacent regions in a 6x6. Whenever two 2x3 regions are orthogonally adjacent... okay, so like this is what it's talking about. They see each other and must follow Sudoku rules exactly as if they were adjacent regions in a 6x6. And standard arrow and consecutive rules apply. Okay. Okay, so we have something in the spirit of the orb puzzles by DeMano. Penpacine. Okay, so every 4x4, oops. Every 4x4 is going to use some subset of the digits from 1 to 6. Okay. And then these we have to treat as being all part of a thing. What was the bit about 6x6s? Where was the... I don't even see a 6x6 in this. One moment, I need to reread the rules. Oh, no, it just says every 2x3 contains. Okay, so there is no, like, whole 6x6 Sudoku. We're just saying that this string of these two rows contain 1 through 6. Okay. So this digit can only be a 4, 5, or 6 because these sum to at least 3. That's at least a 1. So 4, 5, or 6 for the total there. 3, 4, 5, or 6 for that one. This one could even be a 2. Okay. Very nice point, Jalib. So Jalib's point, and it is a very good one, is that this cell and this cell have to be the same. And likewise, that cell and that cell have to be the same. And the reason why, and this is gorgeous, is that because of the 4x4 rules, these 4 digits are the same as these 4 digits. And so I can't have a green in any of these, so I can't have a green in any of these, so where is green going to go in this row? It has to go there. So that's cool. So green and blue are the digits that don't appear in this puzzle. So that is interesting. Yeah, I guess I was looking at it and I was thinking this didn't look super appealing, but I guess actually I can just go ahead and just sort of... Well, that's not a good color combination choice. I can just sort of throw these down and say, yes, those work like that. And so however that ends up working out, and then similarly for the other digits sort of down here. But these aren't connected to anything, which is why I was... Oh, it's something to do with the connectivity. Okay, I will finish coloring this now that it's pointed out what I'm going to get from it. So that's red, that's red, that's red, and that's red. Okay, black is a terrible color. Let's do 0. Okay, so that's orange, that's orange, that's orange, and that's orange. Okay, and so the point is, the reason why Jay liked this is that we go from yellow to red, from red to orange, and from orange to purple, which means that the digits in here are all consecutive with each other. And so these outer digits are something like they're either 1, 6 or 1, 2 or 5, 6. For whatever that is immediately worth. I don't think it's going to be immediately useful, but I think it's a key point that I was not sort of seeing that we were going to get out of this. But good spot by Jay that, yeah, these are 4 consecutive digits. Okay. I suppose up here, while I'm at coloring, I should probably color what happens to this digit. I'm going to reuse orange. My orange down here is not the same as my orange up here. But this digit goes here, and here, and here, I can at least say. So if I switch over to, let's say, blue... No, sorry, I can't use blue. I've used blue in this pile. If I switch over and use red, red goes there, red goes there. Maybe red doesn't get placed in this box immediately. Let's see, but if I now use, let's see. Sorry, I need to scroll because I've forgotten what my color options are. I'm using too many colors. Brown. If I make this brown, that's brown. Yeah, maybe I don't quite understand what's going on here yet. I was hoping that we were going to learn whether there were repeats on this arrow or not, but I don't think we've learned... Oh, we have learned... No, I don't think we've learned whether there are repeats on this arrow or not yet. Row 7, column 3, 4. Okay, so J40 is suggesting, and I think this makes sense, to look at these arrows together and figure out what's happening with these, because they have a bunch of different digits on them, presumably. So whatever the blue digit is, it can't appear on this arrow at all. And same for the green digit. So these 2 digits are 2 digits that are fairly, well, they can't be too big collectively, but they can't appear on this arrow at all. So, for example, if orange is 4, the only way that works is if this is 1, 2, 1. But if that's 1, 2, 1, then blue and green have to be at least 3, 4, and that's already broken. So this can't possibly be 4. So if this is 5, what are the possibilities? Well, this could be 2, 3, with this being... oh, I guess this could be 5. Never mind. Let's see. So, Garion and Calzone are pointing out that this green is both on the arrow, but also on the arrow circle. So, green has to be at least 2. Let's see. So, maybe also worth pointing out, I don't think it's been officially pointed out yet, there needs to be a 1 on this arrow, because if there's not, the minimum would be 7. So there has to be a 1 here. So all of these digits are at least 2. And the fact that these are each at least 2 means this digit's at least 5. So this is a 5 or a 6. This arrow doesn't have a 1 on it, so it needs to have a 2 on it. Because if it doesn't have a 2 on it, then its sum is too big because it can't have a 1. So it has a 2. Now, the 2 can't be green because if the 2 is green, then these digits would both have to be 1, and we know blue isn't 1. So therefore, blue is the one that is 2, as chat has been saying for a while, but that I have not sort of fully processed. Now, what can this be? This digit certainly can't be 2 or 1. So this digit can only possibly be 3 or 4. So this is a 3 or a 4. So this is a 1 or a 2. So now there are no 2's anywhere on this arrow, which means that the minimum is now 1, 3, 1. I guess that doesn't tell us anything. 1, 3, 1 or 1, 4, 1. Oh, it does tell us this cell has to be a 1, though. Because if this cell is not 1, then now suddenly the minimum is that this thing is 7. So it actually does tell us that cell's a 1. So that's something. So we do have a 1 here. We have a 1 in one of these two cells. So yeah, so all of these oranges are 5 or 6. I want to fill in. Yeah, one of these two is a 1. So yes, so by Sam's point, this value is a 5 or a 6. So I can't put a 5 or a 6 on this arrow. So Sam has identified that in this row, which by the rules must contain the digits 1 through 6, I have a 5, 6 hidden pair. So that's a 5 or a 6. So therefore, this is 1, 3, or 4. So we've got that. So the fact that the 3, 4 that appears on this is different than the 3, 4 that appears on this, and the fact that the none 3, 4 digits on this arrow sum to 2 tells us that this 5, 6 and this 5, 6 are actually different 5, 6's. So in fact, actually, if you want, and I kind of do, we can actually give this a color, make that purple. And so now I can place purple up there, purple over here, purple down here, and fill in that these are the other 5, 6. Oops, 5, 6. Like that. So now brown is not 1, so it's 3 or 4. Oh, can't purple be brown? Maybe purple can be brown. Sorry. Oh, sorry. I was right up until there, but purple could be brown, right? Purple could theoretically be brown. That's right. Okay. But that part was right. So that is purple. But yeah, we don't know where purple goes over there exactly. Purple is one of those two. But yeah, purple can be brown. Unfortunately. Maybe I should uncolor brown. That's probably a good idea. We can decolor brown. Yeah, there's a 3, 4. There's the other 3, 4 is in one of these two cells. So yeah, these are from 1, 3, 4. Let's see. Is there any problem if this is a 2? Sudoku logically? Then that's a 2, and that's a 2. That doesn't seem like a problem. Oh, Sam has it. Beautiful, beautiful Sam. Uh, this 4x4 doesn't have a 1 in it because this 1 here is telling us in the 4x4 that this cell isn't 1. And so then this grid doesn't have a 1, so this cell is a 2. Okay, so we can go ahead and blue that, which makes that and that each a 2. Good job to Sam there. Okay, and so now by our 6x6 trick that was pointed out by, I think, JLib earlier, this cell's also a 2. So that can also acquire bluity. So this grid doesn't have a 2 in it, for what it's worth. So now 2 plus 2 is, fancy fact, 4. So that's 4, that's 6, that's 6, that's 5. That's 5. That's not that. Sorry, I'm going to disable draw on edges. That's 5. That's 5. So now this is known to be a 1-3 pair. This is certainly the other 1 or 3. So I could give this a color, but I guess it doesn't really help to give it a color immediately. So this is a 1 or a 3. The top left part. Oh, this one. Okay, got it. Yeah, sorry. I was trying to place 6s in here, and that was confusing me, but you're right. I can definitely place the 6 here. This digit's a 6. Sorry, is a 6. This digit's a 6. We can go to colors and go ahead and 6 those. And that lets us place another 6. I'm going to decolor all of this. We're going to remember, I hope, that this grid contains 4 consecutive digits. But this 6 now gets placed down here. So that cell is purple by our previous work. Let's see. So yeah, so this 1-3 goes here, so this cell's a 1 or a 3. We'll go ahead and make this 1-3 yellow, which is, I think, 8. I got it right. So yeah, so that's yellow. I don't quite know how it goes in the rest of the world, but that's yellow. This is a 2-4 pair. Oh, 2 in this box. Why have I not placed 2 here? This is a 2. But this 4x4 has a 6 in it. We already know it has a 6 in it. There's a 1-3 over here somewhere. There are 2 2-4s, so I know that this cell's a 2 or a 4. And I know there's a 1 or 3, but I don't know which one it is. Yeah, this is whatever that digit is. And are we debating how we know what digits are in this 4x4? Because we started by knowing that 2, 4, and 6 were in it. So I have to put 2, 4, and 6 in everything. And then this one got placed because that yellow 1, 3 had to go in here and couldn't go anywhere other than there. So this is a 2, 4, 6, and a 1 or a 3. Red and orange go below the top left grid. Ah, okay, that's interesting. Okay, so yeah, so we know these 4 digits are these 4 digits. So yeah, so these are an orange-red pair. I agree with Sam, although there's no way to pencil mark that in Penpa. But these are an orange-red pair we can remember. See, we can put the 2, 4 in the bottom. Yeah, I know they're from 1, 3, 5. Okay, fine. I'll mark that they're from 1, 3, 5. Row 5, column 9. I have no idea how to count to row 5, column 9 in this. So I'm going to need a different description than row 5, column 9. Let's see. I mean, yeah, all the odds are in here, we know, because the 2 things missing from this 4x4 are even. One of them is a 6, and one of them is a 2 or a 4. So yeah, should we think about these Kropke? Because these Kropke are different. They both need to have the 1 even digit on them. So this is the even digit. I can go ahead and fill this in, that this digit's even, because I only get 1 even digit in this 4x4. And so it has to go there. Okay. Sam is making a good point, which is that it's not that these are 1, 3, 5. I think that's distracting. These are orange and red. So one of these is a 5. So there's got to be a 5 in one of these 2 cells, and 5 is only adjacent to 4. So in fact, this digit's definitely a 4. This digit's also a 4, and this is a 3, 5 pair. This being a 4 makes that a 2. That being a 2 makes that a 4 and that a 2. This is a 1, 3 of yellow. Okay, and so we can do a little bit of coloring to help hopefully make sense of this. Let's see. So, right. And so red has to be 3 because red shows up over here. Remember, orange and red. Oops. These are orange and red. So these are orange and red. And so this cell's the 1. So yellow is 1 and red is 3. Sort of percolating back through the grid. Going back up here. So let's do some coloring. So let's see. Yeah, there we go. That's yellow. That's yellow. That's going to be yellow. Once I fill in the digit. So now we can come over. Okay, so we can blue our 2s. And then let's see, 4s are apparently green. And yeah, this 4x4 is actually done, so I should actually do it. because now its digits are 1, 2, 4, and 6. So that's a 1 and that's a 4. So you can go back to 1 and 4. And presumably now this is also done, says Alima. Yes, so that's a 3. That's a 3. Let's see, what are the other digits? And that's a 6. That's a 6. That's a 6. That's a 1. Purple, 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 yellow, and 3 is red, which is 9? No. 7? There we go. Okay. Oh, this 3 missed its coloring day. Sorry, 3. Okay, so that tells us that this digit is a 3. Just because we now know what the remaining digit is in this box, so that's a 3. This digit's a 4, just working in this 2x2 business. So these are a 3 and a 5. That's a 3 or a 5. These are a 4 or a 5. Let's see. So those, no, these being 4 or 5 does not transpose. These are down here. So this is a 3 or a 5 for what it is worth. Let's see. Tristan says 2 is placed next to the 6 below the left 4x4. Yes, this becomes a 2 by our old friend. The point that was made, I think, by Jaleb, that these 2 digits get placed down here automatically. That has really been a very profitable observation to have had. So these are a 2 and a 6. Let's see. Yeah, so these are from 2, 3, 4, 5, which unfortunately leaves lots of options available for... Oh, wait, no, sorry. These aren't from 2, 3, 4, 5. These are from not 2. So in this puzzle, there is no 2, but there is a 1. So I know the 1 in this row goes in one of these 2, for what it's worth. Now, if this were a 5, this would become a 1-6 pair, but I don't think I know that. Oh, wait, I know the full contents of this thing. So these are 2, 3, 4, 5. So this pair I actually do know that this pair is 1-6. Which is great. I know that, by the way, because I know that these are a 2, 3, 4, 5 quad. But this can't be the 1 because this grid doesn't have a 2 in it. So that's a 6, that's a 1, that's a 5. So 5 is not excluded from this grid, so that makes that a 3. Makes that a 5, and that a 3. A 3, a 3. We try that again. So this digit, therefore, is a 4, because it's not a 2, 3, 1, 6, or 5. These digits are a 4, 5 pair. These are a 1-6 pair. Let's see what I can do with that. I can probably do a bunch more coloring. So, no. There we go. 3s are red. 4s are green. 5s are orange. No, 0? Yeah, there we go. Okay. 5s are orange. 1s are yellow. Got it eventually. Oh, 3s are red. I didn't do this 3 while I was doing the rest of them. And 6s are purple. Purple. There we go. Okay, so progress. Let's see. So I know these are a 2 and a 3. I might as well fill in. No 1 on the upper right dot in the bottom. Right. One of these is a 2 or a 3. Wait. No, sorry. The 2 and 3 are in here. So these are not 2 and 3 or 1. So these are from 4, 5, 6 is the point. Because the 2 and 3 are in here somewhere. So they're not over here. And so these can't be 1 either. So these are from 4, 5, 6. And definitely contain a 5. And now remember, this grid, the thing we know is that the digits in this are consecutive. So there is no 1 in this grid at all. The fact that there's no 1 in this grid at all actually forces there to be a 1 in each of these places. There's got to be a 1 over there and a 1 over there. Going all the way back to Jay Dyer's point from earlier. So those are 1s. So that means there is a 1... there is a 1 up here, because this grid now has 1s in it. But because of this grid, that 1 can't go there. So that's actually going to place a 1 there and a 1 there to finish the 1s in this grid. Go ahead and color those. That was very clever. I just love puzzles like this, by the way. This is one of my favorite strings. Okay. This 1 down here tells me there is a 1 in this grid, and so there needs to be a 1 in this box, and it can only go here, so that's a 1, and is yellow. One of these two is a 1, and it has to be this one. Same in bottom left. Not sure. Okay, so I know for sure that these digits... Oh, wow, I know this in 2 ways. These digits are definitely from... Well, I know these digits include a 1, and then the other digit I know is a 2 or a 6. Oh, actually, no, even better. These 2 digits need to go in this row. So they're from 1, 2, 3, but I can't put a 3 in here because remember the 4 digits that are in here are consecutive. So actually, this is a 1, 2 pair. So that's a 1, 2 pair. So that gives us our payoff, finally, for knowing that the 6 digits in this grid are consecutive, is that these now have to be a 1, 2. They have no choice. So that's a 3 and that's a 2. So let's see, does that do me any good? I know one of these two is a 3. Yeah, that does do me something. I know one of these two is a 3, so now where does 3 go? Actually, no, maybe I don't know. Maybe 3 could go in either of these. I was thinking 3 couldn't go here, but I think it can. Okay, so this goes here, goes here, and here. I'm sort of trying to rethink through what this coloring looked like and see if it did anything useful. Let's see. This crop key is restricted, so it's from 3, 4, 5, 6, because those are the digits that appear. This digit can't be a 5 because I know there's a 5 on here. So because there's a 5 here, there can't be a 5 in this cell exactly. Let's see, the bottom one is extreme. Yeah, we did have this all colored nicely earlier. 5 can't be in either cell. Look at the arrows. Let's see. If this were 5... if this were a 5, it would force that to be a 5, which would then make that a 5, which would clash. Okay. So yeah, so there's no 5 on this Kropke dot, which means that it must be a 3, 4. Because there's only 2 odds and 5 is not available. So this is a 3, 4. And so now that means this digit's not a 4 anymore. This digit's a 3 or a 4. This digit's a 5 or a 6. So this cell now is this 3, 4. So this is a 3 or a 4, and this is a 3 or a 4. This is a 5 or a 6, and this is a 5 or a 6. So now there's only 3 valid Kropke dots. This is the other one that's not one of these two. So it's not 3, 4, and it's not 5, 6, so it's got to be 4, 5. There's no choice. And so because of the fact that it can't be 5, 6 and can't be 3, 4, so this is 4, 5, which means this one isn't 4, 5, so this one is 5, 6, which then is going to unravel everything, because that being 5, 6 makes that a 4, that a 5, that a 6, that a 3, that a 3, that a 3, that a 6, that a 6, that a 5, that a 4, that a 6, that a 3, that a 4, that a 5, that a 4, not a 5. Okay, so we get all of that in that that grid just sort of falling apart all at once. So let's see, let's update our coloring. So our 3s are supposed to be red. So 3s are red. 4s are green. 2s are blue. 5s are orange. 6s are purple. And that will get us lots of stuff. Okay. This 1, 2, and this 6 are looking up here, so I super know what's going on here now. So this is not a 6, so it's a 2. This is not a 2, so it's a 6. My 2 digits here, my 4 digits in this grid are 1, 2, 5, 6. So that's a 1, that's a 5, that's a 5, so that's a 3, and that's a 5. Let's see, so... so now the 5 is placed here, so that's a 5, that's a 1, a 2, a 1, that's a 6, that's a 2, finishing up this little grid. This grid's numbers... No, I did it wrong. Uh-oh. Where did I double the 5s? Have I unwound enough? Have I not unwound enough? I'm looking for the double 5s. In the lower left. Column 4. Lower left. Yes. Okay. Yep. There we go. Okay. Better. All right. I eventually saw the thing. Okay. So that's a 6. This is a 1, actually. Now that we have that, that's a 2, that's a 1. It's a 5, that's a 2. So these 1, 2 see across and gives a 1 and a 2 over here. So this 1 and 2... Oh, I still have no idea what the mystery digit is over here, do I? Oh, I do. The mystery digit is a 4, because this grid doesn't have a 5 and a 6 in it, so it needs a 4. So all of these as of yet unnamed things are 4s. And yes, hello, Tall Cat. Nice to see you again. Hopefully you had a good trip. Are you back from your trip? Coming up to this one, that 4 comes up here. That's a 5 and a 4. The digits here are 1, 4, 5, 6. So this needs to be a 6. That needs to be a 5. And let's do some more coloring as a reward for all of that. So 4s are green. Green. 1s are yellow. Yellow, 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 yellow. 2s are blue. Let's see. 5s are orange. 4s are green. Let's see. 6s are purple, which is the hardest one to do. 5 for... No, sorry. 6 for 2. All right. This grid, actually, we can now sort of percolate up that... No. This 5 sees up that's a 4, and that's a 5. Let's see. We can place a 5 down here. So that's a 6. That 6 sees that that's a 1, and that's a 6. So that's a 4. That's a 1. So this grid, we can place a 3 down here. So that's a 4. That's a 1, and that's a 2. So let's go finish our coloring. So 1s are yellow. 2s are blue. Blue. Try again. 3s are red. 4s are green. 5s are orange. And 6s are purple. Okay. So, moving in on the area over here. So this grid has 1, 5, 4, and 3. I don't know why I didn't color these. Probably should do the coloring just so that we don't make a mistake. So this is red. So this is going to be red. So this is orange. This is going to be green. Green at the end of the day. So green is going to get placed here. So red is going to get placed here. So red's going to get placed here. So orange is going to get placed here and here. So the coloring is done, and we just have to figure out the digits. So we'll get a 4 and a 4, and a 3 and a 3 and a 3, and a 5 and a 5. And we got a congratulations! Woohoo! Yeah, that one was really fun. I enjoyed that one a lot. I'm going to take a real quick break before the next puzzle, but stay tuned. We have more craziness from Clover coming up. I think we have just one more 9-grid disjoint craziness puzzle, so you can look forward to the 9-grid puzzle coming up, but we will be right back. Thank you for joining us, and thank you to all of our patrons who support us. Alrighty, welcome back, everyone. Zetamath feature on CTC. Well, that'll be fun. Is it distinction? So if it's distinction, that's a cool puzzle. I liked that one a lot. Let's see. All right. I may figure out a way for us to watch the zetamath puzzles on CTC together. But before I do that, I want to finish up this this Clover pack. So we've got one more of these. That was fast. I just sent that in like 2 days ago. But I will figure out. This might take a moment, but I'll figure out a way to do a live watch of the Simon Solve. How long is the Simon Solve of it? I'm curious. Let's see. Woohoo! I'm excited. I really liked that puzzle. I'm very happy that it got picked up. 49 minutes. Okay. Alrighty. So, oh, if I opened it twice? No. Okay. So let's figure out the rules to this puzzle first, and then we'll figure out how to maybe possibly watch. I guess I can just like pull up YouTube and watch it here, probably. I might need to pull in desktop audio or something. I'll figure it out. Okay. So let's fill each grid with a set of 4 digits from 1 to 9. So kind of like the previous puzzle, each 4x4 has its own set of digits. In normal 4x4 Sudoku fashion, the correct set of digits to use in each 4x4 grid must be determined. no digit ever appears in the same position in two different grids. So that means that this is sort of like a weird disjoint puzzle where for every position, if I look at all 9 grids, that position will have all 9 values in some order. Yeah, it does occur to me, maybe YouTube will help you stream YouTube videos to YouTube. It seems like the kind of thing that YouTube might actually help you do. Let's see. Okay, digits appearing outside of the 4x4 grids are non-negative integers, but are not necessarily in their... Wait, digits appearing outside? Oh, so are we actually putting a digit here? Is that what this is saying? Sorry, let me read this again. Disappearing outside the 4x4 grids are non-negative integers, but not necessarily in the range 1 through 9. Standard arrow, killer, inequality, thermo, rules apply. Okay, so I do need to put a non-negative integer here and here. That's weird. Okay. And on the thermo, okay. This is very weird. Okay. So, the final boss of Bitty Bytes 2, here it is. So, let's see. So this thermo, so my understanding is I have to put a digit here. So let's count this thermo and then goodlift it. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So 1 or 2, 2 or 3, 3 or 4, 4 or 5, 5 or 6, 6 or 7. Oops. 7 or 8, 8 or 9. Draw on edges off. We literally just talked about this puzzle last night, Tallcat. How could you not have been aware of it? Let's see. This is a sum of at least... yeah, this is a sum of a bunch of numbers. This is some bunch of numbers. Let's see. So all of the numbers... Okay, so maybe here's a point. Oh, this number's at most 7. Because these are the 4 digits that appear in this puzzle. So because these are the 4 digits that appear in this puzzle, this can't possibly be bigger than 7. And that's got to be pretty big, because the absolute minimum that this could ever be is 7. Because this could be 1, 2, this could be 1, 2, and this could be 1. That has to be what happens. So this is 7. That's a 1. And then these are all 1, 2. So now that makes that a 6, a 5, a 4, a 3, a 2, and a 1, just percolating backwards down the thermo. Can't it be a 0 outside the grid? Oh, are non-negative integers. Sorry, you're right. Okay, so right, it could be a 0. So this is a 0 or a 1. Right, so there is a degree of freedom. Sorry about that. So that means that I don't know that this is a 7 yet. This is a 6 or a 7. Okay, so this is a 0 or a 1, and then these are all from 1, 2, 3. Oops. No, please unselect that. 1, 2, 3. Okay. Good point. Sorry, I missed the non-negative trick. But that does, as pointed out, give us a 6-7 pair in this row. So that means we know that 6 and 7... Oh, it's even better. So 6 and 7 are numbers in this puzzle. So that means this has to be a 6. Because I need to... Wait, does it? Maybe it doesn't. No, yeah. Sorry, this has to be a 5. Because this digit... No. Don't listen to me. I'm being confused. Yeah, if this is a 7, it doesn't work. Because if this is a 7, I put a 6 on the thermo, and now I don't actually have 7 as one of my digits. So this can't actually be a 6. This can only be... Sorry, this can't be a 7. It can only be a 6. And that be a 7. So that does eat our degree of freedom. This is a 0, and these are all 1, 2 pairs. Okay. So now we can go ahead and place the 6 and the 7 here per Afraid Not's point. That's going to place a 7 up there. So now we know there needs to be a 6 on the thermo, so the 6 on the thermo has to go there. The remaining 6 has to go there. This has to be a 3 or a 4. This is a 4 or a 5. And the fact that this is a 4 or 5 is very interesting. Because that's already a pretty big digit to be appearing on an arrow. Let's see. So, yeah, and so probably want to go ahead and give this a color, this 4, 5, because I know where it goes here, and so I know where it goes here. And then we can give this a color. No, I wanted that one. That one, that one, that one. Like that. Oh, which means that this is a 7. How did I not fill in that this was a 7? I don't know how I failed to fill in that that was a 7. But anyway, that's been a 7 for some amount of time. These are 3, 4. These are 4, 5. Okay. So that is all well and good. So 1 and 2 are the values along this diagonal. So I'm interested with what's going to happen between this diagonal and this diagonal. Yeah, we can finish the thermo. Because those diagonals all overlap, and they all want to have low digits on them. So the absolute minimum, this could be 4 plus 0, plus 1, 2, plus 1, plus 1, 2, plus 1. So the absolute minimum this works out to be is an 8. So this is either an 8 or a 9. Now, this is a 0 or a 1. And so these are from 1, 2, 3. This is a 1 or a 2 because there's a degree of freedom. But I want to pay attention in particular to the fact that that gives us a 1, 2 pair in this position. So this digit is actually at least 3 now, for whatever that's worth. Probably not worth a whole lot, but it's worth keeping track of that kind of thing. Hey, Alex, welcome. This arrow, this thing can't be a 9 anymore. For whatever that's worth. These are at least... Okay, these don't overlap with anything, so that's at least 3, 4. Yeah, Peter, thank you. I'm looking forward to watching it and trying to do a live reaction video and seeing if we can figure out how to make that work. It will be its own little adventure, I am sure. So I'm still trying to just hunt down a tiny bit all these overlapping sort of 1, 2s. So if this isn't a 3, then we're saying these two cells are each at least 3. But that's not a huge deal. Is there any possible way that this could be a 5? I don't think so. I'm trying to figure out, like, this 1, 2 is one of those 1, 2s. I'm trying to figure out if I can sort of, like, chase it around. There has to be a 1 on the grid 3 arrow. If not, yeah. If not, then I break my 1 degree of freedom. So yeah, 1 is one of the digits that has appeared on here. That is a good point to J40. So actually, If I use a 3, then the digits in this grid are forced to be exactly 1, 2, 3. Let's see. So the 14 cage. What can the 14 cage be? There, it could be 9 is the bigger digit, 5 is the smaller digit, 8 is the bigger digit, 6 is the smaller digit. I think those are the combinations to make 14. Unless 7 is the bigger digit and 7 is the smaller digit, but I can't do that because I already have a 7 there. So those are my combinations up here. For the 13 cage, there's more options. So this could go as far as 9, 8, 7. So this would be 4, 5, 6. Sadly, we're not yet at a point where any of these are overlapping anything. Let's see, the 12. This needs to be 7, 8, 9. This can be 3, 4, 5. Don't quite have... So I'm beginning to think I might be trying to form a 7, 8, 9 triple in lower left box. Row 4, column 1. Why could this not be a 7? Or what's... This is a 6. 6 is the only digit we've ruled out of this. The 6 in box 5, looking at the 14 gauge. I don't think that these things look up here because the thing is that you can't repeat a digit in the same cell. I will reread the rules just to make super sure. It's in the same position in 2 different grids. So I can't repeat a digit in the same position in 2 different grids, but I don't see I don't see how that affects this. Yeah, this 7's on sort of the other side of this one. Yeah, so let's see. So someone was saying this is from 7, 8, 9. Let's see if we can make that true. Because if this is from 7, 8, 9, that's actually big because it gets us a 7, 8, 9 triple. So it can't be 6. So the only thing we have to rule out is why can this not be 5? And if we know why this can't be 5, then I'll be content. And it probably has to do with looking at these overlapping diagonals together. So that cell's a 1 or a 2 there. It's a 1 or a 2 here. So it has to be at least 3 here. Let's see. Because row 2, column 3 is at least 3. I agree, that's at least 3. And row 3, column 2 is at least 2. Okay, why is this one at least 2? If this were a 1, it would make that a 2 and that a 3. Okay. No, we don't actually... Are we guaranteed there's a 1 used in this box? That's the point. We're guaranteed, actually. I had not actually previously proven this, but it's true. Because we only have 1 degree of freedom, one of these two has to be a 1. I can't possibly get away with making this a 2 and a 3. That's already too big. So yeah, there is a 1, actually. I can just get rid of this corner mark here and actually think about it. Yeah, so there is a 1 here. I had not proven this before, but there's a 1 in one of those two and a 1 in one of these two, so this can't be a 1. So this is at least 2, this is at least 3, this is at least 1, so this is at least 6, but it can't be 6 because there's already a 6, so this is 7, 8, 9. And so that means, for whatever it's worth, all of these remaining cells are from 1, 2, 3, 4, 5. Probably not worth a whole lot, but it's true. Okay. Oh, and not 1, because we actually know there's a 1 there. So yeah, actually, from 2, 3, 4, 5. Top left grid, row 4, column 4. Sorry, row 4, column 4 repeats in row 1, column 3. Right, because this cell can't be a 1 or a 2. Ah, that's really clever. Okay. Let's give that a color now. You can be yellow. No, yellow. You go there. So yeah, this cell's a 1 or a 2, because this cell can't be a 1 or a 2. That's gorgeous. Okay, that's really, that's very slick spotting, Alima. Okay, so that's a 1 or a 2. Hey, SPQ, how are you doing? I'm looking at 4, 5, 6s in these cells just briefly. Like if this is a 5, then that's a 6. Doesn't really seem to do anything, but it seemed worth looking at for a second. Ah, yeah, okay, good point to Christoph. The arrow tip actually has to show up in this box somewhere, and the only place it can show up in the box is there. So these two are actually the same digit, which means that's that digit and that's that digit. No, sorry, and that's that digit. So these are 7, 8, 9. Let's see. Would sure be nice if we knew that this was yellow 1, 2. Let's see. What if this digit is at least 3 and this digit is at least 3? This could be 3, 3. Then this would have to be 1 or 2, but that seems okay. But that was a really good spot, Christoph. Do I know that yellow 1, 2 goes here? I would love to know that yellow 1, 2 goes there. But I don't think I do. Color row 2, column 3. Ah, okay. So, yes, my beloved bringer of tea. Okay, so that digit certainly goes there. That digit certainly goes there, so it goes there. Yeah, I don't think that answers the question of whether this cell is yellow or not. What do I know about the value of purple? I know purple is at least 3. What's the most purple can be? Maybe that's not an interesting question, because maybe I could have... this could be like 5 with this being double 2 or something. It puts a lot of pressure on the other arrows if it happens that these are not that. And welcome, Ken. Let's see. None of these cells show up anywhere, I don't think. So I think I only know that this is at least 4, which is not a huge restriction. If blue is 3... Let's see, I'm looking at Garian's point. If blue is 3, then you can't make purple 3 in the top left box. Agree, yep. So this is... there is this connection. And notably, if blue is 3, yellow is 1. But the blue doesn't immediately seem to show up other places that I can see. Let's see, and there's no place where red touches the same place that a 7 touches, right? In any of these other puzzles? No, I don't think so. Oh, but no, sorry. Purple can't be 9. That is not exciting. I was briefly excited by the fact that purple was not 9, but that is not a good deduction. I mean, it's true, but it's not an interesting deduction. I'm very open to using the fact that each digit has to show up in exactly one grid. I just don't know how to use it. I feel like that's going to be very useful once the puzzle is getting closer to finished. Because once that happens, then we'll be able to say, like, we don't have this digit showing up somewhere yet. And then it will sort of start pulling things apart. See, I know this digit's at least 3 because this digit's in the 12 cage. So this digit's at least 3, plus these are at least 3. So actually this digit here is a 7, 8, 9 as well. Because if I look... Sorry, it could be a 6. No, it can't be a 6. So here we go. So I think this is useful. This digit appears in the 12 cage. So it is at least 3. These are at least 1, 2. So that means this circle is at least 6. But it can't be 6. Sorry, it can't be 6 because it's in a 12 cage, and it can't be 9 because there's a 9 in that spot. So actually, this is a 7 or an 8, and this is a 4 or a 5. So that seems interesting, possibly. Let's see. So the 7, 8, 9. Yeah, this cell. Good point. We can do more coloring. Christos sees this cell. Let's make it green. This cell can't appear on the arrow because this arrow is at most 7 or 8. So it has to show up somewhere here. So this can be 7, 8, or 9. Now, actually, this cell can't be bigger than 5. So actually, this cell is at most 5. So in fact, these two cells are the same. Okay, sorry. I need to figure out what brown is to make a color because I'm running out of colors that I know by heart. Surface brown. Brown is 12. Okay, these two are the same digit as well. So that is interesting. And so actually we could do more coloring, like these two cells are the same. Yeah, we can actually finish green, because where does green go in row 4? I did not see this, but Afraid Not pointed it out. That has to be green, and that has to be green. So that's 7, 8, 9. That's 7, 8, 9. So that is where the green goes. I guess this 3, 4, 5 could show up on the arrow here as long as it's with a 1. I don't think I know anything about 1s in this spot, so I think there could pretty freely be a 1 here. I do just adore this puzzle, by the way. This is super sweet. Let's see. 7, 8, 9 for the upper right corner. Let's see. There's no other... there's a... So we have a 3, 4, 5 in 2 places. Or in 2 of these places. That's interesting. What about this cell? Yeah, brown and orange are sort of interesting. There does need to be a 1 or a 2 in here. I can't get by without a 1 or a 2. But I don't think I need a 1 or anything crazy like that. Sadly, this 4-5 does not see any of these other 4-5 businesses, I do not think. This can only be a 5 if this is a 1-2 pair, for the record. These 7, 8, 9s are now actually lining up. Sadly, not immediately clear how those are going to resolve, I don't think. I'm interested in like what the overlap is between the 13 cage and the 14 cage and the 12 cage and the 11 cage. But I don't think I quite know enough to say. But I think that is an interesting question going forward to ask. Yeah, purple is at least 3, we know. The purple is marked, Nicholas, because of that observation. That this is a 1-2 pair, which makes this digit at least 3. I'm now briefly having terrifying visions of setting this puzzle and how horrible it must have been to try and get this to work out in this way. purple may do something interesting with blue. So what can purple actually be? We know purple is at least 3. Pretty clearly, purple is not larger than 7, but I suspect 7 is way overshooting it. So could only be 7 if both of these cells were 1. Is there any way both of those cells could be 1? Unfortunately, I don't see how I'm ruling out that both of those cells are 1. It would make yellow 2, of course. Box 3 and 7. Oh, that's right. This one can't be 1. This cell is at least 2. So, right, this is at least 2. So this can't be a 7. Oops. Because, oops, whatever I did there is not what I wanted. Not 7. Because we have a virtual 1-2 pair in this diagonal. So this can't be a 1. It could be a 2. So is 6 possible? That would require a 2 and a 1? Maybe? That sounds fishy as well. If this was a 1-2 pair and that was a 1-2 pair. That seems very sus, but we certainly need a 1 or a 2 on this arrow. We cannot get away without a 1 or a 2 on the arrow, but unfortunately I don't know what that tells us. Bottom right corner. It's not yellow. Why isn't this yellow? I'm trying to decide if there's any way I can connect which is yellow to this box or this box so that I could actually have yellow cross puzzle boxes. Because I think if I can get yellow across puzzle boxes, that might actually be useful. So here's an idea. Let's color this 1-2 pair. So I'm going to use some colors for this. Okay, so this is going to be pink. So this can be some non-pink color, like dark gray, I suppose. And so this is dark gray. Now, the question is, do I have any idea how that connects over down here? And I again fear that I don't actually know anything. That's a really good idea, Judith. If I were setting this, I might be inclined to do something like that, where like everything here is just a permutation mod 9, so that you're guaranteed that this works out. In box 1, if row 3 column 2 is more than 2, it must appear on the arrow twice. If this is more than 2, yeah, then it's not purple. So if this is more than 2, it then shows up there as well. So this can't be more than 2. because then that would make the total too big. So this cell is always a 1 or a 2. Which is great, because that gives us our 1-2 pair, which makes this cell a 3 and resolves the world. So great spot to calzone. So let's re-go over this just to make sure we believe it. So now the absolute minimum I could put here would be 1, 3, 1, would be 5, 0, 4, and that is the best. Okay, so yeah, so this is 1, 1, 4, 0, 9. Okay, so I think we can get rid of the coloring of these now, because now they're just going to be digits. Oops. So now, yeah, now we're going to resolve the world. So now that 1 makes that a 2 and that a 1. That 1 makes that a 2 and that a 1. That 1 makes that a 2. Orange is 4 now, so the fact that orange is 4 fixes the thermo back like this. So in fact, this is a 1-2 pair going on in this puzzle. So that's a 2, that's a 2, that's a 1, that's a 1, that's a 2. So this is 2 and 2. So this certainly can't be 6 anymore. Let's see. Now, what else is that? Oh, so blue is 3. I should fill in that blue is 3. 3, 3. Blue being 3 means purple's not 3. So purple is at least 4. Purple being at least 4 now means this isn't 7. It's at least 8. So that is an 8 or a 9. So one of these two is a 7, for whatever that is worth. This isn't a 2 anymore. That's not a 2 anymore. That's not a 2 anymore because of disjoint nonsense. Let's see. Do any of these cages overlap anything in an interesting way? I don't think so. Brown can't be 4, I see from chat. That's true. Brown can't be 4, so green's not 8. Agree as well. Let's see. We can uncolor the 1s, because the 1s are just 1s. These aren't 7 either. Okay, so does this 1, 2 put pressure anywhere else? So this cell can't be a 1. It's at least 2. But this cell, I think, could still be 1. Oh, there's disjoint Sudoku to do in box 1? I mean, there's just regular Sudoku I can do in box 1, I suppose. So I can place a 2 here, and a 2 here, place a 1 there, and a 1 there. And now, let's see, is that helpful? If so, where? Yeah, okay, so we can continue up here. There's a 1 by Sudoku. There's a 1 by Sudoku. Okay. Neither of these, I think, sees any of the 1s, unfortunately. So I could color this entire box. I don't know if it's worth it. 3s and disjoint. Okay, so the 3 is placed by disjoint, Martin points out, is correct. 3 can't go here because it would mirror that 3. So in fact, that's a 3, which makes that a 3, which makes that a 3. Great spot. So now that's a 9, because I need a 9 in this row. So that's a 9 because I need one for this box. That's a 9 because I need one for that box. Do any of those 9s see any cells that I ever wanted to be 9? I fearant that they don't. Yeah, I do not see any. Let's see. Do any of them see this? Somehow I missed all of these. Yep, we exactly missed all of these. But that's okay, I suppose. Now, do any of those 3s see this 3, 5? They do not. I do not believe. So if brown is 3, the only place in row 1 that's allowed to have a 3 that brown could go is there. So that would be a 3 and that would be a 3. So if brown is 3, the 3s end up looking like that. Does that break anything? Not that I see, unfortunately. Let's see. Box 4. Does box 4 need 1s? Let's see. Do we know that oh, yes, I do know this isn't double 2. So, yes. So if there were no 1s, these would sum to at least 5 plus 3? I'm trying to convince myself I know that there is a 1 in box 4. So if there's not, then I would need this to be 2 and 3. The 3 couldn't go there. It could go there. Oh, but then if this is 3, this is 5, and so then it's way too big. Okay, yes, I agree. Because if I want to minimize this as at 2, 3, then this can't be 3. That's the point. And the 3 can't go here by disjoint sudoku. So it's pretty complicated to put all the pieces together. But anyway, this definitely has a 1 on it, and the 1 has to go here. By disjoint, it cannot go there. So that's a 1. So now I need to put a 1 in this row. It can't go here by disjoint, so the 1 goes there. So the 1 goes there. So the 1 goes there. That was awesome. Let's see. Yes, arrow digits can absolutely repeat, but they could not repeat if I literally put this looking at a clone of it. That was the point, Nicholas. But yeah, arrow digits can repeat in normal situations. Okay, have I now placed 1s in strategic positions that are going to make this arrow interesting? 2, 3, 4. Oh, well, 1s are just done overall. There are no more 1s in the entire universe because I've now placed 1s in 4 grids. So no grids have 1s anymore. So this arrow now needs to actually sum to at least 5. So this is 5, 6, 7, 8, 9 naively, but it's not 7 because there's a 7 in that spot down there. At the very least, that might be the best I can do, is that it's not 7 for this particular moment in time. Grid 4 arrow can't be a 7. Let's see. So these two are odd. So in order to make this a 7, this would have to be an even. No. This would have to be odd. So So why can't it be 3, 1, 3? It can't be 3, 1, 3 because this cell is not allowed to be a 3. So this cell would have to be at least a 5 in order to make this a 7. That's not ever going to happen. So that's an 8 and that's a 4. That was a great spot I think it was a Lima. Yeah, that was a really slick spot to see that this couldn't be a 7 because that was not an easy thing to see, I don't think. Hey, Carl, welcome. So So I might use neither of 8 and 4 in this 11 cage. I'm trying to think how the 8 and 4 is going to inform the 11 cage. Okay, so now this is summing to 8. 8 is even. The sum of these two is even, so this digit has to be even. So this is either a 2 or a 4, based on whether this is a 3 or a 5. I don't yet think I know anything about this from sudoku, or sorry, from disjoint stuff, but I know that's a 2 or a 4, that's a 2 or a 4, and that's a 2 or a 4. Aha! But now, if I chase this cell around the grid, it ends up here, and that tells me it's not a 2, because there's a 2 there already. So it's a 4. That's slick. That's awesome. Way to go, Clover, on this puzzle, by the way. This puzzle is insane. So that being a 4 makes brown 3. So now that's a 3, that's a 3, that's a 9, a 9, a 9, and a 9. I can get rid of the coloring on all of that. That 9 makes this an 8 by disjoint. That makes purple 4. I can again get rid of that color. So that makes this not 8, which makes this not 5. This is 7 and 9, 7 and 9, 4 or 6. Scanning just to see if there's any more disjoint nonsensicalness. Also not 9. Yes, good. Not 9 because of that 9. Thank you. Thank you to many in chat who saw that. This has gotten a Q in it, but we won't think about that too hard. So this is 7 and 6. So this is not a 6 either. Now, has it become impossible that this is a 5? Yes, this can't be 5 anymore because this would have to be 2, 3 exactly. Remember, 1s are gone. But actually, 3s are gone in both of these places. So this can no longer sum to 5. This arrow sums to 8 or 9. So that is very large as these things go. Let's see. I don't think I know which of 8 and 9 that it sums to yet, however. I know that these are 7 and 6. I don't know if it's worth recording. Oh, it is worth recording. These are 6 and 7, but I actually know the order because there's already a 6 in this spot. So that's a 7 and a 6. And that's huge because that 6 tells me that that's a 5, and therefore that's a 9, which tells me that that's a 9, and therefore that's a 5. 5, 6, that's a 7, that's a 6. So now I can fill in the rest of these. So these are 6, 7, 5, and 9, 6, 7, 5, and 9, 5, 9, 6, and 7. That 6 looks up there and sees that 6, so that's a 7 and a 6. Let's see. This 9 looks and sees that 5, 9, so that's a 5 and a 5 and a 9 and a 9. So that is going to do tons of work. So we've finished 4 grids now. So that's all good. Okay, so this is a 9. Let's look at these cells and figure out how we're making 9. Someone in chat said there's no 4 on it, so it's not 4, 5, and I agree, it's not 4, 5. There's no 3 on it, so it's not 3, 6. 3 and 3. It's not 3, 6. There's no 1 on it, and so it has to be 2, 7. So this is 2 and 7. Do I know the order of the 2 and the 7? It appears maybe I do not know the order of the 2 and the 7, but this is a 2 and a 7. So that's cool. 3, 4, 5, 3, 4, 5, 3, 4, 5. I assume we're just going to get the last digit in this grid by sudoku at some later date. The 11 cage can't be 2, 9. Ah, right. It can't. That's really clever. Okay. Yes, the 11 cage can't be 2 or 9 because this can neither be 2 nor 9. Good spot. I was trying to look for neither of them can be 2 or neither of them can be 9, but that doesn't work. But the top left does tell us this is not 2, 9. So if this is not 2, 9, could it possibly be 3, 8? Let's see. It looks like it could be 3, 8 if it's in that order. And then the only other option is 5, 6. No, sorry, 4, 7 is also possible, maybe. Yeah, 4, 7, but it would have to go in that order. And 5, 6, it would have to go in that order. I believe. Are any of these numbers seeing something by disjoint? Oh, I'm told we already have 4 grids with 4s. So that must mean there is a 4 in this spot somewhere. Oh. So, no, there's not. But we have 1, 2... So that's actually an excellent spot. We have 4 grids with 4s. So we can't put any more 4s. But actually, that also tells us we can place all the 4s here. So... the 4s in this, the 4 in this row can actually only now go here by disjoint. The 4 in this row can only go, which of these is it? The 4 in this row can only go there by disjoint. So now that's a 4. These aren't 4. Excellent spot to whoever said we already have 4 grids with 4s. That was Brian. That was a very good spot. So now this 11 cage can't have a 4 in it. So it can't have a 7 in it either. Let's see. Could it be 2, 9? It cannot be 2, 9 because there's a 2, 9 over here already. So not 2, 9. So could it be 3, 8? Let's see. No, because there's a 3 in both spots. So it has to be 5, 6, I think, if I did that right. And we know the order. 6 and 5. So if we believe that, then that's an 8, that's an 8, that's an 8. Let's see. What am I missing? I am missing a 6 in this column. I am missing a 5 in this column. And then these digits are a 5, 6 in some order. And I know which order because of that combination. That's an 8, not a 5. That's a 5. That's a 5. That's a 6. That's a 6. That's a 6. Okay. So there we go. Okay. So, yet more fun stuff here. Okay, so now Martin is suggesting we go back to box 6. So back to box 6. We put a 6 here, so now this can't be a 6 anymore. So that is an 8 and a 3. This puzzle is so much fun. So these I know are 2 and 7, and so the 7 goes there. So that's a 2. That's a 7. I know now. Oops. I know now that's a 2. So that's a 3. Let's see. This is an 8. There aren't actually 5s in this puzzle, so that must be a 3 and that must be a 5. Let's see. That's a 2. Let's see. This is not 2, 3, or 8. So if it's not 2, 3, or 8, it's a 7. So the last 7 goes there. The last 8 goes there. Sorry, not the last 8, but that 8 goes there. That 8 goes there. That's a 3. That's a 2. That grid's done. Okay. So all kinds of fun stuff going on now. Okay, so top left corner. I think we have to probably resolve this by looking at the top left corner. Actually, let's not look at the top left corner. Let's look at this cell, where literally all but one of our things is filled in. So this is now not 1, not 2, not 3, not 4. It is 5. It's not 6. It's not 7. It's not 8. It's not 9. So that's a 5. Let's see. Do we know which of these is allowed to be 5 in this universe? I don't think I know which of those is allowed to be 5. Do I know which of these is allowed to be 5? I don't think so. So top right corner, we can do the same trick. So in top right corners, I have a 1, 2, 3, 4, 5, 6. I need a 7, so that digit's a 7. So I need a 7 down in one of these two cells, and I know which one. It's got to be that one by this grid. So now I need a 7 in one of these two cells, and it has to be this one. Sorry, one of these two cells, and it has to be this one by the central grid. Well, that's a 7. Okay, this cell, we can actually figure out what it is as well. It's not 1, 2. It's not 1, it's not 2. I think it's not 3. It's not 4. It's not 5, or... Oh, it is 6, because then it's not 7, 8, or 9. So yeah, so this is a 6. So now, which of these two is 6? It's that one by this cell. So now that's a 6. Let's see. The missing digit in this row is a 6. The missing digit in this box is a 9. So these are a 5 and a 9 in some order. Do we know the order? Yes, we do from this one. So that's the 5, that's the 9, and that's the 5, and that's the 9. Okay, so that's all well done. Okay, so now this cell we have in every grid except this one. So we've got a 1, a 2, a 3, a 4, a 5, a 6, a 7, and a 9. So this had better be an 8. So that's 8, that's 8, that's 8. That's 8. Let's see. And now I should be able to find one more cell where we know everything, maybe? No, these two... Okay, so these two have exactly the same space as empty, which must mean that I don't have 2 in enough boxes. I have 2 in 1, 2... I only have 2 in 3 grids, and I need to have 2 in 4 grids. So these have to be 2s. Because I can't also put 2s over here. And then we just now need to ask ourselves, okay, this is not... It's not 1, 2, 3, 4... And it is 5, because it's not 6, 7, 8, or 9. Yep, so these are 5s. Ta-da! And there we go. That was a lot of fun. Yeah, these multi-grid puzzles I think are quite enjoyable. This is very reminiscent. If you never did Sam Kappelman-Lyne's Sudoku Cube or whatever he called it, it was like 6x6s that had this disjoint property. I really recommend it. It was a lot of fun. I think I'm not certain, but I think Clover was likely inspired by Sam's puzzle. Anyway, that is the end of Bitty Bytes 2. I really enjoyed doing Bitty Bytes. That was a lot of fun. And so now I suppose... I know a lot of Clover's thing with Bitty Bytes was to take other puzzles of other people that she liked and try and make like a little bitty version of them. So I'm not too surprised that she was directly inspired by that Sam puzzle. Okay, so I'm going to pull up the Simon video real quick. And then I will be right back. Let's try and do this kind of on the fly with moderate success. So the thing and reacting to the to Simon doing my puzzle today. So I think this will work, but I think I need to add an audio source for this to work because I think you need to get my I think you need my PC audio as well. And I have to figure out how to get a, audio output capture? Is this what's going to do it? Use device timestamps. Okay, let's try this. Okay, so I'll work on getting the picture set up once it's actually playing, but I want to make sure you can actually hear the audio. Let's see. So let's play this and see. I also need to hear the audio. Can you hear Cracking the Cryptic music playing? Yes.
Hello and welcome to Wednesday's edition of Cracking the Cryptic.
Excellent. All right. In that case, I think we might have got this set up. So, yes, loudly. Okay, I can... Is that a request to de-louden it, or is it just an observation that it is hearable? Because I can de-louden it if you would like it de-loudened. Okay, let's quiet Simon down. Yes, we can get a Mark reaction video to my reaction video to the thing. Okay, so I put the audio. Okay, I'm gonna let Simon talk and put the
zetamath to the channel.
The audio here.
A very long gap between when zetamath last appeared, because actually zetamath was a collaborator.
So how's that volume?
Did last night, but this is just zetamath on his own with a puzzle called Distinction, and we've had this recommended several times since it first appeared, which I think actually was quite recently. But I will read you the rules to this one in a moment. Apparently, it is approachable, whatever that means in the current world.
No, it's too quiet.
I do not know. Couple of things to mention first. I think the first thing I want to say today
is that better?
Is have you looked at last night's video, which we called the Ultimate Miracle Sudoku? If you haven't, I would urge you to have a look at that puzzle. It's by Emre Kalotoglu, and it is quite remarkable. In fact, let me just show you. I have not yet
watched this puzzle that he's talking about, but I really want to, because this grid looks insane.
And you can see there are no given digits, and the clues that we are given are simply question marks. It is absolutely amazing that this puzzle exists. The question marks are sort of a hybrid of X sums and sandwich clues, and they have to, basically all they're saying is that in these columns, those types of clues are the same. It took me a very long time to solve it, but it really is. It's a stunning achievement that Emre has created here. So I thought some of you, if you didn't see last night's video,
it definitely is one of the ones that I looked at and was like, I'm going to let Simon solve this one.
Now, the next thing I need to say is a very, very happy birthday to Lisa Battersby. Lisa, your husband Stephen got in touch with us and said that you enjoy the channel a lot, and I know that the two of you have a very young person at home, a new daughter, just 3 months old. I'm not sure how you've got the time or the willpower to stay awake through one of my videos, but I'm very pleased that you enjoy the channel, and I hope you've had a great birthday today, and of course a big slice of cake. Now, the next bit of news is for our patrons over on Patreon. We have a very special new video for you by Philip Newman. Now, many of you will know Philip Newman if you've been following the channel for any amount of time. A setter of world renown, and recently created this world's hardest classic Sudoku, which many of you have had a go at. It was called Palpatine's Design, and Philip has very kindly made a video explaining, I suppose, A, how he came up with the idea behind that puzzle, B, a load of stuff about very hard classical Sudoku techniques, C, how to solve Palpatine's Design, and D, also running through why he chose the winners of the competition. And I need to
Philip
say
Newman is one of the premier classic
Sudoku
Sudoku
who goes
people,
under the
I would
name
say.
Pulsar77 online. And Emmanuel,
you definitely did this puzzle when I first published it in testing Totally Normal Cat, if I recall correctly. I think you were one of the very first people to complete the puzzle.
I'm also going to be sending a Bubba's key to Bill Murphy down there in Australia. Bill is a doyen of the Discord server, and Philip judged your entry, Bill, as the most amusing. I think primarily because it kept referring to your secret love of Mary Elizabeth Winstead and how hopefully that puzzle would lead you and she to get together. Well, I hope that's true. I'm sure Mary
I did promise Simon he could do it in under an hour, which he cut it closer than I think I estimated. But we'll
pass on Bill's details.
But I will say there's been an awful lot of divergence in what people's solve times have been on this puzzle.
It's a 1 hour video, so lots and lots of extra content there. Now let's get on with distinction by zetamath. What are the rules for this one? They are as follows. Normal Sudoku rules apply. Each purple line must contain a set of consecutive non-repeating digits. These digits can appear in any order. So these lines are normal renban lines. So let's look at this one.
I actually did not send a solution guide with this one.
To make it 9876, and I've just realised that will not work. So now I will put a 1 on it instead. So if that was a 1...
My general policy is if something has more than 30 solves on LMD and is rated at like 3 stars, then I won't send a solution guide. If there's fewer than that, then I usually will. But if something has been done so many times that I'm very confident that whoever's testing the puzzles could do it, then I don't worry about it as much. That is my usual thing. But I like writing up the solution guides if I think the puzzle is tricky, or if, say, it has not gotten 10 solves on LMD, that usually means that it definitely needs a solution guide.
That was a 2, that was a 3, and that was a 4. That would be a valid way of filling this renban line. Now, once you know there's a 1 on it, it has to be 1, 2, 3, and 4 because the digits have to be consecutive. But unlike thermometers, which obviously have to, if you find a thermometer in the Sudoku, it has to increase from the bulb end. With a renban line, you can put the digits in any order you want, so we can muddle them up. We can have the 2 down there, we can have the 1 here, we can have the 2 there, etc., etc. Lots of different permutations. Now, there is more to the rules, though, today. Additionally, no 2 purple lines can contain exactly the same set of digits. E.g., if one length 3 line, let's look at this one, contains the digits 3, 4, and 5, no other length 3 line can contain those exact digits. Okay, so that one could not be 3, 4, 5 either then. However, a length 4 line containing 2, 3, 4, 5, how's that going to have to look? Something like that. And a length 3 line containing 4, 5, 6, let's put 4, 5, 6 in that one, would both be acceptable. Okay, well that's completely how I would have understood the rules without the example, actually. So all that's saying is that if we work out that one of the 3-cell renbans, one of the 3-cell purple lines is 3, 4, 5, you can't put 3, 4, 5 on another one. And then the 4-cell renbans sort of sit in their world
This one I
apart.
actually did send in.
Although this does have 3, 4, 5 on it, it also has the 2. So it doesn't have exactly the same contents as this one, because it also has a 2. So that sort of makes sense to me. Do have a go at the puzzle. The way to play is to click the link under the video as usual. Now I get to play. Let's get cracking. Now, I have to say, I am minded to think that this will be about mod 3, because I know something about 3-cell renbans, of which there seem to be plenty in this puzzle. And that is that the digits on a 3-cell renban must always be, if you add them up, you will get a number divisible by 3. And that is because, if you think about the algebra of a 3-cell purple line, one of the digits on it will be the middle of the consecutive sequence. Let's call that digit x. I don't know if it'll let me do that, actually. Maybe it will if I change. Hang on, let me just see if I can do this. Is there a way to turn on...
If you're at all uncertain, I would send a solution guide.
Something. Or maybe
I definitely have had more success in getting puzzles to appear when I've sent them a solution guide.
I'm gonna have a go.
And I do agree with Finished Guy that writing solution guides is a really good way to sort of like quality test your puzzles.
Completely frivolous and a fool's errand. Letter tool on. Hold Alt for Shift for letters. Oh, good grief. Okay. So, oh, wow. Okay, so now everything's kicking off. So I think now if I press Alt on the keyboard, I go there. Oh, Sven. Look at Sven's software. It's just amazing. So now I'm going to label this X. I can label it X just by pressing Alt. So let's say that this is the middle digit on this renban, i.e. the digit that's the middle size of the 3 digits on the line. Then one of the digits will be slightly lower than x, so it'll be x minus 1. The other digit will be slightly higher than x, it will be x plus 1. So if you sum up those 3 digits together, you will get 3x, and 3x is obviously divisible by 3. That was all a very long way of showing that, but it was quite an advert for this remarkable software that Sven has made. Now, yeah, so what was I thinking about? 3x. I got distracted with all the algebra. So yeah, so if I know that a 3-cell renban is divisible by 3, let's have a look at where the 3-cell renbans live in this puzzle and see if we can use that to our advantage. I'm just going to
This is from today. It came out while I was streaming, so I figured I would do a reaction to it, as at least Niverio and Clover have done before.
Okay, that doesn't seem to do anything. I might well be missing a trick here. I'm not seeing how to use that. Sorry. Okay, so that's not the first way to look at this puzzle.
I was going to be very surprised if he got somewhere from looking at this mod 3, but I've been surprised before.
So my next hunch, and that's all it is to look at the 2-cell renbans. And the only reason I want to look at these is this looks, it looks like zetamath has sort of hidden a pattern in here. These 2-cell renbans, you know, it's not like there's just one of them hidden in a corner acting as a disambiguating pattern. That looks like, it almost looks like zetamath wanted to make this one vertical but then didn't. Right, I can tell you something about the central cell. That is orange. It's also odd because both of those things begin with O. Now, why is this
if you
orange?
Shout loud enough in the chat, it'll help.
Well,
Simon.
it's because of the nature of a 2-cell renban. If you think about any 2-cell purple line in this puzzle, it contains consecutive digits, so it contains an odd and an even digit. Now, in any row of the sudoku, you've got the digits 1 to 9 once each. So there are only 4 even digits, the digits 2, 4, 6, and 8. And we know that they must be disposed along these 4 lines because each one of them individually needs an even digit. So that one must be the spare one, and that must be an odd digit. Now that means that... Oh, that means this domino at the top, unfortunately, is an odd and an even digit, because we're going to have 3 evens in those 6 cells, and we're going to have 4 odds in those 7 cells. So we need 1 more odd and 1 more even at the top of the column. And that's absolutely useless. Oh my goodness me. Right, okay, I'm not on the same wavelength yet as zetamath. Now, zetamath, what else have you hidden in your puzzle then? 1, 2, 3, 4, 5,
there we
6,
go.
7, 8 two-cell renbans. Which is all of them. Okay, right, that's interesting. That is all of them, isn't it? Yes, it is, because, right. Okay, so now we need to use the rule that says that none of these purple lines can contain the identical constituents. And let's think about all the possible combinations of two-cell lines that could exist in this puzzle. There's going to be a 1 and a 2 somewhere in it, a 2 and a 3, a 3 and a 4. Well, yeah, this would be all possible two-cell combinations. So 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9. There are 8 different combinations, and that makes sense because as we go up the digits, we go from the 1, 2 pair to the 2, 3 pair, etc. When we reach 8 and we do the 8, 9 pair, we can't go up again and do the 9, 10 pair. That doesn't exist. So there are only 8 pairs, and there are exactly 8 two-cell renbans in this puzzle. So every single possible combination is represented, and that is very beautiful indeed, because now that digit is odd, and it's the same as that one. Isn't that amazing? And the reason for that, of course, is that whatever this digit is, it must be one of the digits from 1 to 9, and it must therefore appear on a two-cell renban in this puzzle, because all digits appear on at least one two-cell renban. Yeah, so the 1 and the 9 only appear on one two-cell renban, because once you've done the 1 and the 2, you can't do a 1 and a 3 or anything. So the one has only one option, but the 2 will be on 2 different.
I did not make anything look like a face. I'm trying to see the frowny face. I'm not sure I can even see it.
So yeah, so every digit is on a two-cell renban once.
Oh, I see it.
And this digit
you're talking
is
about
of
this piece.
All of those and that one. So it must be there.
So no, the 4-cell renbans were nearly forced where I had to put them in order to make the puzzle actually resolve. So yeah, by the time the 4-cell renbans were the last ones I placed. So by the time I was placing 4-cell renbans, there was very little thought about aesthetics. It was almost entirely what will make the puzzle actually work. Because I expected that I could, when I sort of was setting this, I originally thought, oh, I'll do all the 2 and 3-cell renbans, and then that'll solve the puzzle with maybe like a given or whatever. But then that turned out not to be the case. And so then I wanted specifically, okay, well, if I'm going to use 4-cell renbans, it needs to be the case that you need to use the rule that the 4-cell renbans... Yeah, I guess I could have rotated it. I did not even really think about rotation. But yeah, so I eventually ended up placing it so that you needed to use the distinction rule on the 4-length renbans in order to resolve the puzzle.
And therefore this digit is odd. So let's actually label the options up. Yeah, okay, because that means that one is on a renban with an odd number, so that's even. I think we use blue for even.
Nissig asks how long it takes to set something like this. It varies a lot. So in this case, I set a whole version of this puzzle with almost this rule set. That took a day or two, and then I didn't like that puzzle, but I learned enough by setting it that I then went and set this puzzle. And so, like, actually, from when I drew that plus sign with the renbans that Simon zeroed in on to when it was done, that was maybe 4 hours, 8 hours, so somewhere in the span of 1 to 2 days. It wasn't super long, but that's discounting the fact that I had to set a bunch of bad puzzles with this rule set before I did this.
This digit, this orange digit, must be on this renban. Which, hang on a minute, I'm not understanding quite what this does.
Totally Normal Cat in chat was one of the first people who tested it for me. Who's asking
it's too cute. In fact, well, this is, yeah, let's go back to what I said at the start, which is I thought zetamath had wanted to create this sort of a perfect pattern with this being a vertical domino. Well, actually, that would have broken the puzzle now, I'm realizing, because there would have been all 8 different possible 2-cell renbans, and this digit could never have appeared on all of them. So there had to be a break in the pattern. Okay. I don't know what to do with that. Oh dear. 4-cell renbans?
He is very, very close.
We have got...
It's funny because this opening is very similar to Nabner, where I think Simon's solve of Nabner is one of the fastest that has ever happened, because he was right there on what the Nabner opening was.
Because I don't think we know anything about the modulus of the sum of the digits on a 4-cell renban. And, well, I suppose we can say it's got 2 odds and 2 even numbers on it, which I don't think is helping us, even though zetamath has been kind enough to give me 2 given digits today. Okay. Have I missed something on the 3-cell renbans? That's probably what's happened. Let's do the 3-cell renbans again. 1, 2, 3, 4, 5, 6, 7. I think that's all of them again. Let's highlight those again, in particularly garish yellow. So we've got 7 of these. How many are we meant to have of these if we had all of them? Right, okay, sorry, I had not appreciated this at all when I highlighted this last time. Yeah, that's right. There are only 7 possible combinations of 3-cell renbans, aren't there? Because 1, 2, 3, 2, 3, 4, 3, 4, 5, etc. And when you get to 7, you do 7, 8, 9. But there's no combination associated just with 8, 9, because you can't go 8, 9, 10, and obviously then you can't go 9, 10, 11. So as you increase the length of a renban, you reduce the number of possible renbans associated with that length. Right, okay, so that means that we have to have every single possible version of 3-cell renbans in this combination. Oh, I know what this might be. I know what this is. If this is right, this is going to be very interesting. Let me just have a stare at this for a second before I do some highlighting I'm going to regret. I can't see it. I can't see it without doing the highlighting. Sorry, I'm going to have to highlight this. So I'm just going to highlight those cells in black. And I'm also going to highlight all of the 2-cell renbans as well. Like that. Now, what I'm wondering...
I think he's going to get this in a really, really complicated way.
Yeah, this is right. I've got it. Right, this is absolutely ridiculously clever. And it's also very deeply surprising to me that this is where we went with this. Because this is almost a set type thing going on. But it's this sort of strange way to think about it. So what I'm thinking is that if we think about the nature of all of the black cells, we know that they are all the possible 2-cell renbans that exist and all the possible 3-cell renbans that exist. So how many 1s and how many 9s do we think that there are in the black cells of this puzzle? Well, we know on the 2-cell renban, the only time the 1 appears is in the 1, 2.
I'm definitely surprised we're going here.
9. So there is, in the 2-cell renbans, there is
so just to say how I would explain what's happening before he does this, because I think he's about to combine together the 2 and 3-cell renbans, and I thought about this purely in terms of the 2-cell renbans, and namely how many 2-cell renbans is this digit on? And this digit can only be on one 2-cell renban. Well, most digits need to be on 2 different 2-cell renbans. And so this digit, for example, if this digit were a 3, it would be a problem because that would need to be both on 2, 3, and 3, 4, and it can't be. And so that tells you that this has to be 1 or 9, which is then going to sort of percolate. And I think what Simon's doing is he's adding together that fact for all the length 2 renbans with the corresponding fact for all the length 3 renbans, and now he's going to try and count the 1s and 9s and 2s and 8s. And, well, I'm excited to see where this goes, but I have no idea. And yes, Niverio, this is the reaction stream.
There's 1 1 and 1 9. But in the 3-cell renbans, it's the same. The 1, 2, 3 combo is the only time the 1 appears. The 7, 8, 9 combo is the only time the 9 appears. So within all of the black cells, there are 2 1s and 2 9s only. But look, if we look at the sort of Maltese cross in this grid, if we look at this shape, that's 5 complete boxes of the sudoku. So in that shape, there must be 5 1s and there must be 5 9s. And therefore I've got to fit into these cells. Let me get this right. Those cells there, they have to contain the blue. Sorry, and I'm now polluting my blues. And hang on, let me uncolour these ones. Hang on, I've got to keep the black. I'm going to just remember that thing about the middle and these two being the same. So, right. So what I'm saying
this is cool. I mean, it's going to get him some stuff
in the blue cells and 3 9s in the blue cells, and that's
though. At the end, he's going to say he doesn't see how this is a 3-star puzzle.
It's completely beautiful. It's completely beautiful, not just because the pattern I've made is actually quite pretty, but how are we going to put 3 1s in the blue cells? Now, in row 4, I can put 1 1. And in row 6, I can put 1 1. I can't put 2 1s in either of those cells. So in all of those cells, there can be exactly 2 1s.
Hey, Chip.
So now I need to put a 1 either here or here to complete the quota of 1s. But of course, the same logic I've just done applies identically to 9s. I can put a 9 in row 4 in a blue cell. I can put a second 9 in row 6 in a blue cell, but I've still got to put 1 more 9 into the blue cells. So the 9 will have to go there. So this is a 1-9 pair. And if this is a 1-9 pair, that digit there, which we know is the same as the central cell, is a 1 or a 9. That's just, I mean, oh, so this even digit is...
Oh, I mean, I didn't rate the difficulty myself. The 30 plus people who did this on Logic Masters Germany said this was a 3 out of 5. I would never trust my own assessment of the difficulty of a puzzle.
Trying to do this sort of analysis. Right, now. No, yeah, oh, my brain's going mad now. Right. Now look, I've got a 1-9 pair in column 4. Now that means when we were thinking about the fact we needed to put a 1 and a 9,
I actually thought this one was a 3 and it ended up as a 3.
They can't go in these 2 cells anymore because there's a 1-9 pair already looking at those 2 cells. So they get de-bluified, and if they get de-bluified, now the 1 and 9 I know exist in blue in row 6 have to be in here. So they're in there.
This is very cool, though. I mean, this is actually like going to get him some very useful stuff.
And I'm only left with 2 bluified cells in row 4, which have to now be 1 and 9. QED.
There are definitely 3 of 5 puzzles.
My earlier thought, which was that this was meant to be approached, but that is not it. That's really.
This is definitely not the approachable way to do the puzzle.
Beautiful logic. Don't get me wrong. It is beautiful logic, but you have to you really have to be careful about counting your.
The comments are going to be all people explaining to him the way to do this,
and then thinking about the composition of the totals, and then noticing the overlap with the cross, all of which strikes me as being not easy. It's taken me 22 minutes to do it. I'm sorry about that. Maybe this is just
He was so close. He was right there as he was explaining it at the beginning, and
anyway,
then he went off on this.
I love it. Now, I can do some Sudoku now, because look, I've got 1, 9, 1, 9. I've got to put, therefore, 1s and 9s into those 3 cells in row 5. On that one can't be a 1 or a 9 because it sees a 1, 9 in its column.
This is very hilarious that it did not get him the thing that I thought.
Aha, I have a digit. That's an extreme even digit. It's either 2 or 8 because it's got to be consecutive with 1 or 9, and it's not 2. So that's 8. That's 9. That's 1. We know that's the same as that. So that's 1. That's 2. That's 9.
So just a bit of like behind the scenes setting stuff. This puzzle solves uniquely without this 2. Like humanly, it is solvable without this 2. However, I don't think it solves in a way that is super fun without the 2, because a lot of the stuff you end up chasing around ends up being quite difficult to keep track of if you don't actually if you don't keep this 2 here. So most of my puzzles have more information in them than is strictly necessary to make them unique and to make them humanable. I think that's usually a good idea to ask yourself, like, is it fun to have to chase all of the possibilities through the puzzle, yes or no? And I think for some puzzles it will be, and my impression was for this one it was not.
So 9 is now in one of these 2 cells, and whichever one... Ooh... Well, it would be very useful if it's there, because this renban would be determined.
Hey, Kodak. We're reacting to Simon solving one of my recent puzzles.
Oh. Yes. Yeah, I know which one it is. It's not this one, because if the 9 is there, it has to go with 8, and it will be the same. It will be a zygotically identical twin to its friend there, and that won't work. That's not allowed by the rules, so that can't be 9. So the 9 goes up here, and that's huge. Because if that's 9, 8 must go here, 7 must go here. So now 8 is in one of these cells.
Yeah, I mean, part of the reason I thought to do this is because Simon was excited to see other people doing reaction videos.
It might... actually, I don't need the blue now, do I? Let me just de-bluify the whole grid, I think, while I stare at this and try and work out what's going on. Yeah. Look, there's a 1 on that renban.
Which is something he saw right at the beginning and then went on the...
So now, in our 3-cell renbans,
we've got a
987. Well, yeah, we've got 987 and a 123. So actually, if there was an 8 on this renban, it would have to not be the 987.
Yeah, all of my streams are automatically available on YouTube, Javier, so you won't miss anything. You can go back and watch anything. You can watch this tomorrow or any of my other stuff. So feel free to go to sleep, and it will be here for you tomorrow.
2 must be in one of those 2 cells, because of this 2, and this 2 all interacting. If 2 is on the line, that would have to be a 3, because it couldn't be a 1. So 2, 3... oh dear, now I'm stuck, I think. Oh, no, hang on, look at column 6 by Sudoku. Those must be 4s, 5s, and 6s. So that digit needs to be 3, 4, 5, 6, or 7. Are we prepared to... Yes, I am. I'm not proud. 3, 4, 5, 6, or 7. Okay. So, now what do we do?
Sleep well.
That is the next question. We have got to think about... I don't actually know what to do now. I thought it would be more obvious, but I'm not seeing anything.
Sleep well, Nicholas. Thanks for some of your cool observations earlier.
We don't know where 3 is in this box. These squares are 3s, 4s, 5s, and 6s. So that cell can't be 3, 4, 5, or 6 because it sees this one on its
Wow,
renban.
Simon solved that fast.
So whatever these 3 are, obviously it can't be the same as this, but this is also not able to be this. And as this is a quadruple, that therefore restricts this value, which also can't be 8. And actually, it can't be 1 or 9, because 1 and 9 are not consecutive.
Oh, thank you,
3, 4,
Kurban.
5,
Tristan
and
made
6.
that.
So
I am
that square is
excited
a bit
by the new
restricted.
thumbnail as well.
It's not the same as 7. So it's 2 or 7. I was going to say it's not the same as 7 different digits, but actually it is the same. It could be the same as 7 itself. So this is 2 or 7. So if this is 2, this is 3, 4, this is 5, 6. I don't see what's wrong with that. What about if this is 7? If this is 7, this is 5, 6 then. So this is 3, 4.
Yeah, I think you dig this one, Kodak, but I know you were on vacation, so you have all this puzzle, so you can just watch Simon do it, as would be my usual strategy.
Okay. 9 in this box is restricted because I can't put 9 on that renban. And I remember I can't put 9 on that renban because I tried to do it in the example when we were looking at the puzzle, and I noticed that 8 couldn't go on this renban. So that means that in this box, 9 has to be in this domino, look. So 9 is in one of those 3 squares. Oh, right, that's beautiful. That is beautiful. In fact, I just noticed that can't be an 8. But where does 9 go in this box? It can't go on this renban, or this renban would be 9, 8, 7 and be the same as this one, which is not allowed by the rules. So that's not 9. This is 9. That's 9. This is 1. This is 8. 9 is almost locked onto this renban, which would make this renban 9, 8, 7, 6, which would then not have to be the same as... Oh, okay, we don't know about these at all, actually. We know that one is not 9, 8, 7, 6, but we don't know about this one, so we don't know what this is. What else have we got here? We've got 8 has to be in one of these 3 cells. 1. I don't know. I've got 8. Oh, look. Yeah, I've got 8 on this renban, and it can't have 9 on it. So those 2 squares have got to be 6 and 7. So 1 in this row has to be... beautiful. So 1 has to be on this little renban. And once 1 is on a renban, we know the composition of the renban. That's 1, 2, 3, and 4 with a 1 in one of those. So that's not 2. So 7 only has 2 possible positions in row 3. But what... Oh, I see. If that's 2, then that can be 2, and that wouldn't necessarily break the puzzle. So... Now what do we do? Now where shall we look? We shall look at 7. No, 7's still got 3 possible positions in box 1. Oh, 1 has to be in one of those 2 cells in box 3 by Sudoku now. Oh, that just follows from the 1 being here. Okay. So we've now got a 987 renban. We've got a 123 renban. I've got an 876 renban. So I need to have a 234 renban, which could be that one. Oh, okay. So where is the 234 renban in this puzzle? Now that's
I thought
one
Simon would see
possibility.
this.
Now it can't be this one because this 2 rules it out. And it can't be that one. And it can't be this one. I think it might be able to be that one. Let me just have a look.
This is optional.
So is it just 2 possibilities for the 2,
but it is
3,
very
4
helpful
renban?
towards solving it.
I want to say yes. I might be missing one of these. I might be missing another 3-cell renban. I can't see any other options. And this can't be a 2, 3, 4 renban, can it? Because it can't have 2 and 3 on it. I can put 2 or 3 in this cell, but I can't put both of them in. So I may be wrong about this, but I think this is the only one that can be 2, 3, 4. It's weird scanning you have to do in this puzzle, because I'm having to scan all the renbans and count their lengths and check. I think these are the only 2 candidates though. So if that's right, this has to be the 2 on this 2, 3, 4 renban. So that means these 2 squares are not. So this is a 5, 6 pair, which makes this a 7 and this a 6. So now 6 has to live in one of those squares in box 1. 2 comes out. Oh, 2 has to appear on that renban, so it has to go there. So this becomes 1. Oh, I see. This becomes a 1, 3, 4 triple. 2 has to live down here in box 7. This square has got to be 4, 5, 6, or 7. And that is very useful for some reason I can't appreciate. Right. Now we get stuck again. What we should look at now is... No. I want to say that you can't put 7 on here, because I need to put 8 in this column, and 8 can't accompany 9 in this column, because the 9's already been used. So in this column, wherever the 8 goes, and it's going to be in one of those 4 cells, it must accompany 7 on its renban. So that square I don't think can be 7.
Nice spot.
And that is the world's most useless deduction. Oh, well, apart from it gives me a 4, 5, 6 triple in column in box 5 I've just seen. Well, and therefore, actually, that's quite good, because now a 3 in this box is suddenly placeable here. And that means I should be able to deduce what this digit is. Because it can't be 2, so it's got to be 4. So that is now a 5, 6 pair. And this down at the bottom must be a 7, 8 pair. Which means these 2 squares have got to be a 5, 6 pair, I think. And that square has got to be... Oh, now, I've got a 5, 6, 2-cell renban, but I can have a 5, 6, 3-cell renban. So this square has got to either be 4 or 7. Right, I understand what I've got to do next, because now I'm going to look at the remaining renbans. Doesn't one of these renbans have to be a 3, 4, 5 renban? I think it does. And I haven't got one of those unless it's this one. So I think this... I know, I'm not sure I know what that one is, but this 3 is ruling out 3.
Good luck on the exam, Logan.
Renban. That one doesn't seem to have 3 on it. So I think that one has to be the 3... It's got to be 3, 4, 5, and the 4 must go there, the 5 must go there, the 5 goes there, the 6 goes there. And now that's a 6 by Sudoku. So now we've got... Yeah, okay, so this is either the 4, 5, 6 or the 7, 6, 5, and then this is the other one. So there must be a 5 on this renban. That is what we can say for certain. And that means that 5 is in one of these 3 cells. And 5 is not here because it would have to be with 4 or 6 on its renban. So that is a 5 on this renban. And we can probably work out, yes, we can. Yes, we can work out the composition of this renban because the 1 has been missed out. We know the 2 will pair off with the 3, then the 4 must pair off with the 5. So that's a 4, 5 pair. So 4 is now in a sort of an arrangement. We've got 2 4s in those 5 cells of columns 1 and 2. Now, how many 4s are we expecting there to be in columns 1 and 2? Exactly 2, and they are in those 5 cells. So there are no more 4s in any of these cells. So the 4 in this column has to be down in one of those 3 cells. That's very annoying, because it seems to be able to be on the renban or in the digit at the bottom. Right. Oh, no, I know what we do. 4, 4, there's got to be a 4 on this renban. So that's 4, 5. So this is now 6, 7, I think. Oh, that's done. 6, aha! I'm getting all my pencil marks wrong. Look, this 6 now has to go there. That has to be 7 by sudoku. This has to be a 2, 3 pair, and the 2 can't go there. So that's 2, that's 3. Those 2 squares are 7 and 8, I want to say, which seems to be possible either way round.
Yeah, in my sort of like way I'd go through this, Ben, I would have used the fact that I knew what the things were in column 5 and then worked through how they had to be by using box 8. But he ended up getting there through his counting argument in a different way. So he didn't use it in the column, but then used it in the row.
These 2 squares, I seem to have this already pencil marked in, but that's a 7-9 pair because of this 9-7 pair at the top. So those 2 squares have got to be 5 and 6 to fill this box and make sure it's replete with digits it should have. So these 3 squares are 2, 3 and 4 by sudoku. These squares are 1, 5 by sudoku. 5s are aligning in column 7 and 8, so we can ask where 5 should go in column 9, and it's going to have to be almost on the renban. Yes, and if this is 4, 5, 6, that one is not 4, 5, 6, so this must have 7 on it. This is so clever. So that's 7, that's 7, that's 8, that's no longer 8. This 7 is fixing a 7 and a 9 in this box, look, by sudoku. That's no longer a 9, but it can still be a 1.
I think part of what makes this puzzle a bit more approachable than a lot of my puzzles is that there are a lot of different ways to go through it, including at least one I did not know about that I learned about from Simon.
4 7s looking at box 9. So this must
but yeah,
be 7.
I'm a very big fan of different solutions
beautiful.
to the same puzzle.
Right, because why is that beautiful? Well, if you can't put 7 on that renban, you definitely can't put 8 and 9 on it, because it's a 4-cell renban, so it's going to need those digits. So the 9 shifts up to here, and the 8, I think, now has to go there. Which means 8 is... Can 8 be on the renban with a 4? 4, 5... No, it can't. So 8 is placed now in this box, because you can't put it on this renban with a 4. 4, 5, 6, 7 is as high as you could go. So that becomes 8. Surely that's resolved, isn't it? Which one of these is 8? No, okay, maybe it isn't. So, oh, right, the other thing is, we now know quite a lot about this line. And that's because it's got a 5 on it, but it doesn't have a 7 on it. So it must have, it's the maximum it is 6, 5, 4, 3. So it must have 4 and 3 on it. So it doesn't have 1 on it. Oh, that still doesn't do anything. Okay. Okay, that's not a 2. Oh, bother. I think I'm getting stuck. It was going really well for a moment or two, and now I've ground to a halt. There's a 9 in one of those 2 cells. So is there something I can say about this? This renban doesn't have 7 on it, and it does have 4 on it. So we're selecting a slice of 4 digits from the digits 1, 2, 3, 4, 5, and 6. So there must be a 3 on this renban, which must actually therefore be in those 2 squares because of the 3 here. Oh, hang on. Yeah, look, there's a 4 looking at this as well, looking at that cell. Sorry, I could have done that by sudoku. That's a 4. So now that's not a 4. Okay, that's very interesting, but doesn't seem to do anything. So I can see here there's a 6 in one of those 2 cells. Now that aligns the 6's, look, in columns 1 and 3. So in column 2, the 6 is down here, and what I'd really like to know is that it's not there. For what reason can we say that that is the case? I don't think I can say that, I'm afraid. So I'm afraid we're going to have to carry on thinking. 4, 5. So this renban might have
givens
6
are
on it,
vicious.
but it might not. We don't know either way. Is there some way of doing this so that we can learn more about the world? We can... Oh, okay, there's a 5 on this renban and there's a 5 here. So there's a 5 in one of these 3 cells. Is that useful? Nearly. I'm very close, I think, to forcing digits onto this renban, but I can't quite do it. These squares are from 6, 7 and 8. Have we got more? It's almost certainly going to be sudoku, isn't it? That's normally the thing that I forget to do. So let me just check whether I can do some sudoku to help me here.
Thank you, David. I'm happy to do it. I have a lot of fun with this.
Sudoku. You want to help me. Help me to learn about the puzzle. 9s. I can't see how to do it. Maybe it's... Okay, in this column, these squares have to be from 3, 4 and 5. Is that helpful? The answer is I don't know. 6 is almost very restricted in box 9. It's one of 2 places. If I can force 6 onto the line, it would be happy days because there's no 7 on the line. We'd know the line was 6, 5, 4, 3. And this would be a 1, 2 pair, which might be possible. Don't know actually. No, hang on a minute. I see what we do. Right, the key is the 2s. There is a 2 in one of those cells, so there is no 2 on this renban. If there's no 2 on that renban, then what's on it? It's a 4-cell renban that doesn't have a 7 or a 2 on it, so it must be 3, 4, 5, 6. So that's a 3, 4, 5, 6 renban, and I want to say that therefore I can fill it in, but I'm not sure I can. I can say those are 3, 5 and 6. I can say that's certainly not a 3. I can say probably some other things as well. But also, now I've got to have 1. This is not 6. I've got to have 1 in one of these 3 cells. Now that's interesting because the 1 in box 1 is in one of those 3 cells. So these are not 1, and that must be the 1 in box 4. And now I should ask where the 8 goes in this box and use my pencil marks. So that's the 8, that's the 8, that's the 7, that's a 6, that's a 6, that's a 5. We know that's not a 5 already because it's been forced onto this renban here. But this 5 is giving me a 5 here, that's giving me a 4 here. Those 2 squares are now a 7, 9 pair, which is resolved. 7 and 9 go in the grid. 9 gets put in the corner. That puts 2 and 1 into those cells. That cell is now not 1. This cell must be known. That's a 5.
Yeah,
So
the design was specifically that learning that this renban had a 6 on it tells you the other one doesn't. That was what I designed all of this.
Now we're getting hopeful, I think.
These machinations
let's
for.
Put 3, 6 into those squares. Let's put... How is this resolved? So this square's got to be 1 or 6 only. And 2, 3, 4, 5. Oh, I see. Yes, I do see. This is beautiful. Right. So now, yeah, look, the 7 here operates a bit like the 7 here. So if 6 is on this renban, this has got to be a 6, 5, 4, 3 renban, where it would become the same as its friend over there, which is not allowed by the rules. So you can't put 6 on this renban. So the 6 must go there, which means that's 6, that's 3, That's 1. It's probably done something. It's given me a 6 here and a 5 here, which means this is not a 5 anymore. So if this renban hasn't got... So this is 1 by sudoku. So there is a 2 on this renban. That's a 1, that's a 5, that's a 5, that's a 4. Okay, so now this must be a 2-3 pair. So there's a 2-3 pair in the bottom row. So goodness only knows what these 2 cells are. Let's try and work it out. These are somehow 4s and 5s. And there's a 5 here. So 5 goes in the corner. That's a 4, that's a 2, that's a 3, that's a 4, that's a 3, that's a 3, that's a 2, and that's a 2. And suddenly... Oh, that's a strange thing. Looks good to me. Sorry, that's a different version of the normal Sven finishing. Must be because I'm using the test solver in order to do the X thing I did at the start. That is just magnificent. What a magnificent puzzle. It's so surprising as well. I was convinced when I read the rules and when I saw the grid layout, it was all going to be about mod 3 and possibly parity. But it's not at all, and it's a very beautiful idea that there has to be a particular number of 1s and 9s in this sort of Maltese cross of the grid, and so much of that was consumed with non-repeatable renbans. It was beautiful, and then the whole way that you got this, well, the whole way you got those digits then being 1s and 9s with this one, and that forced a 1-9 pair here. Can't remember quite what happened after that, and then we just had to keep track, which I think I probably did very badly, of which 3-cell renbans we'd used and which 3-cell renbans we had not used. And slowly it revealed its secrets to us. So zetamath, take yet another bow, my friend. Very much enjoyed. I hope you did enjoy it. You all enjoyed it too. Let me know in the comments. I do enjoy them, especially when they're kind. And we'll be back later with another edition of Cracking the Cryptic.
Well, that was a lot of fun. So let's see. I want to talk just a little bit about... So first of all, I should say... as much as we in chat somewhat tease Simon for the fact that he did this in a somewhat complicated way, he really honed in on exactly the right thing to ask, which is how many... let's see, I'm going to pull up a copy of this puzzle. I bet I can do that. Okay, and we'll switch back to CTC mode. Okay, so the thing that Simon did here was to count all of the 3-cell renbans in here and look for 1s and 9s, but he absolutely picked up on exactly the right thing to ask, which was about, okay, how many 1s and 9s are there on these things? And so my sort of intended solution path was to notice whatever this digit is, it has to show up on all of its renbans, because every possible length to renban is in the puzzle, exactly like Simon said. By the way, let me remove my audio. Oh, did I? There we go. Okay, there we go. Let's remove that. I don't want you accidentally hearing, I mean, I don't know, random Windows noises or whatever. Oh, wow, my thing didn't replace this. Usually my computer automatically makes things go to the test version instead of whatever. But anyway, this digit needs to show up on every length to renban it does. So every length to renban it does is only one possible. It has to show up on a renban. It can only be there. So these two are immediately the same. And then the deduction that I had in mind was, okay, so what does that mean? This digit is, it's 1 or 9. And so people in chat were going over that. And so now, where's the other 1 or 9 in this row was the question I intended to ask next. Okay, so this is purple 1, 9. Where's the yellow 1, 9? Well, the yellow 1, 9 in this row is with the yellow 2, 8. It's with either the 2 or the 8. So then where's the yellow 1, 9 in this column? Well, the yellow 1, 9 in this column, now it can't repeat on a renban because that would be repeating the renban that exists in row 5. And so it has to actually go here. Was the way I sort of saw this. But it's still exactly what Simon was doing, which is to say we're going to count all of the 1, 9s and think about them. And so now the way this sort of proceeds is, okay, so now there's a purple down here. So there's a purple over here. So now this yellow is on this renban, so this renban's all yellow. And so we have both extreme length 3 renbans from the beginning. And you can get the digit that Simon got here now by asking, okay, where does the yellow 1, 9 go in this box? The yellow 1, 9 in this box can only go here, because if I put it on the length 3 renban, it would repeat that length 3 renban. And so then we ask, okay, where does the yellow 1, 9 go in this column? And it can't go here or here, because that would repeat it on a length 3 renban, so it goes here, and then we end up here, and now we converge back to exactly where Simon was. So Simon identified that it was the counting the 1, 9s that was important, and then got exactly the digits that I intended you to get, or exactly the pattern that I intended you to get, because this now tells you, okay, so this has to be 9 and this has to be 8, because if this was 1, this would be 2. But in a way that was sort of like putting together the two pieces of logic that I think are a little more clear separately, if you think about the length 3 and the length 2 renban separately. I'll notice, just because it's cute, after I set this puzzle, there's an accidental thing that happens here where you can ask about what happens with 1 and 9 in this row. Well, where's the 9 going to go? Well, the 9 can't possibly go here, because if the 9 was on this length 4 renban, it would need an 8, and it can't have 1. The 9 can't be on this length 3 renban. Can't be in here, it's the 1, 9 pair. Can't be here, because it would repeat on a length 3 renban. Can't be either of those places, it would repeat on length 3 renban. So actually, if you look at in row 3, you get that this is a 9, and then you now ask where the 1 goes, and you actually get that the 1 now, because there's a 1 over down here, the 1 now has to go over here, and so this would be 1, 2, 3, 4. And so then you sort of can go off to the races from there. But that was completely unintended. I only noticed that in like my third test solve. I was like, wait a second, I actually really packed this this row, so it lets you sort of circumvent some extra logic if you want. Alrighty, well, that was a lot of fun. Thank you to Simon for solving the puzzle. That was a lot of fun to see. Hopefully those of you who did this puzzle had fun with it. I really enjoyed setting this one. Question for, or sort of proposal. I'd like to see a version of this rule set with arrows. So I don't know if I'm capable of setting it, but there are some number of length 2 arrows. I think there are 16 length 2 arrows in total. I'd love to see if you could make a version of this that just used that. So any of you fancy arrow setters in the chat, I'd be interested to see how you did this. So the first version of this puzzle I did used like it was sort of like a kitchen sink one where I used every kind of clue, and so there are whispers and renban and X's and V's, but the V's couldn't be the same as the whispers or whatever, et cetera, et cetera. So yeah, I'd be really interested to see if you could do this with length 2 arrows. I'm almost positive you could, and that it would be cool, but I don't think that I don't know that I could do it. All right, I'm going to take a real quick break. I'll be right back, and then we can do more puzzles. Welcome back. So we just had Simon do my renban with a twist puzzle, so I'm going to do Memeristor and the Kojito's renban with a twist puzzles. So, by the way, to people in chat who are talking about thermos and arrows and whatnot, so in my original version of Distinction, there were a bunch of thermos and a bunch of length 2 renbans, and then the clever thing was, oh, the thermos can't be consecutive because the length 2 thermos, if they were consecutive, would match one of the renbans. So I sort of used that, playing those two off of each other. I think you could do something similar with lots of length 2 thermos. My idea for the break-in, so if you want to make the arrow distinction puzzle, is to have 16 length 2 arrows that are completely contained in a row, column, or box, and then have several other length 2 arrows that go diagonally across boxes. And so those that go diagonally across boxes, because there were 16 length 2 arrows that saw all of their own digits, they couldn't contain repeat digits. But that would cover every arrow that contained no repeat digits. And so the deduction you would get out of that combinatorics argument is that these two digits on the length 2 arrow had to be identical. And so then you could do something where you sort of chase, okay, these two have to be the same, and chase it around the grid and maybe get some cool deduction that way. That is my suggested way of making a break-in for this, if you are so inclined. Alrighty, so this we're doing something with renbans. I don't know what yet. Let's read the rules together. So some of the purple lines are renban lines. A renban line contains a set of consecutive digits in any order. However, some of the purple lines are instead 2 renbans adjoined at the renban's midpoint. These adjoined renbans must most contain the same set of unique digits, not necessarily in the same order. Okay, so if this is a real renban, it could be, for example, 3, 4, 5, 6. It's just a string of 4 consecutive digits put in whatever order they feel like existing in today. If it's not that, then it could be 2 separate renbans. But if it is 2 separate renbans, then those have to be the same digits. So it could be 7, 8, and 7, 8, for example. I actually just set a puzzle that involves like lines that can be split into sublines or whatever, that I think is going to be unveiled by Ranks shortly. That will be fun. But I will publish it after that. So if you're looking for more Zeta puzzles, there are more Zeta puzzles forthcoming. Okay. Yeah. And so which renbans need to get split up? That is for us to decide. Okay, so are any of these things either too long or too odd in length to not be split? Okay, so this could not be split because its length is odd. So this renban, this is a real honest renban. So I believe, if I understand this, I'm going to reread this real carefully, but I think if a renban has odd length, then it cannot possibly be split in this fashion. Let me know if I'm misinterpreting this, but I think that I think this has to be a real renban because its length is odd, as does this, as does this. It doesn't say share a cell. Like, I feel like, let's see, in the example, they can share one cell. So for example, the purple length starts in row 6, column 2. Okay, so I think the example will help. Containing the same... Okay, so... Okay, so I guess... Okay, so I think in the example, they're specifically including the possibility that this is a length 4 renban joined with this length 4 renban. Okay, so I guess that's... I guess we can make do that. Sadly, it ruins my deduction about the digit 5 and the nature of the universe. Oh, no, I can get it anyway. This is a real renban. If this were 2 renban, they would each be of length 5, and they would each need to have a 5 on them. But I can only fit one 5 on this line. So there needs to be a 5 up here, but I can't put one anywhere down here just because of the givens. And so as a result of that, this is a real renban. No splitty business here. I don't think I need to mark that the length 2 renban are real renban. Okay, so this is probably going to be a count the 5s puzzle. Maybe not. Okay, so this renban must be split, because this renban sees a 4 all along it. And if this were actually an 8-length renban, it would have to have a 4 on it, and it can't. So this renban is split. So we'll split it like that. And there are exactly 2 split renban, right? Oh, no, it does not say that. I don't know where I got that from. There are some split renban. Okay, so these are 2 split renban, meaning that these sets of 4 digits are the same as... This set of 4 digits is the same as that set of 4 digits. Set of 4 digits. Okay. In particular, they contain no 4s. And so if they contain no 4s, these digits all have to be from 5, 6, 7, 8, 9. So both sets need to contain 6, 7, and 8. Yeah, we'll say, okay, these definitely contain 6, 7, and 8. So, okay, I don't want to mark that just yet. That looks horrible. Where did these 3 digits go in this box? That's the question to ask. So these 3 digits in this box, they can't go in any of these places, of course. They can't go there. We know one of them goes here, but the others absolutely can't go in these 2 cells. Because if either of them went in these 2 cells, that digit would be ruled off the entirety of the yellow renban, and that's not allowed. So the green digits, these 3 digits, where do they go in this box? They only have 3 options. They have to go in these 3 places. And that tells us what they are, because it means that there's a 9 on this list. So these are all from 6, 7, 8, 9. These aren't 9, of course. And this digit also is from 678, owing to the fact that, as we said, these digits go in. Did I screw that up now? I now think I screwed up this logic. What did I do? Okay, these 3 digits, where did they go in this box? They can't be there, there. They can't be there or there. No, okay, no, I think I was right. Yeah, this is still 6, 7, or 8. Because it is one of the... Yeah, that's the thing I wasn't counting. Yeah, okay. So yeah, these are 6, 7, 8. All good. Okay. Yeah, when I was thinking about it, I was forgetting about the can't repeat there. So there is my triple of cells. Yep, so all good. So now, afraid not, though, think something's wrong. Row 2, column 3. Yeah, I highlighted this group, but I meant to highlight that group. But same idea. So the whole point was that this is a 6, 7, 8 as well. So that gives us a 6, 7, 8 triple in the box, so we can fill in these digits. These digits are a 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and these are not 3. These are not 5. That one's not a 1. That one's not a 2. So we've got all kinds of stuff going on with that. Now, if this renban were split, I would need to have this be a 6, with these each being 5, 4, 3, because otherwise I'd run into problems immediately. But I don't think that quite works. 1, 2, 3, 4, 5, 6, 7. That's length 7. Let's see. It's a 2, 5 pair in row 1, columns 1 and 2. Oh, okay, I see. I think row 1's column 1 and 2 is not what Tallcat meant, but I can understand it. I need both a 2 and a 5 in row 1. But 2 and 5 can't go in any of these cells, and because 2 and 5 are in this box over here, they can't go there. That's not a 4. So in fact, this is a 2, 5 pair, means that's not a 2. Good spot, Tallcat. Because of the 2 and the 5 marked over in this box, was the whole point. So over here, we have a 1 and the other 6, 7, 8, or 9. But that's fine. Let's see. If this were split, those 2 digits would be exactly those 2 digits. That looks okay to me, I think. Let's see. So if this is not split, I'd probably have to have a 5 right here, unless it didn't have a 5. Well, that seems helpful. Okay, the 1 in this box is in one of these cells. That seems cool to notice. So probably, just by probability, probably the 1's up there. Let's see. Ben has a very clever observation, which is that this renban either is split or it isn't. If it is split, this has to be a 6 because every other cell on this renban sees 6, 7, 8, 9. But if it's not split, this was the part I didn't see. If it's not split, well, it needs to have a 6 on it somewhere. Actually, it has to be split, because if it's not split, it needs to have a 6 and a 7 on it, and it can't have both. Because these cells all see a 6, 7, 8, 9 triple. And I can't make a length 7 renban that does not have a 6 and a 7 on it. So yeah, can't be split. Can't be not split. So it is split. So this is a 6. And now these see 7, 8, 9. So these have to be 3, 4, 5, and 3, 4, 5. Thanks, Memeristor, and thanks for the puzzle. So this is split, but this just isn't doing anything, so I don't think it's worth marking. This renban is now dead. But it does give us that's a 1, and that's a 3. The 3, 4, 5 gives us that's a 2, and that's a 5. Let's see. We know what these two cells are. 2, 3, 4, 5. They are a 6. Oh, I guess they're 6 and a 7 or an 8. Oops. 7, 8. These are also, let's see, they're also known 3, 4, 5. They're also from 6, 7, 8. So where do these 3 digits go in? No, never mind. Pretend I didn't say anything. So got it. Okay, so I've got to think about ones. So the key observation here. Oh no, I don't know that there's not a 1 over here. Never mind. So I know there's a 1 somewhere over here. So this renban kind of wants to be a 1, 2. If this renban isn't 2 copies of a 1, 2 renban, then what happens is I put a 1 here and a 1 here. Oh, that does actually break it, yeah. And so I'd put a 1 in both of these places, but now that rules 1 off of an entire length 9 renban, and that's not possible. So in fact, so again, if this... So if this is split, it has a 1 on it. But what if it's not split? Well, if it's not split, then it has a 1 on it. And so it would be 1, 2, 3, 4. But it can't be 1, 2, 3, 4 because there's a 3, 4, 5 triple in both of these boxes. So yes, so this renban is a split 1, 2 renban, owing to that combination of things. That's cute. So this is a 7, 8, 9. This is a 7, 8, 9. So all good stuff. These two 7, 8, 9s have to be different, which is kind of cool. Let's see. They're not 9, right? They're a 7, 8 pair, and they're different. Okay. Good point. They're not 9 because the 9 in the box in each of these cases is over here. Good point. So that gives us a 7, 8 pair in the column. So the column has a 1, 2. It needs a 3 and a 4. It's got a 5 and a 6 and a 7 and an 8, and it needs a 9. So these are from this is a 3, 4, 9 triple over here. We've got a 1 and a 2. We've got a 3. We need a 4, a 5. We've got a 6. We've got a 7 and an 8, and we need a 9. Okay. So I only get 1, 9 on this line, and I only get 1, 4 on this line. And so the off things here are a 4, 9 pair. Oops, 3. That's right. They are a 4-9 pair. Because otherwise, if I don't put exactly a 4 and a 9 over here, then I would have 2 4s or have 2 9s on this renban, which does not work. So one of these is 8 7, and the other is some length 4 renban. As of yet to be determined. This 7 8 is over in one of these two places, because remember, these two 7 8s are different. But that doesn't immediately seem to tell me anything that I can figure out. Let's see. Tallcat has figured out that this renban is split. Couldn't it also be 989? Oh, that's a good point. I was not even thinking about the fact that, yes, 989 is a valid thing. I can split the length 3 renbans. Thank you, Garion. I don't think that messes with my logic that this is a 4-9 pair, but it definitely messes with my claim that that this would be 987. It could be 989. So what is this digit? It is not a 1, a 2. Could be a 3, a 4. It's not a 4. Could be a 5. Could be a 6, a 7, or an 8. Can't be a 9. So because this can be, and so this must be, this must have been Tallcat's argument. Because this digit can't be a 1 or a 9, and it's not going to appear anywhere on this renban has to be split. So we'll, again, split the renban. We'll split it into green and yellow, but we'll pair them the opposite way to create a prettier pattern. So now this is a length 4 renban that's looking at this digit. So never mind. Yes, the length 2 renbans cannot be split. I agree. The 1 in this column certainly isn't on here. Oh, actually, right. These don't have a 4 or a 9 on them. And so because they don't have a 4 or a 9 on them, they're forced. They're 5, 6, 7, 8. Because that's the only length 4 renban you can make without a 4 or a 9. Because these digits, those 4 digits are the same as these 4 digits. One of them looks at a 4, one of them looks at a 9. So that's beautiful. So these are exactly 5, 6, 7, 8. And so this is not 5, 6, 7, or 8. It's a 3. So let's see. I probably want to go ahead and fill in what these digits are, because I've got a 5, 6, 7, 8 quad. So these are 1, 2, not a 3, not a 4, not a 5, 6, 7, or 8, and a 9. You can go ahead and fill in that's not a 5, just for the record. So let's go ahead and fill in the column. Let's see, I need a 1. I've got a 2, 3, 4, 9. So these are 1, 4, 9. These are, hey, again, Jessica. 2, 3, 4, 5, 6, 7, 8, 9. 2, 4, 9. I know that's not a 9, because there's a 3, 4, 9 triple. Or it's not a 4 either. It just is a 2. Do I get the same joy over here? Yeah, I've got a 4, 5, 9 triple, so this isn't a 4 or a 9, it's a 1. So that's not a 1, that's not a 2. Woohoo! 950 subscribers. Probably should have advertised in Discord that in like the video discussion channel, that I was doing a live reaction to Simon's Puzzle, but I did not think of it. Let's see. Okay, so these are 4-9 pairs. Let's see. So do I want to color these? This digit is the same as that digit. Oh, you did think of it. Nice. Excellent, excellent. I don't think that's going to let me do anything. 3, 4, 5, 9. Okay, so this is a 3, 4, 5, 9 quad. So this is everything that's not 3, 4, 5, 9. So 1, 2, not 3, 4, 5, 6, 7, 8, and not 9. Hey, Chillian, thanks. It was fun to have... That's the first time it's happened that there was a Simon video of one of my puzzles on a day I was streaming. So I got to do a live reaction video to it, which was fun. Okay, so... Not quite. We're like so close to getting to a triple of some sort. But that's not quite there, I don't think, because that's from 1, 2, 5, 6, 7, 8, 9. Yep, that's from too many digits. Close, but no cigar. Let's see. Oh, this digit I suppose I should fill in as a 6, 7, or an 8. Just to finish off the box. Likewise, that's a 6, 7, or 8 to finish off the box. Oh, and not a 6, because there's definitely a 6 up here, and likewise, there's definitely a 6 down here. So, in fact, those are a 7, 8. Yes, row 6, column 6. Good point, Josh. This sees this 7, 8 pair. And remember, we know these two are different, because if they were the same, I'd have ruled that digit off the entire renban. But this pair sees this, so this is not 7 or 8. It's 1, 2, or 6. I guess I should fill in these digits. That's probably a good idea. These are a 3, 4, and 9 to finish off the box. And so we've got a 3, 4, 5, 9 quad in the row. So 3, 4, 5, 9 quad. Oh, even better, a 3, 4, 9 triple, as Tall Cat points out, is even better. So that actually places the 5. And likewise here, 3, 4, 9 triple places the 5. So these are not 5. Those aren't 5. In particular, this is also not 9. Likewise, 3, 4, 9. That's not 9. Yes. Okay. So these two triples together really beautifully, as Chili points out, they place the 3. This is not easy to see, but they place the 3 here. And that's because I know one of these 3 digits is a 3. Well, that one's not a 3. So I know one of these 2 digits is a 3. Likewise, I know one of these 3 digits is a 3, but that one's not a 3. So one of these 2 digits is a 3. So if this digit is not a 3, both of these are 3s, which would place 2 3s in a box. So that's not what's happening. That's the 3. That was a really good spot, Chili. So these are a 4, 9 pair. Let's see. Similarly, says Garion, no 7, 8 in row 1, column 6, or row 6, column 1. Right. I know I need this 7, 8 to show up over here. So I have a virtual 7, 8 pair in this row and a virtual 7, 8 pair in this column. And so these aren't 7, 8s. That is an excellent catch. I know this isn't a 5 anymore. I know that's not a 5 anymore. Well, one of these two is a 5. Let's see. Row 6, column 9. Yes, also applies there and there, because again, I know one of these is a 7/8, so that gives us a virtual 7/8 pair, and likewise in these, I know one of these two is a 7/8, so that gives us that. So yeah, so same point for those, that and that. Can't be 7 or 8 either. So they are 5 or 6. So in particular, these two are a 5-6 pair, so this cell can't be a 6. Because if these were the same, that digit would be unable to appear in this box. So these two have to be different, which means one of them's a 6, which means this digit's not a 6. Which is cool. I don't see what it does. It feels like that's the deduction that the setter wanted us to make, but I did not. I don't quite see yet what it does. Okay, so so this doesn't have a 3 or a 5 on it. Chad is pointing out, because it just sees 3s and 5s. So it can't have a 3 or a 5, which means this can't be a 4. Because if this were a 4, one of these would need to be a 3 or a 5. So this is a 9. So that's a 4. That's a 9. That's a 4. This 4, coming over down here. What? How did this break? What did I do wrong? How is this working out? There's no 3 and no 5 over here. But this cell can't be 3 or 5 either. Yeah, so we broke the puzzle. That is what happened. Somehow, because I am pretty sure there is no way that you can fix it from here. Let's see. Likewise says row 7, column 5. Oh, we can have 4, 5, 6, right? Because it's not ruled off of both of them. So okay, so I was right. This one can't be a 4. It has to be a 9. This one now has to be a 4. And so now this can't be 3 or 5. So my argument that this had to be a 9 was right, because I can't have a 3 or a 5 in either cell. This one I need a 3 or a 5, but it can go here. And in particular, it's a 3. And so that's a 2. Okay. Thank you. That all works out. Checks out. So there we go. Got all of that in. So that's not a 3 or a 4. So it's a 9. So that's a 3. So these aren't 9. These aren't 2. These aren't 9. Okay, these are from 7, 8, 9. And that one's not a 9. Just for the record. This 7, 8... No, don't listen to me. Oh, I do have a 7, 8 pair in the column, though. That I should look at. Thank you, Ben. So that's a 6. That's not a 6. So that's not a 6. Let's see. Okay, and then this is now a 5 because of the 7-8 pair. So now that's a 4 and that's a 5. That 4 looks down here at these two. Let's see. So as soon as that's a 5, that's a 6. So these aren't 6. That one's not a 5. So this yellow needs a 5. So that's a 5. Go ahead and fill that in. I know one of these two is a 6. So that's not a 6. It's a 7 or an 8. So that's a 7-8 pair for the box, which says that this is a 9, which says that this is an 8 and that's a 7. So this is split. So these aren't 7. So that is 7, because I need to have a 7 over here. And that's an 8. Okay, so doing well aside from briefly convincing myself that I'd broken the puzzle. But what else is new? Let's see, there's only one more 5 left in the grid. Let's see if we can place it. With our powers combined, I believe we can place the last 5 here, which means that this digit has to be the 4, because it has to touch a 5. So this is a 1-2 pair, so that's a 9. That 8 looks up and sees that's a 7. That's an 8. That 7 reaches over and makes that a 7, and that an 8. That makes that an 8. So these aren't 8. Not 8, not 8. 6-9 pair makes that a 7. These aren't 7. 6-9 pair makes that an 8. Let's see. So that 7 looks down and makes that an 8. That 8 looks over and makes that a 7. So this isn't a 7. This isn't an 8. That's not an 8 either. Let's see. These aren't 6 anymore, owing to that whole catastrophe. Let's see. So these aren't 8. They're a 6-7 pair. These digits are a 1. We've got a 2, got a 3. We need a 4. We've got a 5 and a 6. We need a 7. That's not a 7. But this is a 1-2-8 triple, so this is not a 1 either. It is a 4, which makes that a 3 and a 4. So that's more progress. These are not 4. Actually, there's a 1-2 pair looking over at this, so that 1-2 pair makes this a 7 and that a 1. This column now needs that to be a 4, and now I probably can figure out, okay, well, this is at least, that's a 1, that's a 2 because of that 2. So now this is not 1, 2, or 7, so it is 6. So that's a 9 and that's a 6. Let's see. So this is not 1 or 2 because of the 1-2-8 triple that appeared out of nowhere. So it's not a 1, 2, or a 6, so it is a 7. Let's see. This 4 or 9 is actually a 9, owing to that 4, so that looks up and fixes that pile of stuff. This 4 looks over and fixes that stuff. Let's see. This row, it already has an 8. So that's a 1-2 pair, so this digit becomes a right-in. 1, 2, 3, 4, 5, 6 is what this is. We've got a 7, 8, 9. So this cell's a 6. Let's fill in these 3 digits. These 3 digits are 1, 2, 3. We've got 4, 5, 6, 7, 8, and 9. Yep, so these are 1, 2, 3. That one's not a 3. That one's not a 3 either, so that one is a 3. So that's a 2. That's a 1 and a 2, and a 1, and a 2, and an 8. And a 1 and a 2, and a 1. And then we turn our eye down here. That 7 sees a 6 and a 7. That 6 sees an 8 and a 6. And then we're done. that was very fun. I enjoyed that one a lot. So in the end, this was split. This was unsplit. Very cool. Good use of given digits as well to sort of steer around how this all worked out. That one was a lot of fun. I enjoyed that. Nice and quick, but really cool logic in there. I liked a lot the knowing that you had these sort of remote pairs. And in particular, the way the remote pairs then ended up playing against this length 9 renban. Alrighty, I'm going to take a quick break, and then I will be right back with another puzzle. Alrighty, next up we have, can move that just a smidge so that you can see the totals. So we have here a combination killer sandwich sudoku by Niverio. Now, I will already say that I am terrified by the name here, because the name here is Lobster Roll, which sounds like it might be referencing Cobra Roll, which is a Jovial puzzle that involves a really complicated classic technique that I think Jovial invented. So I am hoping that that's not what's happening here, but if it is, we'll figure it out. Maybe, possibly. These killer cages just tell you the sum of the digits inside them. So that's all you have to know about these. The outside clues are sandwich clues, which are one of my favorite little clue types, which tell you the sum of the digits between the 1 and the 9. So, for example, if I made the 1 and the 9 in this row here, I would be saying the sum of these 3 digits is 9, so it could be 2, 3, 4, for example. And so there is a 1 and a 9 in every row and column, and so you can always construct a sandwich sum for them. So that is what we have to do here. So I'm going to follow my usual standard, which is to make purple cells that are definitely 1 or 9, and make green cells that I know for certain are not 1 or 9. And so in this instance, I immediately know these can't be 1 or 9 because I can't make a sum of 9 in only one total. But I could make a sum of 9 in 2 or in 3, as I showed you with 2, 3, 4, but these can never be crossed, and likewise, these can never be crossed. So we have made some amount of progress by doing that. Let's see. Oh my goodness, what is this? Says Niverio. I was just, when I pulled it up, I was a little concerned about the title being a reference to Cobra Roll or whatever, that this is going to somehow be a like really complicated advanced classic Sudoku technique. But we will see if that is what actually happens or not. So is this crust? If this were crust, this would have to also be crust. So this would be 1, 9 because of that, 6. then we'd have to have a 2 exactly here and then a 9 there, but that all seems okay. Let's see, 21. What's the minimum number of cells you can make sum to 21? 8, 7, 6. Annoyingly, it's only 3. So I know I need to have at least a 3-cell sandwich in this row, but I could make a 3-cell sandwich that's those 3 cells with these 2 as crust, or these 3 cells with these 2 as crust. And annoyingly, those don't overlap, so that doesn't tell me anything. Let's see. Should I look at the sum of these 3 cells? Because these 6 sum to 24. So these need to sum to 21. That's not super exciting. Yes. The secret of the given digit is the way that we figured this out. I am noticing these can't both be 2, 3, 4. So I know actually, I know one of these 2 is a 9, at least. So this digit I know is not a 9. Annoyingly, it could be a 1. So let's see. So Garion is saying that something goes wrong if I try and put a 1 here. So I can't put a 9 here, just to be clear, because if I put a 9 here, it would force there to be a 1 here, which would force this to be a 14, which is not going to work. So if I do put a 1 here, then what I end up doing, just to show you so that I can see what Garion is doing, that's a 1, that's a 9, that's a 2. And so Garion says you end up with 6, 7, 8 sandwich filling in row 7. Why? I'm missing something. Because, like, this would be a 9, that would be a 6. Oh, but now, right, okay, so here's the point. So you have to chase this rather far. This is farther than I'd usually look ahead, but this is cool, so I'm going to do it anyway. Because now, where are the crusts? These are the crusts, and so I'd need to make 21 and 3, which I could do, but only with 6, 7, 8. So that doesn't work. So I agree with Garion. We can prove that this cell is not a Houdigi thing. Okay. Let's see. So what if these are both 9? If these are both 9, then these would sum to 18. That would be 19. 19 and 19 is 38. That would make this a 7. Houdigi thingy is an official term. I don't see why that's a problem. You can't put a 1 in a 19 cage. Finish guy is a good point, which is that, of course, now this definitely can't be crust either. Because as soon as I put crust somewhere in this column, the 2 end up being next to each other. So that gives me that as well. So I know this cell's not a 9. So the only way for this cell to be crust, I think this is what Niverio maybe meant. The only way for this cell to be crust is if it's a 1. So can we somehow rule out the possibility that this is a 1? If this is a 1, then the 10 cage has to be 2, 3, 5. And now I need to make 13 without using 2, 3, or 5. I'd have to use 6 or 7. That still seems plausible to me. The puzzle has disjoint? Are you kidding me? Oh, no, you're not kidding. There really is. It really does say that in the rules. Have you figured out with Sven how to make it so that a rule appears at a certain amount of time into the solve? Because I swear that wasn't there before. Okay, so the puzzle has disjoint. I am now being informed. This being a 1 says this can't be a 1. So we have proven that indeed this can't be a 1 or a 9. And if it can't be a 1 or a 9, then this is not a crust. Yes, I definitely did not at any point when I was going over this notice that. Yeah, usually chat is pretty good at noticing if I completely don't read one of the rules. But I was like, oh, well, I know what these are. There's outside stuff and all these other things. I'm good. Okay. So okay. So now here's another point. One of these has to be a 9, but they can't both be a 9. So one of these is 2, 3, 4. So one of these 9s is a 2, 3, 4 because one of them has to be length 3. So there is a 2, 3, 4 either there or there for whatever reason. Now, what does that tell us? So one of these is a 9 and 2. Okay, and there's only 2 ways to make 9 and 2. Sorry, there's 3 ways, but each of them uses 1 of 2, 3, and 4. So what we have is a virtual 2, 3, 4 triple in these cells. So one of these is a 9 and 2. It uses 1 of 2, 3, 4. The other is 9 and 3. It uses 3, 2, 3. It uses 3, 2, 3, 4s, but one of them's out of the box. So 2 of them in the box. So there are no 2s, 3s, or 4s involved. Which now means that this cage is minimum 5, 6, 7, which would be 18. So therefore its exact contents are 5, 6, 8. And having exact contents 5, 6, 8 means that none of those are crust, which means that this is crust. So that's the 9. And now that these have the 5, 6, 8 here, we know that the one of these that's honest is 2, 7. So yeah, so one of these is a 2, 7, and the other is a 3, 4. So we know one of these 2 cells is a 2. So this cell's not a 2 either. So this cell, if we're keeping track, can be 3, 4, 5, 6, 7, 8, but not a 2. So don't worry about the 2. It's not a 2. Right, good point. These are a 2-9 pair. Thank you, SPQ. Because we know the digit that has to hang off is a 2 for the 3-cell one. This is really cute setting, by the way. I am impressed with this puzzle. One of those 9s will place a 1 in the cage. One of these 9s will place a 1 in the cage. That's a good point. Whichever of these is a 9 is going to put a 1 exactly either there or there. One of those 2 is a 1. Because whichever of them is a 9 is going to put another 2, 3, 4. So this digit, in fact, is always a 3 or a 4. Because it's not a 2. So we have a 9, 2, 3, 4, 1, or a 9, 2, 3, 4, 1. Those are the options. So if I have a 1 with a 3 or a 4, well, then I must have a 1 with a 4, because otherwise I can't get to enough. And so this must be a 1 and a 9, which is perfect because those are both crusty. So here we are. So now this cage is a 2, 3, 5, because the only way to make 10 without a 1 is with 2, 3, 5 in 3 digits. And so now these digits are a 2, 3, 4, 5, 6, 7, 8. Chat will look out and tell me if there's a disjoint thing I'm supposed to see, right? We'll trust chat with that responsibility. So now looking at this, what's going on with the other one? Do I know if the other one goes forwards or backwards? So could this be... So the one where this isn't a 9, it's a 2. Could this go like 9, 4, 5, 1 or something like that? Good point. Okay, so chat has realized I have put the second 9 in the upper left corner. And so I think I saw Garion point this out. So there's already a 1 there. So these cells are definitely green. Because of that. Row 7, column 7? Row 7, column 7 is also green. Poor box 9. It got neglected. Yeah, I'm trying to figure out. Okay, so one of these goes 1, 2, 7, 9. That 9 looks at a 1 and goes 2, 3, 4. I'm trying to figure out what the other one looks like. So the other one has a 2 and then a 9. And so 2 and 4 are gone in the column already. But I don't immediately see why I could not go crust 5. That seems plausible to me. Let's see. I've used 2 of my 5s in these 3 positions, but I'm allowed 1 more 5 in one of those positions. Got to look for those like hidden triple businesses. So one effect of this is I'm going to rule 2, 3 entirely out of either this cell or this cell. Because whichever of these is a 9... Oh, no, that's not how it works. Whichever of these is a 9... No, I think it is. So if this is a 9, these two are 2, 3. But in this universe... Oh, I guess these are 3, 4 in this universe. So 3 is going to get ruled out of these cells, is the point, if I do it that way. Let's see, top, middle, and top left is always used by those 3 9s. Right, because one of these two is a 9. And so I actually yeah, one of those two is a 9, and one of these two is a 9, and so that gives us a 9-9 pair, and so actually we know that if I look at a cell like this, I know it's not a 9. Good spot to totally normal cat. Now, unfortunately, knowing it's not a 9 doesn't let me turn it green. But it's not a 9. So, like, these two cells are not 9s in any of the relevant boxes. Okay, is that... Sorry, not those. Because of the 9s showing up in these. So, is the fact that these aren't 9... it's nearly forcing a 9 into the 15 cage, but not quite. The 9's certainly not going in the 9 cage, though. So one of these is a 9. Oh. I see. So, wait. Right, so... Sorry, I need to keep track of how the 9s and the 1s work here. Okay, so if this is a 9, this is a 2, 3, 4, with a 1 there and a 9 here. And so the 9 here will look backwards, and so the 9 here will rule out the possibility of the 9 going this way. Because the 9 won't be able to go here, I guess just by even sudoku, actually. And the 9 won't be able to go here. So actually, I think the point of this is this always goes the other way. I think I always get a 2-cell 9 sum that reads this direction. So one of these cells is always a 1. So the fact that one of these cells is always a 1 has to be somehow useful. Maybe. It looks useful. I mean, it sounds useful. It means one of these digits is pretty small. Oh, the point is I also get a 1 pair. So that's it. So this also uses up the 1s in the same spots. So we said we've used up the 9s in these 2 spots. We've now also used up the 1s in these 2 spots. And so these 2 spots really aren't crust, is the point. And the same is true over here and over, not over there. Same is true over here and over here. These are really not crust, I believe, is how that worked out. Because we actually showed these spots in... We've actually used the 1s and the 9s for all of them. So that is, I think, nice. Uh, Nine in box 9. I have 9's pencil marked in box 9. Do I know? Oh! Yeah, I pencil marked 9s, and then I completely ignored the 9 that we actually have in the grid. Okay, so I could have had this ages ago, because when I pencil marked what cells could be 9, I completely ignored that we actually have a 9 there. So this has been sitting here for forever, effectively. Whew, boy, that was bad. Double plus ungood. So this sees a 1 and a 9, so it's not sandwich. Now there is a 1 in this box, and so if this was a 9, this would be a 1, this would be a 9, and that would need to be a 1. That doesn't work. So now this can't be the 9. Now this has to be the 2, and that has to be the 9, if I did that correctly. So that's the 1, that's the 9. This is a 2, 3. So purple, green. This is a 3, 4. This is a 2, 7. This is purple and is a 9. These aren't green anymore. Why can't row 4, column 2 be the 1? Uh-oh. Really? Row 4, column 2. Didn't we already prove this can't be the 1? I thought we already proved that the 9 sandwich went on the outside. Oh, I guess there's 2 of them, and so this one could be on the inside? Whatever. I'll think about it again later. We still have greening there. Let's see. But anyway, the work we did with the ones, I think, was completely excessive, because we then realized the whole 9 business. So if this is a 9, this is a 1, that's a 9, and then the 5 has to go, this has to go, this has to be the 9, and that's the 5, apparently. 21 in column 7 needs a 1 in row 9. Yeah, we need a... Okay. Yeah, so these 21 clues are now awfully tight, because now the 21 clues, remember, need to be at least 3 long, so that gets greened. This 21 clue, if I don't make this a crust, now is at most 2 long. So this has to be a crust. So that's a 1. That's an 8. These are green. That gets greened. Because of that, let's see. If I put the 9 up here, my outies need to add to 14. So I guess this would be 6, 8. Okay, this is not a 1 or a 9, just because it sees both. Row 9, column 4 is green. Oh, sorry. Let's do the obvious thing. There's an 11 clue here. 11 takes at least 2 cells. So that was the low-hanging fruit. Let's see. So row 7 sandwich can't be 3 cells anymore, since you have 6 and 8 in the box. Ah, right. Good point. So yeah, if I try and make this a 3-cell sandwich, Garion sees it. If I try and make this a 3-cell sandwich, these would need to be 6, 7, 8, and they can't be, because these would need to be double 7, and that's not going to work. So that, in fact, can't be crust. Okay, that is a huge spot, Garion. So that, therefore, is a 1. And so these need to sum to 14, so they're 6 and 8. Because that's the only way to make 14. Now, exactly the same thing happens in the column, because these can't be, I can't make that a crust either. So that is the crust. These are 6 and 8. That's a 9. Let's see. Is there anywhere interesting that 9 is going to help with? Not especially, I don't think. Okay, and now the lower left. Okay, yeah, the lower left is now done. Okay, so yeah, I think people in chat were seeing this somehow else, but I have my 1 and 9 in the lower left, so these are not crust. So that is crust. That's a 9. So that's not crust. That's not crust. These aren't crust. Say 8, 6, 8. Yeah, chat somehow saw that in a not disjoint way. But whatever, it's good. Yeah, we got this 9 a while ago. Racemaster Dave might be a little bit behind. Maybe only a little, actually. I think we got this just a moment ago, actually. So I do need a 9 in this spot. This is, I think, the only place, actually, that a 9 in this spot can go by disjoint. It can't go there, and it can't go anywhere else, so I think this is a 9. Finishing this box. Column 6 needs a 9. Yep, column 6 needs a 9. It's got to go there. Good point to chat. Let's see. So, where else do we need 9s? Got almost all the 9s, but we don't quite have all of them yet. Let's see. I need a 1 in the lower middle. I guess I have 2 choices for 1 in the lower middle. But one of these 2 is the 1 in the lower middle, which means that this cell is not... this cell is not crust. Let's see. And so that places the 1, once we have that observation. That places the 1 there. And now once we've placed that, that's weird. It's very weird. But once we've placed that, now, of course, this isn't the lower middle 1. This is the lower middle 1. So that's green. These are green. That's green. So now I need a left middle 1. Oh, I guess the left middle 1... The left middle 1 is one of these 2. Oh, no, it's one of those 3, isn't it? Darn it. Okay, I don't think I can quite do that. Oh, yeah, we should probably look at this clue. What is this clue? Well, the minimum would be 2, 3, 4. So that would be 9. So we could do 2, 3, 6. In fact, it definitely has a 6 in it. Because if you just look by Sudoku, it's got a 6 in it. So I need a 6 and two things that sum to 5. So this is 2, 3, 6. That is a good observation. So these aren't 2, 3, 6, or 8. So if they're not 2, 3, 6, or 8, or 1 or 9, what are they? 2, 3, 4, 5, 6, 7, 8, 9. So these are a 4, 5, 7 triple. That one's not a 4. Actually, I don't think this can ever be a 5. If this cell was a 5, how am I making 9? Oh, I could do 2, 3, 4 maybe. Never mind. I think I was wrong. But anyway, I can fill in what these two digits are. These two digits are 2, 3. So if those two digits are 2, 3, these digits are 4, 5, 7. Let's see. Oops. Right. The point is this can't be the crust. I was looking at something more fancy than that. This can't be the crust because I can't possibly make 9. So that is a 1. So that's a 9, and that's a 1, and that's a 2, and that's a 9. If I fill it in fast enough, I'll get the puzzle done before Niverio can tell me it's wrong. So 1 over here, like that. So that's green, and that is a 9 in purple. These are a 3, 4. These are a 2, 7. So now what is happening? Okay, so now these are a 2, 3. So these are a, that's a 5. Just, it is a 5. So that's a 5. So this way, okay, so we've got that one all done. We can't put any more 3s in these spots, but that's seems to be basically done. This digit is a write-in. It is a 6. No, it's not a 6. It's an 8. How about an 8? I think it's an 8. So this is not an 8. So that being an 8 makes that a 6 and that an 8. So that 6 makes that an 8 and that a 6. Let's see. So, 2, 3 pair in column 4. Good thing to spot. So that's a 6. So, so that's now a 7. So that's a 5. Gets us some more digits floating around. Let's see. Row 7, column 1, 2. Right, this is resolved by that. So that's a 6 and that's an 8. Let's see. Probably should write in what the remaining digits in this box are. Okay, these aren't 3 or 4. These aren't 5. Let's see. These aren't 2 or 3 by the 2, 3 pair over there. Okay. And that 7 sees that 7 by disjoint, so that's not a 7, it's a 5. So these aren't 5. So this is a 2 or a 7, and it's not a 7. No, there is a 2 literally in the column. This is a 7. It's a 4. So these are not 4 or 7. These aren't 7, so that is 7. Let's see. Okay, what is this digit? This digit should be a write-in. It's not 2, 3, 4, 5, 6, 7. It's got to be an 8. So I think what it was the last time I had to do that. These digits are 3, 4, 5, 6, 7. 3, 4, 6, 7. These are not 7. These are not 6. Let's see. Quick. That's not 4 by disjoint or by regular Sudoku, I suppose. Let's see. 4, 3, 6. Okay, I don't necessarily see something more immediately. These aren't 7. I see that now. Oh, let's see. I need a middle 8, says Ben. Middle 8 has to go here because I can't put a middle 8 there. And that's the only other place. Yep, so middle 8 goes there. So that's middle 8. That's middle 6. Places the 8 in this box. There's a 2, 3, 5 triple in this column. So that means this is a 4 or a 7, but it's not a 7 because of the pair. So that's a 4, and that's a 7, and that's a 4. So that is all well and good. Let's see. See, I'm told I can look at this by disjoint. I don't quite see it. Let's see. We need a top right 6. We have a top right 6. Let's see. Yep, there's the final 8. So these two digits are a 3 and something else. 3 and a 7. Yep, 3 and 7. Box 9's 4 comes about via disjoint, I am told. I don't see it. I believe you, but I don't see it. Let's see. These digits are a 2. We've got a 3. We need a 4, 5, 6. We've got a 7 and an 8. So these are not 6 via the column. Did I not do that right? I think I did that right. 2, 4, 5, 6. So that gives us a 2, 4, 5, which would make that a 3 and that a 7 and a 3 and a 2. That doesn't feel right. Well, chat will tell me if I screwed this up horribly. That's not a 6, so the 6 in this box goes here. The 6 looks across and sees that that's not a 6, placing the 6 in the box there. Let's see. So the 2 in this column is definitely here, so that's not a 2. These digits are 2, 3, 4. We've got 2, 3, 4, 5, 6, 7, 8, 9. Yep. So that's a 4. Not a 4, not a 2 by the row. This is not a 5 by the row. Let's see. Let's see. Row 1, column 9. By disjoint. Yep, by disjoint with that cell. Thank you, Ben. So that's a 3. That's a 3. Let's try again. So these aren't 3. These digits are 2, 3, 4, 5. Sorry, 2, 3, 4, 5, 6, 7, 8, 9. So this is not a 2 or a 7 because of the row has a 2, 7 pair already. This is not a 2 because of the column having a 2 already. Let's see. Yeah, so that gives us that. There is already a 4 in that spot, so that's actually a 5. So these are not 5. Let's see. This 5 looks down. So that's a 4 and that's a 5. The 4 looks back up and sees that that's a 7. This 2, 4 pair fixes that that's a 5. Everything the light touches is Grokkel's fault. Is that the basic conclusion? Okay, so these cells, I know what they are. They're not 1, 2, 3, 4, 5, 6, 7 is what they are. So that's not a 5 either. So that is the 5. This is not 6 or 7, so it's a 5. This is not 5 or 6, so it's a 7. That's a 6. Just to go ahead and peel through that. Let's see. I already have a 7 in the center cell, so that's a 3, and a 2 and a 3, and a 7 and a 2. Let's see, that 3 gives me a 4 and a 7. That 4 gives me a 2 and a 4. The 2 gives me a 3 and a 2. The 2 and the 3 give me the 3 and the 2. That 2 makes that a 4 and that a 2 by disjoint. Makes that a 3 and that a 2. Makes that a 3 and that a 4. Is this like the lobster claw? I'm not sure we should attempt to enter Grokkel's mind state to try and dissect exactly what's going on here. I really enjoyed that one. Sandwich is one of the genres that I think doesn't show up as often. Like Sandwich and its variants. I like Sandwich and their variants, so I quite enjoyed this. And, you know, a little disjoint scanning is good for the soul every now and then. I'm going to take a quick break, and I'll be right back with more puzzles. Thank you once again, by the way, to our patrons. I really appreciate those of you who support us on Patreon. If you'd like to support us on Patreon, it's patreon.com/zetamath. Also, if you have not yet done so, I'd really appreciate if you liked the video. And I will be back shortly. welcome back. Oops. Nope. As I destroy the world. Sorry about that. No, stop moving. No. I'm not trying to move you. I'm trying to shrink me just a tiny bit. Okay. We have here a thermo puzzle by favorite of the channel, Glum Hippo, aka Philip Bloom. So there's a few different things going on here. Also, I realize I should probably pull up the English rules of this first, and then look at it, since the things are in German. And I don't want to I want to read very carefully for the part where it tells me the puzzle is disjoint this time. So normal Sudoku rules, cages contain 1 through 9. So the cages are extra regions. Thermometers increase. And additionally, one of the 2 marked diagonals satisfies the diagonal constraint. Okay, so I did know all the rules, but I just wanted to be sure. Where did I put it? There we go. Okay. So just to go over that slowly, one diagonal, and we don't know which, contains no repeated digits. These cages, the green ones and the yellow ones, they each contain exactly 1 copy of the digits 1 through 9. And along these little thermometer things, the digits have to get bigger if I start from the circle and then move along. So one consequence of that right away is that I know one of these 2 cells is a 1, because I can't put a 1 part of the way along a thermo. Likewise, I know one of these is a 1, and I know one of these is a 1, and I know one of these is a 1. I'm not sure that actually helped all that much, but it felt good to write in. Now, also, you could do the same thing with 9s. The 9s can only go on the tip of a thermo. So one of those is a 9, one of those is a 9, one of these 2 is a 9, and one of these 2 is a 9. So the 9s actually get us a little bit more leverage, because we actually know we have the 9 in this row and the 9 in this column taken up by these. Now, chat has pointed out, let's see, Gary and I believe points out, one of these 2 cells is a 1, so this cell can't be a 1. That's really clever. And so, oops. So that's not the 1. So this is the 1. And we get our first digit dance. And we're about to get another digit. Digit dance. Digit dance. So now this 1 being here tells us that's not a 1, so that is a 1. So that's not a 1, so that's a 1. And I still don't quite know about that business yet. That was really cool. I liked that a lot. Oh, and there's a similar thing with a 9. These 2 cells, the 2 9s here, see this cell, so that can't actually be a 9, so that's a 9. Yes, standard rules, except that only one diagonal is real, and we don't know which one. So that's not a 9, so that's a 9, so it's not a 9, so that's a 9. Okay, so we got progress on 1s and 9s. We've got a bunch of those placed. We strangely don't know which of these is a 1 yet, although maybe we would if I was better at things. Not sure. Let's see, are we now supposed to ask about 2s and 8s and see if there's a similar effect where the 8 now would go in one of those 2. The 8 here has to go in one of those 2. The 8 here has to go in one of those 2. And the 8 here has to go in one of those 2. None of that immediately strikes me as being as useful as any of the things that that works. Okay, so what about 2s? Our 2s could in each box go? Okay, so our 2s could go, sorry, no, our 2s could go one of these two places. I'm actually going to mark that because that's useful sudokologically. So one of those two is a 2. One of these two is a 2. That's less useful. One of these is a 2. That also seems less useful. And this box I just don't know anything about. Let's see. Box 4 becomes interesting because of the given 7. Okay, so where can 7 go? That's a reasonable thing to look at. Where can 7 go in this cage? So 7 could go there right before the 9. 7 could go here, except it can't. Or 7 could go there at the end of this. I think those are the two places that 7 can possibly go. Row 5 needs a 9. That's a good point to ask about. Where does row 5 get its 9? It can only get a 9 here. Oh, interesting. Okay, so yeah, these two cells are both the only position for 8 and the only position for 7, owing to the given 7. So this is a 7-8 pair. That's very cool. Nicely spotted, Kurban. So now where is 8 in this row? 8 in row 5 now has to go here, doesn't it? Because I can't put 8 in this box anymore. 8 here is way too early on the thermo. 8 here is way too early on the thermo. So Kurban's point at least places an 8, I believe. I guess I actually know that there's a 1 and a 9 down here because the 3 digits that live on the pyramid ends have to appear in the box that the pyramid primarily occupies. So I know there's a 1 and a 9 over here. Likewise, doing that backwards, if I look at this pyramid, I know there has to be an 8 in one of the tips of the pyramid. And there are only 2 tips of the pyramid that 8 could go in. One of these 2 cells is an 8 in this pyramid. Let's see. I know one of these 2 is a 1 for the same reason. I know one of these is a 9, although I could have probably gotten that one without going so fancy. But yeah, that's certainly getting interesting. Oops. Row 9, column 5 is only 1 or 9 by Tris logic. Because if it wasn't 1 or 9, then where would 1, 9 go in the column? They'd be there and there. I don't quite see it. 6 in left yellow has to go next to a 7-8, says Ambrose. Oh, right, because where does it go in green? That's a good way to put it. Again, these are the three tips. This one can't be that tip. So this one this one has to be a 1 or a 9. So 6 in this, to go back to Ambrose's point, 6 has to be in one of these two cells, because the 6 has to be before a 7 or an 8. So we can't put the 6 or the 7 over in these cells over here, although I'm not sure that we were keen to. Let's see. I actually know just by sudoku, maybe it's worth taking a second to do some sudoku. I know that there's a 1 in one of these two cells. And I know that there's a 1 in one of these 3 cells. That wasn't exceptionally helpful, I'm going to be honest. We don't know whether the blue diagonal is actually a diagonal. In this puzzle, only one of the diagonals is actually a diagonal, Dave. We read the rules on LMD together in English, and then we are making do with the German rules on the side. Why is row 5, column 4, 6? Not a 2. I don't think I've pencil marked that this one isn't a 2. This one can't be a 2 because if it was a 2, what would I put here? Is the problem. Because I already have a 1 and this is a region. But I have not pencil marked 2s in this region, although the 2s in this region are in one of those 2 spots, just for the record. 1 in row 2 is an interesting question. Okay, so 1 in row 2 is not here, it's not there, or any of those places, or there. Ah, yes, gorgeous. Okay, 1 in row 2, good spot. So 1 in row 2 is there. So if blue is the good diagonal, the 1 has to go exactly here, because a 1 here would rule 1 entirely out of this green region. So if the blue diagonal is the good diagonal, that's the 1. I don't know if we have anything similar going on. Oh, we have a similar problem with 9s. If the blue diagonal is the good diagonal, also that's a 9. Because, again, I couldn't put it anywhere else. But unconditionally, I do know one of these two is a 9. Nine in box 9 is on one of these two cells. I'm not seeing the is placed. Because of box 8. Yes, got it. Because we know the 1 and the 9 are down there. So no 9 here, so 9 here. Thank you, Tall Cat. And yes, welcome, Loretta. Good to see new names poking up around. So yeah, the now with all of these pencil marks, now where the 9 goes in box 5, as Garion points out, tells us which is the real diagonal. Should I start good lifting these thermos? I'm seeing like this bulb. What is the biggest it could be? I think the biggest it could be is 4 if these were a 2 and a 3. So I think this is at most 4. Yeah, we looked at the 2s and 8s previously. I know one of these two is an 8. I know one of these two is an 8. One of those two, these are already marked. And one of these two is an 8. So let's see. Is there something to be gained from that? So this cell is not an 8. That's one thing I can gain from that. But I think the others could be. Let's see. And then let's look at 2s. So 2s in this box actually are quite open. 2s over here are in only one of those two. 2s here are in one of those two. And here are in one of those two. Does that speak to anyone? Let's see, if row 8, column 4 is an 8, where do you put 7 in green? Oh, that's a good question. Okay, I probably should be paying more attention to this given 7 than I am. If I put the 8 there, then the 7 needs to go nowhere, basically. So this can't be the 8. So that means that is the 8. So that's a 7 and that's an 8. That's a really good spot. So these are a 1, 8, 9. Triple. That 8 went over there. Okay, so this 8 is going one of those two places. I don't think I learned anything more about that just yet. This 8 up here is now, still going one of those two places. I think we run into the same problem, though. If I put this 8 here, no, I don't. If I put this 8 here, I put the 7 over there. If I put this 8 over here, I put the 7. Yeah, so the 7 I don't think puts quite as much pressure there. Now do the 7 in box 6. Oh, yes, I cannot actually put a 7 here because there's a 7 in the column. Good point. So, yes. So where am I putting 7 and 8 in this box, keeping in mind that this can be neither a 7 nor an 8? So this could be a 7, 8, but that means this cell's always a 7 or an 8, and it can't be a 7, so this cell is always an 8, I believe. So again, where can I put 7, 8 inside this box? Well, those cells are out immediately, the things in the plus sign. So I could put them both here, or I could put one here and one here. Those are my options. But in all events, I put one here, and that one has to be the 8. So this is an 8. One of these two cells is an 8. So now one of these two cells is a 7. Just continuing down the chain. Get 8 in row 8. Okay, so not there, not any of these places, not there or there. Good point. The 8s are marked vertically in this pyramid, so that's an 8. Yes. What is this cell? Well, it's not an 8. This is a beautiful spot by Kurban. Remember, these 3 cells are these 3 cells. Well, this cell is not that cell. But it's also not an 8. So this cell can only actually be a 9. That's really clever, Kurban. So these are 8s. Or sorry, one of those two is an 8. I don't know which one. That's a 9, which looks down to make that a 1. Make these not 1s. That 1 now looks back up, means that's not a 1, means that is a 1. Means that's not a 1, means that is a 1. So that is golden. Okay, so the 1... So do we have all our 1s now? Not quite. We have a little X-wing of 1s left. What about 9s? We have a little X-wing of 9s left. Okay. So, so let's see. So chat is saying now yellow can't be the real diagonal, because if yellow is the real diagonal, then 1 and 9 both need to go in these 2 cells. But this one can't be 1 or 9, so 1 and 9 both have to go here, and that's going to be a problem. Okay, right. So yellow is not the real diagonal, so blue is the true diagonal. Well spotted to Tall Cat and chat. We're going to make this blue just to emphasize it's the real diagonal. And so now that it is the real diagonal, I want to ask where 9 goes on it. 9 goes here on this diagonal is the answer. So that's an 8 and that's a 9. So now, is that all of our 9s now? I think that's now all of our 9s. So where does 1 go on this diagonal? It has to go here now. So that's a 1 and that's a 1. So these remaining digits are a 2, a 3. I guess there's a lot of remaining digits. I don't know that I want to write them all out super quickly. It seems like a lot, but that probably got us more. So now 8, yes, it did, because now 8 on the blue diagonal has to be up here. It's not there or there. So 8 on the blue diagonal now has to go here. So that's not the 8. So that is the 8. So now have we finished our 8s? Now we have finished almost our 8s. We didn't get that one. Let's see. Where is the 7 now in the right pyramid? I'm being asked. There or there? Oh, no, it can't be there because there's a 7 across. Yeah. So 7 in the right pyramid now has to go here. Good catch. Which actually tells me that this cell's a 7. Okay. So seven in column 9 has 2 places, I believe. This is not a real diagonal. It serves no rule significance. We will try to remind ourselves before we accidentally use it. Let's see. So this cell is repeated there. Oh, I guess so this cell goes in one of those two. That's not super useful. Let's see. I have an X-wing on 7s. So I'm looking at the 7s in... Let's see. Your claim is row 8, column 4, which I randomly have selected. Let's see. I don't see this. Right. Okay, sorry. Yeah, the diagonal is saying none of these are 7, which I was not appreciating. Yes, none of these cells are 7, so the 7 is in one of those places. Likewise, the 7 is not here or here, so the 7 is in one of those, and so the 7's align. That was a really good spot. The 7's align, and so the 7 in this box just gets placed here, which then places the 7 up there. I was just missing the diagonal piece is the thing I did not see. So we're now back in the place where one of these two, sorry, no, not one of those. It's that one, or it's one of these two is a 6. If we want to continue down the chain. One of these is a 2, for whatever that's worth. 1, 8, 9. Let's see. Does feel like 6 is a reasonable... I suppose I should fill in this digit's a 2, 3, or 4. What are the candidates for this digit? It's not a 2. It could be a 3, a 4, or a 5, I believe, if I write this in correctly. Because I could hide the 3 and the 4 over here and make this as high as 5. No. Yeah, I could hide the 2, 3, and 4 over here and make this as high as 5. So this cell's also 3, 4, 5. So this cell, what can it be? Well, I can hide the 2 here, but then this would be a 3, or it's a 2. So this is always a 2 or a 3, actually. So these are all from 2, 3, 4, 5. So we need a 6 somewhere. The 6 has to go in one of these two cells. Do I know which one? I don't think I do yet. Let's see. Let's see. So Ambrose is giving me this long chain. Row 6, column 9. Row 5, column 6. I'm assuming that one. Row 4, column 3. These are all the same digit. Yes, I agree. So this is, I could mark this as being 3, 4, 5. Yeah, and this digit goes over there. I should mark that that's a 2 or a 3. And so then that digit also goes here, so that's a 2 or a 3. Ben says, so it's not a 3. I don't understand. Via the thermo and box 5. Sees row 4, column 5. It is row 4, column 5. Row 4, column 3. Yeah, this can't be a 3. I agree this is definitely not a 3 because it would make both of these digits 2. And I can't have that many 2s. That's too many 2s. So this digit is, it's that digit, right? These two digits were the same. And then that got placed there. So these aren't 3 either. Okay. Thumbs up. Agree with that now that I know what we're talking about. So that is a 4 or a 5. So now I need to bury... Yeah, I still need to bury the 2, and I need to bury the 3 along these. So one of these 3 is a 3. For whatever that is worth. Okay. If row 5, column 6 is a 3. Oh, yeah, we went over that one. I'm trying to only pencil mark the 6s and 2s when they are immediately useful. Like, I can pencil mark these now because they're in a column. Otherwise, I just highlight them to look at them. So, like, one of these 2 is a 2. One of these 2 is a 2. Interesting. Yeah, one of those 2 is a 2. And then 6s, one of these 2 is a 6. One of those 2 is a 6. That's a 6, or that's a 6. One of these 2 is a 6. One of those 2 is a 6. Row 4, column 5 is in right yellow. Oh, sorry, you're just saying find this cell. Yeah, this cell has to go here. Whatever it is, it goes here just by Sudoku because it's a 2 or a 3, and 2 and 3 can only live in these spaces. So now this cell, that cell, now they have to go into this yellow. So they end up here. So this is a 2 or a 3 as well. Very nice spot, J. Let's see, I'm going to give that a color. Although the very colorful original board has made that difficult. I don't think I can erase this color. Can I? No, I can't. Let's see, and I guess the other cell we keep chasing is this one. I'll make that horrible red. Burnt rust is sort of like what it looks like on top of the yellow. So I suppose I can fill in. I know this cell is 2, 3, 4. And I know this cell is 5 or 6. Yeah, I mean, I'd love it if this color were added as a color to the solver. I think I would use it. So that means one of these 2 cells is a 6. For whatever that's worth. So either that's a 6 or that's a 6. Yeah, we know this is purple. We just didn't ever color it. I only relented that I was going to color on top of the coloring after a long period of resistance. So that is why we did not do it initially. So purple only goes in 2 places on the diagonal while we're talking about purple. Purple only goes there or there. So purple is never here, for whatever that's worth. Oh, so purple's never here, and so therefore purple is placed in row 2. That's ridiculous. So look at purple and look at purple on this diagonal. It only goes in these 2 cells. So now where does purple go in row 2? Well, it could go there. It can't go anywhere in green. It can't go here because there's a purple in the column, and it can't go here because it would rule it off of the diagonal. So in fact, this actually is purple. So that's 2 or 3. That's purple. I think I'm going to de-blue the diagonal. I think it's distracting me, although I now worry that I will forget which diagonal is real, but we'll try to remember. So anyway, that's a purple 2, 3. So yeah, one of those 2 is a purple 2, 3. Purple 2, 3 is down in one of those 2 cells. Where is purple 2, 3 in row 8 now? Purple 2, 3 in row 8 now only goes here without any further shenaniganery. So now purple in box 7 now needs to go in one of these 2 places, but it can't repeat on the diagonal, so it goes there. And so now the last purple 2, 3 goes here. So now I know that rust on the blue diagonal needs to go in one of these 2 places. Therefore rust in row... oh, no, I don't know that. Sorry, I don't know that rust goes in... I don't know that rust doesn't go in here, is my problem. I do know that rust in row 7 doesn't go in either of these 2 cells, but that's fine. 6 can only go in one place in box 1. Let's see. Okay, so no 6s over there. Okay. I think I'm going to need help as to why 6 can't go in one of these places. Do keep in mind this diagonal doesn't do anything. Let's look for rust in row 3. It's there or there or there. Oh, by looking at box 8. Okay, so yes, got it. Okay, so rust not here, because rust is in one of those 2. Row 3, sorry. Well, it is true that rust is in one of these 2. And so now when I look at row 3, which is the actual row we're supposed to be talking about, rust is not here. Rust is not here because of that, and rust is not here, so rust is here. Okay, so we will make this rust. 4, 5. If you color the fake diagonal yellow, it'll hide the line. That's an oddly clever idea. It's very tempting. I don't think I've ever deliberately colored something to make it show up less, but it's a good idea. One of these 2 is rust, so one of these 2 is rust. do I want to start coloring this digit? I think I probably do, right? Is there any chance that this digit goes here? I don't know. I'm not sure that I know the answer to that question, actually. I know these two are the same digit. I can, I suppose, make them... I guess that kind of shows up. It's not great. Row 7, column 7 needs to be red because you need it on the blue diagonal in box 7. Yeah, we know that... right, okay, so... But why is it that neither of these are red? Or sorry, why is it that's not red? So, yeah, red in this box is in one of these two cells, which I guess it could theoretically be in either. I think. Sixes might be colorable a lot of in only two places. Yeah, we keep selecting the sixes now and then. So, like, those are sixes, those are sixes. Let's see. Those are sixes. The sixes in this one are in one of those two. Let's see. Row 3, sixes. Row 8, sixes. Yeah, the row 8 sixes are in one of these two places. I believe they're there or there. Row 6, column 7 is 5 or 6, says Loretta. Let me convince myself that I believe this. How do I know this is 5 or 6? Sorry, row 6, column 7. This one. Sorry, this one. Yes. This is 5 or 6. Okay, thank you. Thank you. Row 6. I've been doing better about the reading things lately, but not so much today. Okay, so this is 5 or 6. And so, yes, so this cell places itself in box 5 here because it can't be rust. So these two are the same. We'll do further horrible coloring. Just to try to keep track of that mess. Okay, so now... yeah, that doesn't quite get us this in these places, but it's close, maybe? Let's see. Do we have all the 7s? We don't quite have all the 7s, I suppose. Yeah, I've got 7 here or here, 7 here or here, and 7 here or here. Okay, so now Jay asks, where does row 3, column 5 go in other green and box 5? So this digit is a 3 or a 4. In other green, because it's not purple, in other green it goes over here. So in box 5, it has to go here. So therefore, this is green, is what we're saying. And this being green tells us that this green is not 2. It's 3 or 4. Good spot. Good spot. So yeah, and it's up here somewhere. Green in column 3. Green in column 3 is an excellent deduction. So green in column 3 now goes here. There's a 3 or a 4. Now Tony asks, where is 2 in column 4? So 2 can't possibly be here. So the only place for a 2 is here, making purple 2. So all of those 2s go in at once. So this is not a 2. Great observation. Let's see, rust is in one of these 2 cells. Green in row 2. Green in row 2 has to go here. Just because green can't repeat in green and everything else can't go there. So now green in this pyramid has to go here. Green... green in column 9 because of the diagonal. Really slick. Okay. That was a team effort in chat to see. So green in column 9 can only go here because it can't repeat on the blue diagonal, which remember is the real diagonal if you're just joining us. So that's green. So now, let's see. So we've got almost all the greens now, but we do still need one of these to be green and one of these to be green. Rust in box 3 now. Okay, so rust in box 3 is in one of these 2 cells. I don't know which, but now whereas rust in row 2 can only go here. So now rust does need to show up on the diagonal. It can only do so here. So this is rust. Rust now needs to show up in this pyramid. In this pyramid. And so rust in this pyramid now can only go here. So that's not a 6. That is rust. So that is a 6. If I have done this correctly. So now... Yeah, okay, so now what does that do? So now that makes yellow 6, because now where does 6 go in box 5? It now goes here, so those are 6, so this should be yellow. Now where does 6 go in this box? It has to go here now. And now that I've written in that 6, now I can just write in the rest of the box, because now everything else in the box, in this pyramid, needs to just go in order. 3, 4, 5. So rust was 4. Green was 3. So now... Oh, I still don't know if this is green or not. Oh, I still have a digit in here. It's a 5. Let's see. I guess I know this is a... Oh, that 4 looks over and says this is a 3. Okay, so this is green. At the end of the day. So this is the green 3 up here at last from that green 3. This is whatever digit is missing. 1, 2, 3, 4. This is a 5. And I think 5's just ended up without a color. So now... yeah, so box 5 can get finished. 1, 2, 3, 4. It needs the 5. So the 5s have been the problem the whole time because we never knew anything about 5s. But now we know occasional things about 5s. Let's see. This row needs a 5 and a 7. I don't think I know which of these. Oh, no, I do. No, I don't think I do. We'll just put 5, 7 there. Column 8, we know what's left. We need a 4. Oh, the 4 has to go here and is rust. And this digit is 2, 3, 4, 5. This digit's a 6. 6s were also pretty horrible to us, this puzzle, but we do award them yellow status to at least show that they're better than 5s. So this cell can't be a 6 because I need a 6 on the diagonal. It's got to go in one of these two cells. So actually, let's write down. What are these? We've got a 2, 3, 4. These are a 5, 6 pair. These are neither 5. So this cell is neither 5 nor 6. So 1, 2, 3, 4, 5, 6. It is a 7 is the answer. It is a 7, which makes that a 5, which makes that a 6, which makes that a 5. We remember that 6 becomes yellow. So now this diagonal, 1, 2, 3, 4, 5, 6. This is a 7. Sorry, it's a 7. 1, 2, 3, 4, 5 to finish this. That's a 7. Let's see. 1, 2, 3. Okay, this column needs its rusty 4. 1, 2, 3, 4, 5. This is a 6, which gets awarded yellow, mostly to make the 5s jealous. 1, 2, 3, 4, 5 in this row goes here. Let's see, this box, 2, 3, 4, 5. This box needs a 6, so that's a 5. 6 gets to be yellow. 6 gets to be yellow again, as that becomes a 6. That was a really intricate puzzle, but very cool. I enjoyed the sort of the journey through that, through the grid. And through the, like, at first I really thought that coloring was going to be excessive, that we weren't going to need it because sort of things seemed to work out. But then eventually, once we started coloring stuff, it all sort of went along pretty smoothly. So I think that worked very well. Another great Glum Hippo puzzle for the stream. Alrighty, I'm going to go take a real quick break and fetch us up another puzzle, and I'll be right back. Alrighty, welcome back to a puzzle that I have... This is another puzzle that's been in the bucket forever, and I always sort of have had it left aside, and then at the end of stream, I'm like one puzzle short of getting to it, so we're going to do it now. This is Keys to the Kingdom by Jeremy Dover. Normal Sudoku rules apply. German Whisper rules apply, so we haven't done a German Whispers puzzle today somehow. So if you're on a green line, any digits that you put next to each other have to be at least 5 apart. So I could put, say, a 2 here and a 3 here. I mean, aside from the fact that I can't put a 3 there, but, whatever. So I have to alternate along, making sure to always bounce at least 5 back and forth. That's how green lines work. They're called German whispers lines. And then the purple lines that are not really renban purple, they're a different kind of purple. These are keypad king rules. Consecutive digits along indigo, they're called indigo lines, must be a king's move apart on a telephone keypad. So if you look at your keypad in front of you, you'll see that, for example, I could go from a 6 to an 8, that would be fine, but I could not go from a 6 to a 7. They would not be a king's move apart on the line. So this is rather cute. So 5s are the best digit on an indigo line, and the worst digit on a green line. I mean, in that 5s literally can't be on a green line at all. Alrighty, so that's the rule set. So we get to figure out where to start, question mark. We do have a lot of given digits. Let's see, so the 7s need to go, so the 7's definitely on one of these indigo lines. If the 7 goes at the top up here, does that do something? So here's an interesting point. 7's only actually adjacent to 3 digits. So if I were to put a 7 here, these would need to be, the 3 digits a 7 is adjacent to are 4, 5, and 8. So if I put a 7 here, I break the whisper line, actually, because I can't put, 5's already in the box, actually, even. So actually the 7 needs to go in one of these places in order to not break that. So one of these is a 4 or an 8. Now the fact that these are 7 means that both of these are high, means that this is low. This has to be a 1 or a 2. If this were a 1 is only next to a 2, 4, and 5. So if this were a 1, these would have to be a 2, 4 pair. Seems like maybe that's possible. I can go ahead and fill in. These are 6, 7, 8, 9. This is a 1 or a 2. Okay, so I know there are 2 low digits and 2 high digits on this. So that's 3 highs for the column and 3 lows for the column. So these are a high-low pair, unfortunately. Let's see. So if one of these was a 9, 9 only connects to 5, 6, and 8. So I'd have to put a 6 or an 8 there, but that seems fine. Okay, so the high digits on this. So I need 2 high digits on this whisper. They can't be a 6 or a 7. So there are an 8 and a 9 on this whisper line. Not the biggest deduction, but it's true. There need to be an 8 and a 9 on here. Somewhere. Yeah. King's move on the keypad. Okay, so these are not 7, 8, or 9. So these are 1, 2, 3, 4. Oops. These are 1, 2, 3, 4, 5, 6. That one's not a 5. These two aren't 3. I know I can't put a 4 on the whisper line either, so the 4 and the 6 both live off the line in these cells for whatever that's worth. Not a lot, I'm afraid. Let's see. Garion says this cell can't be a 1, which would be huge, because that forces these to be 2, 4. And so now this would have to be a 3, with these being 8 and 9. Except that... sorry, so these would be 2 and 4. Okay, so if this is a 1, 1 is only adjacent to 2, 4, and 5. So if this is a 1, these are a 2 and a 4. Now I need a low digit on here, so the 3 would have to go here. So these would need to be an 8 and a 9, except one of these being a 9 is a problem because 9 is adjacent to neither 2 nor 4. So that does not work. So that's actually very, very clever. This can't be a 1, so it has to be a 2, which means that there can't be a 6 involved in any fashion. 2 is adjacent, if I look at my keypad, to the digits 1, 3, 4, and 6. There's no 2 over here. Okay. One and 3 don't connect to 7, 8, and 9. That is a good point. So these can't be 1 or 3. These are actually a 4, 6 pair. Beautiful. Okay, so these are a 4, 6 pair. Very cool. So now that means this is not a 4 or a 6. Sorry, this is not a 4 or a 6. This is a 1, 2, 3. And now I need 2 of 1, 2, 3 on this line, so I can't have any more 1, 2, 3s that aren't on the line. So these are a 4, 5, 6 triple now to make that work. So that's interesting. Because these not being able to be 4, 5, 6 is going to mean that these are going to have to be either 7, 8, 9 or 1, 2, 3 because I can't cross the middle line. And they can't be 1, 2, 3 because of this 1, 2, 3. So these have to be 7, 8, 9. Right? Because they can't be 4, 5, 6. So I have to stay away. I can't go from the top of the keyboard to the bottom. So these are 7, 8, 9, which means these are 1, 2, 3. So 7, 8, 9 only connect to 4, 5, 6. So these are all 4, 5, 6 numbers. That gives me a 4, 5, 6 triple in the numerator. Sorry, in the top row. So this is, by the way, these are 8, 9. Yeah, these are 8, 9 because they can't be a 7. Okay, so that's my 7, 8, 9 and my 4, 5, 6. So these are a 1, 3 pair. So these are a 2, which has to go there, and a 4, 5, or 6. Oh yeah, I could probably think about this more and realize that this digit needs to connect to both of those, so it can't be a 7 or a 9. This digit has to be an 8. Good point, Carl. So these aren't 8. 2 only can... Oh, I guess 2 connects to a fair number of things. Sorry, I thought 2 was more restricted. That's a 4, 5, 6 triple. So no 4s, 5s, or 6s. No 2s. Let's see. We've used... So yeah, so we need a 1 and a 3 in this box. The 1 and the 3 have to go here. So this digit needs to be an 8 or a 9. Is the punchline of all of that. Where else am I putting 1 and 3 in this box? Yeah, whisper stuff. Okay. So, it's very interesting. So I'm going to fill in candidates for these just because I have absolutely no instinct for these. So these are 1, 4, 5, 6, 3. I was positive I would be able to eliminate one of those, but I actually don't know that I can eliminate one of these. That is a lot of candidates. Okay, well that was horrible. If this cell is high, it's a 9. Otherwise, it's low. Okay, so let me just quickly high-low color this. So if these are high, these are low, or vice versa. This is just high-low coloring, but I don't know the whole thing. But the reason why I was interested in that is that this is a high digit or a low digit that connects to the other kind of digit, which requires a lot of perspicacity, if you will, in order to make happen. Because like 7, 8, 9 can only plausibly be adjacent to... in fact, this digit can never be a 9 or a 1 because 9 and 1 aren't adjacent on the keyboard to a number of the opposite high-lowity. So, so these are not 1 or 9, for whatever it's worth. I don't know that that's immediately like jumping off the world useful, but it's true. They are not 1 or 9. Something. I'm sure it tells us something that will become clear in time. I know one of these digits is a 2, just by sudoku. Yes, okay. I did this count before, and then I got confused, but Carl has brought my attention back to it. Count the highs in column 5. There are 4 of them already. So this must be low, and so it is 1, 3, or 4. Now, if it were 1, it would force the highs on this to be... Sorry, it would force the lows on this whisper line to be 3 and 4, and that doesn't work, I don't think. It would have to go 4, 9, 3, 8, and then that would break this 8 or 9, so that does not work. So this is not a 1. In fact, actually, what happens if there's a 4 on here at all? If there's a 4 on here at all, it would go 4, 9, 6. Right. There's definitely a 6 on this line, so there's definitely a 1 on this line, but there can't be both a 6 and a 4 on this line, I don't think. Because if there were both a 6 and a 4, it would have to be... They were opposites, and then this would have to be a 1-9 pair. Maybe that's okay? Anyway, there's definitely a 6 on this line on one of the ends, so there's definitely a 1 in one of these two cells. I'll at least go that far. One of these two cells is a 1. And so whichever one is a 1 means digits on the side are from 2, 4, 5. What's wrong with 6, 1, 9, 4? I feel like you can absolutely have 4, 6, and 1, 9 on a whisper line. I wanted to not be able to, but I think you can. Unfortunately. But I think chat has the key thing, which is that this can't be a 3 because 3 doesn't connect to enough keyboard numbers. This cell connects to 4 keyboard numbers, and 3 is in a corner, so it only connects to 3. So this is a 4 for keyboardy reasons. So this is a 4. So 4 connects to, and so let's fill in the digits that 4 connects to. 1, 2, 7, 8, and 5. That one's not a 5. In fact, none of these are 7, because there's a 7 in the box. So that actually gives us that actually gives us a quad, so we can actually fill in the rest of this. So these are a 3, a 5. I know where the 5 is. No, sorry, not a 5. There's a 5 over there, a 6, 7, 8, and a 9. These are a 3, 6, and 9. Is the moral of the story. Okay, 3, 6, 9 connecting to 1, 2, 5, 8. It's not immediately clear to me. Let's see. Let's look at this. Could this be a 1? Would need to connect to 4 and 2. That looks reasonable. Trying to look at this whisper line. I'm of course like naturally inclined to focus as much as I can on the whisper lines because the whisper lines are the things I have experience with. Let's see. Ben says can't be 2 in row 9, column 4. If this were a 2... Oh, but then this message has been retracted, so I am going to assume that that is... that means I should not look at it. Okay. 9. If this was a 9, 9 only connects with 5, 6, and 8. So if this was a 9, this could be 5 and 8. That's not 5 or 8. That's not exciting, I don't think. If yellow is high, then these two are a 7-8 pair. And so what does this 7 or 8 connect to? That's low, says SBQ. So if yellow is high, this is a 7 or 8. The only number it connects to by keypad is 4. Which then makes this a 9. It doesn't work. So in fact, actually, I think before I basically proved without realizing it that this is 1 or 9, because my argument was, what is this cell going to be that connects to something low? It's going to be either a 7-8 connecting to a 4, or it's going to be a 2-3 connecting to a 6. So this cell's always 4 or 6, just because of the way the connectedness works. So this is 1 or 9. I did not write this down before, but I should have written it down before. But the point is now that there's a 9 over here, so I actually know that this is a 1, and that's a 6. 1 is low, so that could still be 2. Let's see. So, so now this is something that connects to 6, but is low. So it's a 2 or a 3, and it's not a 3. Wait, what? I screwed this up somehow. 6 connects to... Six connects to only 2 and 3, and it can't be 2 or 3. What did I screw? Okay, I screwed this up somehow. Okay, so what did I do? It's definitely not a 2. Can't row 7, column 7 itself be 4 or 6. Ah, that's probably what's happening. Yes, so I think my argument before was actually only showing one of these has to be 4, 6. That's the problem. One of these has to be 4, 6 because 4 and 6 are the only way I can connect a high and a low. But I don't actually know it has to be this one that's 4 or 6. It could be this one that's 4 or 6. So one of these is 4 or 6. The other is 1 or 9. So these are 4, 6, or 1, 9. This one's not 6. This one's not 4. So my two possibilities are that this is a 6 and that's a 1, or that this is a 4 and that's a 9. Those are my two universes. So yellow is still low. It just is a question of which way around this goes. So this is not 2 or 3, and it's not 4. So this has to be 1. That's the upshot. Because of the placement of the 2, because of the placement of the 2 and the fact that yellow is low, this is not 2 or 3, and it can't be 4 because of the whispers. So this is the 1, and that's the 4, and that's the 9. Sorry. That's the 6. That's the 4. That's the 9. I think I did it correctly that time. I think I did this right now. Let me know if I've screwed it up. It's very possible. So wait, no, that's not right. Yep, J is right. Okay, let's think about this box again, because I cannot, for the life of me, think about this box correctly. These aren't the ones that are these aren't the ones that are connecting with the 4 or 6. It is true. One of these has to be 4 or 6. Yeah, one of these has to be 4 or 6, but they can't both be 4 or 6. Oh boy, okay. But one of these has to be 4 or 6, because that's the only way I'm keyboard connecting a high and a low. So one of these is 4 or 6. So either this is 4. Maybe I was right. Either this is 4 or this is 6. Can't go the other way around. Now, as soon as this is 4... So, yeah, so these are two universes. This is 4 or this is 6. That's where I screwed it up. If this is 4, then it's not this that's 9, it's this that's 9. So if this is 4, this is 9. If this is 6, this is 1. So in either universe, the point is yellow is low. And so what number is this, given that yellow is low, and this is not a 2 or a 3, and it can't be a 4? So this now is actually, it is actually 1. So that's what's going on. Okay, so I got that 1. I think that 1 I really believe now. I don't think that immediately tells me that this has to be a 6, though. I think it could still be that this is a 4. These are high. Oh, right. It places a 4 not through keypad logic, but through whisper logic, because this needs to be low, and it's not a 1, 2, or 3. So that is a 4. That is a 9. This is not a 6 because it has to see a 4, which means it has to be a 1, 2, 5, 7, or 8, most of which it can't possibly be because it has to be high. So it's not 1, 2, or 5. This has to be 7 or 8. Now, this has to be 2 or 3. This has to be 7 or 8. This 8 looks down here and sees that that's a 7 and that's an 8. Good catch. That 1 looks up, sees that's a 3, that's a 1. I don't think I need my coloring here. I think it's probably a distraction. Okay, so that's a 1, that's a 3. Let's see. This is not a 1 or a 3 anymore. This is a 4, 5, or 6. Okay, 8 is placed in box 8, I am being told. So these aren't 8. So this is a 1 or a 2 only. And so once this is a 1 or a 2 only, neither of those connect to 8. So that's not 8. So this is 8. Excellent spot to bend there. So that's 8. So this is not 8. We know there's an 8 in one of these 2 cells. There's an 8, 9 pair looking down here. So this is not 8. So now what sees both 4 and 8? The answer is not 1 or 2. The answer is 5. So that's a 5. So this is not a 5. It's a 1 or a 2. Okay, so this will now work either way. But now once this is a 1 or a 2, by whisper logic, this is not a 3. So 5 does indeed... 5 sees literally everything, so the 5 is literally meaningless. These digits are a 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, these are 1, 2, 3, and 6. But there's definitely a 6. I can't put the 1 in the middle for sure, because if I put a 1 in the middle, it only connects to 2 of those. But I think 2, 3, and 6 all would work here in the middle. This is a whisper, not a keyboard connection, Josh. So now box 2. Box 2. Got it. This 1, 2 here sees that that's a 3. So that's a 1. So now the 1 connects to 4 but not to 6. So that's a 4. So that's a 6. Now the 4 keyboard connects to 2 and to 7, but not to 9. So that's a 7 and that's a 9. Sorry. So that's a 7. I don't know if that's a 9 yet. It's not a 7, though. 6 connects to 8 or 9. So yeah, I think this 8, 9 is unresolved. But that's a bunch more damage that got done to the arrangement. Let's see. Andrew W., not sure if you're the same Andrew W. with a different color or a different Andrew W., says this can't actually be a 3. Right. This can't be a 3 because it connects to 4 different things, and 3 doesn't connect to 4 different things. So this is only a 2 or a 6. You might have been the one who recommended this to me. This 3 sees that that's not a 3, for the record. Could this actually be a 6? Because 6 only connects to 5, 8, 9, and 2, 3. So these could be neither 8 nor 9. So if this were a 6, these would have to be from 5 to 3. It's maybe okay. If this is a 2, like, it works a lot better if this is a 2, but I don't think it breaks immediately if this is a 6, although it really tries to. Oh, no, it does break if this is a 6, because if this is a 6, I can't put 8, 9 anywhere on these. And so if this is a 6, because of this 8, 9 pair, there are only 3 digits to pull from these, so this does not work. So this really is a 2. I wasn't crazy in that particular instance. So this is a 2, that's a 1. These are not 1 or 2, they are 3 and 6. So 2 connects to also 1, 4, and 5. So these are from 1, 4, and 5. That one's the 5 because it sees a 1 and a 4. This is a 1 or a 4. 1 or a 4. Try again. That's a 2. The invisible 3 does look down. The 6 places itself up here. That's not a 2. Let's see. The 2 looks over here and makes that a 3, which makes that a 2. So this isn't a 3 anymore. Yeah, 5 is adjacent to everything, so that's not telling me anything. These 2 digits, I know what they are. Seven and 8, I believe, for the row, and the 8 and 7 work themselves out with the given. So these digits are a. Let's do these 2 first. 3, 4. We need a 5, and I don't know where it goes, and a 6, and I don't know where it goes. Well, these are a 5 and a 6, for whatever it's worth. These digits are a 1. We've got a 2, 3, 4, 5, 6, 7, 8, and a 9. Or 1, 4, or 9. This one's not a 4 because of the 4, 5 pair looking down at it, at the very least. So that is something. So what are these digits then? We need a 1 and a 2. We've got a 3, a 4, and a 5, and a 6, and a 7, and then we need an 8 or a 9. That one's not a 2, actually. If this digit is low, it can't be 1, 2, or 3. So it can only be 4 if it's low. So this can't be an 8. That will not work. Column 4 has a 6 already. Column 4 has a 6 already. Good point. So that's a 9. So these aren't 9. Thank you. That 9 looks back up here and says that's an 8. That's a 9. This 9 on the keyboard only connects to a few things. It only connects to 5, 6, and 8. And this is not a 6 because of the column. So this is a... Oh, it's not an 8 either. So this is a 5. Okay, so it's a 5 followed by us learning nothing. Let's see. These 2 digits now are a 2, 3... Need a 4. We've got a 5, and a 6, and a 7 we need, and then we've got an 8 and 9. So these are 4 and 7 in some order. So, yeah, 4 would go with 9, 7 would go with 1 or 2. Okay, so the whisper doesn't give us any more. If this was a 7, then this would have to be an 8. if this were a 4, there'd be more options. Actually, let's fill in this column. This is a good idea, because this column actually has its digits fixed now. The digits on the whisper line are a 1. We've got a 2. We need a 3. We've got a 4. 5. We need a 6. We've got a 7. We need an 8. So the digits on the whisper line are actually 1, 3, 6, 8. This one's not a 3. So this is only low if it's a 1. Oh, of course, this isn't ever a 6, and that's never a 6, because 6 only goes in the middle. So this is going to go 6, 1, 3, 8. So, this has to go 6, 1, 3, 8. That's the only way it works, and so the 8 can't go in the middle. So that goes like that, I think, is the way that this all works out. I do know it didn't go 6, 1, 3, 8 the other way, don't I? Yes, because yes, because the 8's on the outside. Yeah, the 8's on the outside. 6, 1, 3, 8. That's the only way it works. And this can't be an 8, so that has to be the 8. Oops. Except I then... So yeah, I had that right. Chat was confused. Oh, why am I doing it in that order? Yes. Okay, no. 6, 1, 3, 8 is not correct. 6, 1, 8, 3 is correct, but unfortunately that puts the 8 in the middle. So the middle is 1 and 8. So this I know is a 1, 8 pair. That's not a 1. It's a 3, 6. Yeah, I was somehow in my head flipping those around, which is not especially helpful. Okay, so one of these is a 1. 1 only connects to 2, 4, and 5. So that means one of these two cells is a 2, but I guess I already knew that. It's going to be a 1 going into a 2. This 5, no. And the 8 connects to... So yeah, so one of these is a 2. The 1 only connects to a 2. The 8 connects to a 7 and a 4, which aren't available. They're over there. A 5, which isn't available. It's in the box. And a 6 or a 9. Well, the 8 can't connect to the 9, because if the 8 connected to the 9, it wouldn't be able to connect to the 2. So this is actually a 2, 6 pair. That's the only way that this works, because I need to connect something... I need two things that connect, where one of them connects to a 1 and the other connects to an 8 without repeating stuff in the box. And the only way that combination of things happens is if the 1 connects to the 2, connects to the 6, connects to the 8. So that works out what that is. So that does a lot of damage, because first of all, that makes that cell a 9. And probably the easier way to articulate that was that this cell, that I could not possibly put a 9 here, because it would not serve as an appropriate bridge. But anyway, that 2, 6 makes that a 3, and that a 6, and that a 3. And 6 goes to 1, goes to 8. So now 1 goes to 2, goes to 6. 5 and 8 are both next to 4. And are both next to 7. So actually, this is not resolved yet. This isn't a 9 anymore by sudoku. Let's see. Row 2, column 2 is 3. Yes, by sudoku. This 3 sees up here, so this is a 3. Thank you. I'm being told I should put an 8 in column 4. Wait, we already have an 8 in column 4. But that 8 does look over and disambiguate that has been hanging out for a while. Now, I do have a 1, 2, 9 triple in this column, which places an 8 there. So that is what Ben was pointing out. Good spot. So that is an 8. One of these two is a 9, but I don't know immediately which one. There's a 4 looking up here, so that's not a 4. Let's see. The last 8 is in column 7. We should probably go ahead and fill that in. Yep, so that's an 8. Thank you, Chet. The box 6 with... Oh, yeah, this digit is opposite a 9, but this is not a 1 or 2, so... or a 4, so the only thing that can go here is a 3. 3 is only next to 2, 5, and 6, so this is not 1 or 4 by keyboard logic. So that makes a 4, 5, 6 triple, so these two digits are the remaining things. So they are a 1, not a 2, 3, 4, 5, 6, 7, 8, or 9. So these are a 1, 9 pair. So this needs to connect to both 1 and 9, and the only thing that connects to both 1 and 9 is 5. So that's a 5. So that's a 6, and that's a 4. Hopefully that works. So 1, 2, 3, 4, 5, 6. This is a 7, making that a 9 and that a 7. This is a 6 by Sudoku, so that's a 5 and a 6. These aren't 6. Let's see. The 4 here finally disambiguates what's going on over here. So that's a 7. And this is a 1 or a 2. It's not a 9. So the 9 in the column goes that a place. So that is that. Okay, so this connects... let's see, row 6, column 8 cannot be 1 by Sudoku. Yes. So that's a 9 and a 1. So that 1 looks back over here, says that's a 2. That's a 4, while we're completing Sudokological phenomenon. So this is a 1, 2, 3, 4, 5. 1, 5 pair to finish this in that order. I'm not sure if we used this line, but anyway, that 1 looks down there. That's a 4. That's a 1. So now let's just fill in the rest of this box. 2, 3, 4, 5, 6, 7, 8, 9. These aren't 4 or 9, so they're 6, 7. These aren't 6 or 7. So that's a 7 and a 6 and a 4 and a 9. The 1 looks up here and gives us a 2 and a 1. Oh, and we're not quite done. What am I missing? Uh-oh. How did we finish this with a 4-5 deadly pattern? That's problematic. Row 1, column 8. Oh, yep. Yep. This fixes it because this needs to connect to both 7 and 9. Somehow I was looking at this cell and thinking both of them connected to 7 and 9, but this one does not. So yeah, this connects to both 7 and 9. Well, 4 doesn't. So that's a 5 and a 4 and a 5 and a 4. And that does the puzzle. Very nice. Ooh, excuse me. Good day of puzzling. Good day of Simon puzzling as well. Yeah, because you almost have to have a number pad in front of you to be solving the puzzle. I think it's probably not that bad to solve. Yeah, if you have a laptop keyboard and you're looking at the digits across, then that would probably be very unpleasant. Although even then, you probably have the number pad that pops up in the Cracking the Cryptic app. So yeah, there was a lot of very careful finagling that the setter had to do in this puzzle to make it so that you could make these sorts of geometric deductions. So I think my favorite one was the realizing that because this ended up being a 4-5-6 triple, this ended up having to be a 7-8-9. That was my that was what I thought was like really chef's kiss. That was my favorite move out of this whole thing. I mean, doesn't solving on a phone always suck? I feel like the best possible case for solving a Sudoku on a phone is very, very bad. But yeah, this is a cool idea for a puzzle. I feel like it might be just a little too open to make a whole bunch of these. Like, you might have to somehow, I don't know how you would do this, but I think in order to make a bunch of puzzles like this, I think you would need to make this slightly more constrained. I don't know exactly how. Like, maybe orthogonal moves instead of king's moves would make it slightly more constrained. Because it really did require... This is not a complaint about this puzzle, but it's very clear how much effort the setter had to put in this puzzle to make the interesting geometric things actually come to fruition on the grid. And so I think you would not want to make a whole bunch of puzzles with this mechanic, because I think there's so much flexibility. I think you might go mad. Also, if you did orthogonally, you could do the whole like black-white digit thing, which would be cool, because you'd know that everything you did would have to sort of bounce between the 2, 6, 4, 8 set and the 1, 3, 5, 7, 9 set. So yeah, that I assume someone has done this. I highly doubt that it is a creative and original idea, but I suspect you could do one with orthogonal moves and it would be cool. Alrighty, well, I should probably wrap up stream approximately here for today, but it's been a blast. I've had a lot of fun with all of you. It was a lot of fun to watch the new Simon solve of Distinction with you. I have a new puzzle coming out, premiering, I believe, on Rank's stream on Saturday, that I think is really exciting, so I hope to see you all there to celebrate Rank's 100th stream. By the way, if you have not previously been informed, Saturday is Rank's 100th stream, so instead of me streaming after Rank's, it's just going to be Rank's, and more Rank's. But I will be guesting, among many other guest stars, on Rank's stream on Saturday, so you want to be sure you show up to Rank's celebratory stream. It'll be fun. I look forward, though, to seeing you hopefully then, and if not, I will see you next week. Have a wonderful, wonderful day, evening, morning, whatever time of day it is, and I hope to see you all very soon. Thank you all for stopping by. If you have not yet subscribed, please do so. Again, I want to say such a huge thank you to all of the patrons for all of their help and support. It really does help keep the channel going and help us get our studio set up and recoup some of the costs of getting everything set up. Anyway, if you want to become a patron, patreon.com/zetamath. No pressure if you are under any financial strain whatsoever. Definitely don't feel any pressure to. But if you would like to give a little bit of money, by all means, it's appreciated. But always we appreciate subscriptions and likes. And people have started commenting on the videos, which has been fun, because it's a lot of fun to sort of bounce back and forth replying to people in the various VODs of things. So if you want to go back and see some of my old solves of puzzles, see if you think I've gotten better or not, you can go back and look at those and make comments. That's fun too. Anyway, have a wonderful day. See you all soon. Thanks for watching.